very good morning to everybody at the TransHyDE Scientific Conference. And I welcome you wherever you are, whether in live stream or here present in Berlin at the Harnack House of the Max Planck Society. My name is Dorothea Mischenborn. I'm member of the TransHyDE office, and I have the pleasure to conduct you through the day today and our program that we have jointly put together with our TransHyDE projects. The topic of today is overcoming techno-economic and regulatory barriers towards an efficient green hydrogen economy and storage and transport infrastructure. I'm very happy to be here with you together. And before we start and go deep into the topics, I would like to point out some organizational topics. One is just for the people here inside. So I need to inform you, in case of an emergency alarm, please exit the room via the door and then go outside of the building, either to the front or to the terrace in the direction of the garden. And the gathering point would be in the garden area. You find signages around the building as well of the emergency exits. The same applies for the smokers amongst you, so please use the pathway to go outside for smoking. It's both possible on the terraces or in front of the house. Then I have a short note for the speakers. Our technicians ask us that you please use the speaking desk and that you can move and be on the stage as well, but it would be good for the live stream to do the presentation from the speaker desk. Thank you very much. And we have the possibility during our presentations that you as an audience can really get into discussion with our specialists. And we use a technique which is called Mentimeter. And so please take out your mobile phones because you need it in order to sort of address the questions through the chat function of the Mentimeter. And how do you do it? You can either scan the code which you see on the slide with your mobile, or you can go onto the website menti.com and use the number code that you see on the slide presented here. And in order to see whether it functions, we would like to test out a question with you. In the live stream, we would be interested to know from which city. So please scan the code and we get sort of type in your answers and let us check out from where you are joining. Oh, I see Berlin, Essen, Hamburg, Munich, Leipzig, Freiburg, Cologne, Kiel, Prague, Mülheim. So all over Germany, that's wonderful. Offenbach. Thank you very much. We also have international participants. I see Prague joining. Bonn is there, Rostock, Leipzig. So we get a whole sort of magnitude. We are locally here in Germany, and we are also connected internationally. Wonderful. Thank you very much. Let me just briefly give you an overview of what you can expect of today. We will start with a brief overview of the energy supply security, and also touch upon the point of the perspectives of a hydrogen infrastructure. And then we will go into the energy vectors that the TransHyDE project, which is funded by the Federal Ministry of Education and Research, with about 135 million euro, is addressing. And this is gas hydrogen, it is the vector ammonia at hydrogen carrier. It is also liquid hydrogen, as well as liquid organic hydrogen carriers, or LOHC, commonly said. And then we go into sort of the topic, because even if we tackle all the technical issues, then we need to go into the application. How can we really apply what we have developed? And so we look at standardization, at certification issues, maybe also what the rules and regulations are in this area, and also look at the regulatory framework today, and bring the topics that we have been discussing during the day to a panel discussion with honorable, respectful scientists, also members of the political area and of industry and the public domain. And we are very honored to have special guests. So we have the ambassador of Australia to Germany here, His Excellency Philip Green. Thank you very much for joining. Warm-hearted welcome to you. And we will also have Federal Minister of Education and Research joining us in a virtual keynote in the afternoon. Honor and delight to introduce to you now the first speaker. And it's Professor Dr. Mario Rackwitz. He's currently director of the Fraunhofer Institute of Energy Geothermal Systems, also called Fraunhofer IEG. He is also in the Fraunhofer community. He's the spokesperson of the Hydrogen Network. He's the scientific director of the Fraunhofer Cluster for Excellency in Integrated Energy Systems. He also chair in Integrated Energy Infrastructures at Braunschweig Technical University. He holds a professorship also in Freiburg University, and he is guest and honorary or part-time professor at the Florence Institute. Together with Robert Schlögl of the at the Max Planck Society of the Fritz Haber Institute here in Berlin, and also with Jimmy Langham, CEO of Crew 21. He is TransHyDE coordinator and responsible for the strategy and also the implementation of the whole project. And he will give us an overview of the current situation, and his speech is called Current Challenges of European Supply Security and Perspectives of a Hydrogen Infrastructure. Please welcome Professor Mario Rackwitz together with me with a great applause. The floor is yours.
Thank you very much. It's been to be here and to open the scientific conference, the TransHyDE project, and thank you for the kind introduction, Dorothea. The only correction, it's at the Brandenburg Technical University in Cottbus, but everything else was correct. So we are in a very intense situation of energy security in Europe and the introduction of a hydrogen economy and infrastructure at the same time. Actually, tomorrow in 20 months, or 20 months ago, project TransHyDE started. And 2 years ago, I remember well sitting together with Robert Schlögl and Jimmy Langham, thinking about the proposal and the final steps. And with many of you here in the room, we have elaborated on the key elements of a technology value chain that would be needed for introducing hydrogen and building up the infrastructure. I have the feeling there's something in terms of acoustics. Can you all hear me? Okay. So I would like to just briefly outline what is the overall challenge? Probably most of you know this graph. We have the very tight ambition to reduce carbon dioxide emissions globally to 0 until mid of the century. And if we don't want to go into massive negative emissions by after the year 2050, we have to mitigate emissions radically, and hydrogen and direct electrification will be key technology elements for that. And so we have looked also on behalf of the German Hydrogen Council at the wealth of European studies to mitigate greenhouse gas emissions to by 90 to 100%. And most of these studies, of course, reach the target because that's their aim, but they show differences in the way the target would be reached, and particularly on the role of hydrogen and synthetic fuels. The range of final energy demand in Europe is somewhere between 6,500, 8,500 terawatt hours. We can use some biomass for it, up to 1,500 terawatt hours of sustainable biomass, and up to 2,000 terawatt hours in the maximum of local renewable energies, solar and geothermal energy, and environmental heat. But then the main part has to come from renewable electricity in Europe or outside Europe, and the big question is which share of that will be used by direct electric applications like electric cars and electric heating, or by synthetic fuels typically based on hydrogen and then transformed into other derivatives like ammonia and methane, etc. And when you look at the European studies of the Commission and other actors in the field, then you see the wide range, and this is mainly due to the fact that the key applications of hydrogen there's still uncertainty, but also due to the fact that it is unclear what is the optimal infrastructure and whether we can build up the infrastructure at reasonable cost to supply the European economy with low carbon fuels. And therefore, we have looked at the different variants, and in particular in TransHyDE, we build up models that can build a digital twin and show the transition path towards a zero carbon economy based on synthetic fuels like hydrogen, but also considering the interaction with the electricity sector. And this interaction is the main unsolved element in the system analysis until now, and TransHyDE will be one of the first projects building up those tools in order to set up system development plans. I will come to that. But this was the picture essentially 2 years ago. The war in Ukraine and security of supply issues for Europe weren't existing to the extent that we witness them today. And therefore, just a short picture on that, we have in Europe and here in Germany increased the share of imports of natural gas, crude oil, but also coal over the last decade, and have more of 84% import dependency on natural gas in Europe, more than 96% of crude oil. And the big question is how to secure energy supply and at the same time reach climate neutrality. And we see member states in the European Union are different or vulnerable at different degree. Germany in particular shows a high share of Russian imports, but also other member states like Italy, Hungary, Poland, and the Czech Republic. And we so have to look at the next couple of years, 2 or 3 years, in order to secure energy supply, to keep our economies running and the industry in Europe. And when looking at the perspectives for Europe and possible import alternatives, we see that LNG, of course, is a key element for reaching security of supply of natural gas, and therefore onshore LNG, but also FSRUs, so LNG based on regasification terminals floating regasification terminals will increase rapidly within the next 2 years. And we see that if we reach the energy efficiency targets and reduce energy demand at the pace that has been set out by the REPowerEU perspective and the Fit for 55 program at the European level, then we will be able to reach security of supply by the year 2025, 2026. However, energy infrastructures are a key question mark on that. We can reach energy security of supply in overall energy balance terms, but will we be able to transport the gas from LNG terminals also to the demand centers in Europe within the next 2-3 years is an open question. And that was also one of the questions that was addressed by TransHyDE members. The TU Berlin, Fraunhofer Sky and Fraunhofer IG, for example, worked on an ad hoc paper on that. And one key result of that was that security of supply can be reached provided that we reduce energy demand by at least 20% compared to last year's levels, and that we realize the already planned pipeline and interconnector projects to neighboring or within Europe between main countries like Spain, France, but also between France and Central European countries, and also between Italy, Austria, and Germany. And so building new LNG terminals will play a key role. Here in particular, 4 terminals are planned in Germany, and converting compressor stations to reverse flow. So we have to be able to let the natural gas flow from Western Europe to Eastern Europe as compared to the flow direction that was planned with Russian natural gas. And therefore, we had a first really very pragmatic and important application of the toolbox that is provided by the TransHyDE Consortium on answering key questions that came up during the last months. And we spent quite some time on that in providing those calculations, and had also a strong political impact in discussions also with transmission system operators on transforming the European infrastructure to a natural gas system that provides security of supply for the next 3 or 4 winters. But then this has to be transformed further in order to also allow a transition to low-carbon hydrogen and derivatives. And therefore, this has also been addressed by the European Commission in this very ambitious plan, REPowerEU, which fits very well to the ambitions which we address with our analysis within the TransHyDE project, in particular reforming the European economies by reduction energy consumption. So we still have to reach the energy efficiency targets within the next decade, but also until mid of the century. On hydrogen, the REPowerEU package probably has the most ambitious plans that we have ever seen in Europe. 20 million tons of green hydrogen by the year 2030, or zero carbon hydrogen by 2030. And half of this 20 million tons should be based on domestic production, and the other half, 10 million tons, should be based on imports. And here we, of course, have big tasks to fulfill in order to analyze possible import routes, infrastructures within Europe, etc. Of course, the renewable power production has to be scaled up massively to about 1,000 gigawatts of wind and PV in order to reach also the domestic satisfaction of demands for hydrogen, but also direct electricity. And this will require large investments. Additional 200 billion euros are foreseen by the European Commission. But in order to really analyze and understand the transition towards green economy and carbon neutrality by 2045, we have to understand where are the demand centers for
green hydrogen, green electricity located, where could the supply come from, and what are the infrastructure needs in between. It's unfortunately impossible to address these very deep and intense questions within the next 10 minutes of my keynote presentation, but I think we will provide a lot of results within today's conference, also the next talk on energy system analysis, but also for the rest of the day and the remaining of the project. One key message that can be given already, and which is also one of the funding principles of the system analysis within TransHyDE, is that we have that these questions cannot be addressed independently, but the interactions between demand, supply, and the different infrastructures have to be considered intrinsically. First, we have to look at the demand for hydrogen in particular. Here, just for the example, and the main demand sector shown is the energy-intensive industry. Here, in particular, basic chemicals, iron and steel, as key demand sectors for hydrogen. And so here shown the forecast database of Fraunhofer ISI. And when looking at the 5,500 companies at the EU level that belong to basic industries, which could be major hydrogen demand industry clusters, we see here in particular shown for the chemical industry and also steel production, large demand centers in northwestern Europe, for example, and other clusters distributed within Europe. And this gives a first indication of hydrogen infrastructure needs here, in particular also within the next years, connected to harbor infrastructures and hydrogen pipelines, which could supply from southern Europe and from production potentials within Europe. At the global level, of course, we know the very sunny regions of the globe. Australia is, of course, one of the key regions we look at, but also Northern Africa. The United States is, of course, one possible candidate as well. But we see, of course, that the advantages, the benefits of sunnier and windier regions are partially compensated also by transport costs, and therefore we have to optimize the overall picture and find the optimal infrastructure of hydrogen production globally and transporting hydrogen to Europe. And we are looking at that also at, from the global perspective, at the cost of hydrogen potentials and infrastructures. And the first programs are actually running on that or being implemented. Here, for example, or as the main candidate, the H2 Global program, which provides currently roughly 1 billion for international hydrogen imports. And we will also set up hydrogen production and demand programs for European domestic hydrogen supply. But then, once we have a full picture of hydrogen demand, here particularly in basic industries, hydrogen supply internationally and within Europe, we have to look at the infrastructure needs within Europe in order to bring the hydrogen and derivatives to the demand centers. And the first plans on the European grid have been sketched by the hydrogen backbone at European level and the hydrogen start grid or backbone at the German level. And we see that major parts of the existing natural gas infrastructure can be transformed to transport hydrogen. However, a fully economically optimal transition picture of integrated infrastructures, electricity and gas, including the different storage needs for hydrogen storage in particular, have not been published yet, because we are in a situation where the infrastructure analysis is based on independent and disconnected analysis of electricity and hydrogen and gas grids based on the electricity and gas network development plans. But this will now be changed in order to transform the analysis in integrated system planning and an integrated system strategy, both in Germany and in Europe. In Germany, we have started with integrating supply into different infrastructures in the so-called long-term scenarios for the Ministry for Economy and Climate. But this is only the first step. We have to go a step further by integrating supply, demand, and all infrastructures. And this is actually the key challenge which we will address here within the TransHyDE project by fully integrating the assessment of supply of green electricity, demand for green energy carriers, both electrons and molecules, and modeling the optimal transmission grid for electricity, natural gas, and hydrogen in between. And there are grid-based multi-energy system models which are used within the TransHyDE project and which are connected with many other sector-specific models for hydrogen here in particular within the TransHyDE project. And the first draft assessment has been provided, and we will discuss that probably also in the next presentation, where we have located the hydrogen demand for energy-intense industries. And based on the first draft assessment coordinated by the TU Berlin, we have, or we can see the picture of a German backbone grid for hydrogen, which connects the main supply and demand centers here, in particular based for energy-intensive industries, steel, chemical industry, and process heat, where a total grid of 8,000 kilometers is modeled and which is capable also for further transport needs. And this is really only the first step. We have also accelerated some of the steps and tasks within the TransHyDE project, but within the next year, we will then really enter production and publication mode on more results within TransHyDE on these infrastructures. So the main conclusions of my short introductory keynote today are that sector coupling based on direct electrification and hydrogen use will be the dominant property of future climate-neutral energy system. Sector coupling in that respect will serve both climate neutrality and providing the basis for a secure energy supply in Europe. The share of electricity-based sector coupling versus hydrogen synthetic fuels is still characterized by large uncertainty in the system development plans which we see today. And TransHyDE will provide key methods and data and analysis in order to reduce this uncertainty. Besides the uncertainty in input data, there's a key reason for this is actually the fact that integrating modeling technologies are not used and developed today, and that will be provided within the TransHyDE consortium and TransHyDE project, and therefore the detailed assessment of hydrogen demand supply within Germany, within Europe, is a key element. And here we base, of course, the assessment also on demand projections of the industry, the demand sectors, and develop a fully integrated picture and a vision for the hydrogen transition in order to then build the infrastructure and plan our system in an optimal manner. And with this, I'm really looking forward for today's discussion and the further presentations this conference. Thank you very much.
And setting the framework for all the other topics that we will discuss during the day and present to you. We thank you, and As discussed, we will gather all the questions together that you have from the keynote as well as from the next presentation, which is very much coupled to the presentation that Professor Rackwitz has given us right now on demand and supply and on the infrastructural needs. So we will gather your questions and tackle them together then after the next speaker. And I'm very honored to present you as next speaker, Dr. Joshua Fragoso Garcia. He has worked many years in the solar thermal industry and also in the photovoltaic industry. And he studied in the Netherlands and in Sweden and focused with his studies on environmental pathways for sustainable energy technologies. He obtained his PhD at Karlsruhe Institute of Technology, and currently he is working in research at the Fraunhofer Competence Center for Energy Policy and Energy Markets at the Fraunhofer Institute for Systems and Innovation Research, abbreviated ISI. And he is giving us a speech on a systemic perspective on Germany's, EU's future hydrogen system, what are the needs for hydrogen infrastructures under alternative scenarios. Please let us welcome Dr. Garcia on the stage.
Thank you very much. Can you hear me? Yes? So, welcome to my presentation. As it has already been mentioned, my presentation will be on the system perspective in Europe and Germany and the needs that we derive from the hydrogen infrastructure. From a scenario, well, we will look into two different scenarios. I would first like to introduce the scenarios to you from a hydrogen demand perspective. We will take a look into two different scenarios. The first one is called S2 Chem Steel, and in this one we see the demand into three different sectors. The first one is the industrial sector, the second one is the transport sector, and then the building sector. In the first one, in this scenario in the industrial sector, we see the demand for the feedstock, steel, and certain heating process, basically the high heating temperature process. For the transport, we consider a highly electrified transport system where there are just synthetic fuels used for the aviation sector and ship transport. And for building, there is no direct use for hydrogen in the heating sector. In our second scenario, we call it S5, all sectors. Well, here we consider the demand of the first scenario plus other demand. In industry, we consider the demand for the overall heating of the industrial applications. In transport, there is the hydrogen application for the trucks and a small part for cars. And in building, we consider hydrogen for the decentralized heating in the building sector. Therefore, we can see that the hydrogen will increase from one scenario to the other one. If we look at the final energy demand of these scenarios in Germany, we can see that there is a decrease in the demand from 2018 to 2045 that occurs because of energy efficiency measures. We can also see that the hydrogen perspective that is here, the light blue, it increases, it starts in 2030, and it's almost twice as much in the S5 all sectors than in the S2 Chem Steel. Also, we can see that the demand, the final energy demand is higher in the S2 all sectors scenario, and that the electricity demand goes lower as more applications that were electrified now will use hydrogen. From the European perspective, we can also observe the same final energy use reduction due to the energy efficiency measures. Of course, here it goes from 14,000 terawatt hours to around 9,000 terawatt hours. Similarly, we have twice as much hydrogen in 2045 for the S5 all sectors scenario compared to the S2 Chem Steel scenario. similar way, there is the lower electricity demand for the S5 all sector scenario. And yeah, that's what I can say. Well, now, if we want to see this demand and we want to analyze how to supply the energy for this, as Professor Mario Rawitz has said, we need to consider the renewable energy sources that we have available. Therefore, the first step in our energy system calculation is to calculate the renewable energy potentials available in Europe. For this, we first start with two different sets of data, the area data and the weather data. The area data basically comprises the land area uses, the protected areas, natural protected areas that we will exclude from our calculation, and some other technical restriction, like the slope in the mountains. We take this set of data and we make a specific calculation to find out how much land we have available for the installation of our renewable energy systems. Then we have the weather data. That, of course, comprises wind speed, radiation, temperature, and we have data worldwide in 800 to 20,000 world stations, approximately. Then we do, again, technology-specific calculations for photovoltaic, CSP, and wind, and we obtain the availability for each technology in the area that we are considering, and we can obtain weather time series, so photovoltaic time series and wind time series that will let us know how much energy we have available. Then we take these two sets of results and we integrate it into a model grid. The model grid is composed of tiles. Each tile has a resolution of 7 by 7 kilometers, so we have a high geographical resolution. And in each of these tiles, we have the results of the costs, the full load hours, and the available capacity in megawatts that we may install in our tile. So we have the results for the wind, photovoltaic, and CSP for each tile. In the next slide, I would like to show you some results. This is the wind potential per tile in megawatts in Europe. We can see that we analyze wind offshore, and therefore in wind offshore we have the highest potential in megawatts that is represented here in the yellow color. In the purple color is the lowest potentials, and we can see that, well, in general, compared to the wind offshore, the potential is lower. However, there are some green areas in Spain, in Sweden, where we may install a lot of megawatts. For the photovoltaics, also, we have here integrated together the photovoltaic on roof and the photovoltaic in utility scale. And we can see that the main sources of land that we may use is actually the cities, the urban states that we can identify here, Berlin, Paris, and several other cities, and the barren areas that are available in Europe, basically in Sweden, in Spain, some in the mountains in Switzerland. The next slide is the specific cost for wind. We can see that the North Europe has lower costs below 40 euros per megawatt hour in 2045. This is really promising. However, we can see that there is a contrast with Southern Europe, where we have purple areas that they represent higher costs, like in Italy or in Greece, that they basically have no wind resource. Therefore, they have a lower cost per megawatt hour produced. Just to add, for the wind offshore, although it had the highest megawatt that we're able to install, here we have considered the grid connection, and therefore the price for wind offshore is higher than for wind onshore, even though the resource is higher. Now I show you the specific cost for the photovoltaic in utility scale. We can see that in Central and Southern Europe there is an affordable resource, really under 40 euros per megawatt hour, with resources going under 30 euros and even under 20 euros per megawatt hour in 2045 in Southern Europe, basically in Spain, Italy, and Greece. In Northern Europe, for obvious reasons, the resource is more expensive. Now, when we see the numbers for this together in a graph, in this graph we have the potential in terawatt hours for each specific cost in Germany in 2045. So we can see that starting at under 40 euros per megawatt hour, there is already a considerable resource that is around 500 terawatt hours. And there are two cost step jumps. One that goes from 600 to around 900 terawatt hours, that is led by the photovoltaic on roof installations, that they come under 70 hours 170 euros per megawatt hour. And the second one, the wind offshore capabilities, that they come in the game under 80 euros per megawatt hours. Now, for the European perspective, we calculate a considerable potential, that is 12,000 terawatt hours under 60, around 12,000 terawatt hours under 60 euros per megawatt hour. Here, the photovoltaic on roofs plays a lower role as compared to Germany. There are less cities in all Europe. Germany has a high population density. And here we can also see that there is a small fraction for CSP production in the order of hundreds of terawatt hours. We can see also that the wind and photovoltaic technology potential is the dominant potential. Now, I would like to talk about the system perspective. And first, then, I would like to tell you how we calculate the energy supply for this demand and using these renewable potentials. For this, we use the system model Enertile. Enertile is a supply optimization model from the cost perspective that takes the given demand and we find the lowest possible cost to supply the energy for this demand. It covers 3 different energy sectors, coupling them and analyzing them together: the electricity sector, the heating sector, and the hydrogen sector. Besides the demand, we have to feed the system with other data, like hourly weather data, available areas, existing generation facilities and infrastructure, techno-economic assumptions, political restrictions or political goals, and CO2 limits. Now, for each one of these systems, Enertile will calculate the capacity expansion and dispatch of the different generation technologies. For that, it will use the renewable energy potentials that we calculated previously. And in this case, especially for hydrogen, it will calculate the capacity expansion and dispatch for electrolyzer technologies and hydrogen storage. We consider for this analysis the years 2030, 2035, 2040, and 2045. And Enertile provides hourly resolution in these years. And it considers, well, as I said, different flexibility options, like on the demand side, like heat pumps and electrical cars, electromobility. So among the restrictions that we provide Enertile in our simulation for TransHyDE were the German and climate policy goals. First, nuclear and coal will be phased out. Second, are the goals for the renewable energy installations. For wind onshore, we have in 2030 115 gigawatts, in 2040 160 gigawatts. Wind offshore, 30 gigawatts, 40 gigawatts up to 70 gigawatts in 2045. Photovoltaic, 215 gigawatts in 2030, up to 400 gigawatts in 2040. And we also implemented the national hydrogen strategy, which considered the installation of 10 gigawatts in 2030. We also consider almost a phase out of biomass in the conversion sector in 2030. Other assumptions, the price for the energy carriers and CO2 price. We here consider the natural price, 25 euros in 2030, 40 euros in the further years. These calculations were done before the Ukrainian effect. And we capped the CO2 price in 2045 at 300 euros per megawatt hour. We consider non-European hydrogen imports, mainly in 2 ways: pipelines and ships. The pipeline comes to Italy and Spain from the MENA region. And the ships come to different ports around Europe depending on where the demand is needed. The prices for the European imports are given here. Of course, the pipelines are cheaper, and they go from 97 euros to 73 euros in 2045, and the ship cost in euros per megawatt hour are 117 euros to 95 euros per megawatt hour. We calculated this cost using a 2% WACC. That is the same WACC that we use for the whole of Europe. This was not to have a bias in favor of the European hydrogen production. However, the cost, this may be an underestimation of the cost of the non-European hydrogen costs. And then, as a further remark, Enertile will further calculate the hydrogen generation that it needs. I will then show you some results, starting with the electricity system results. This is the installed capacity in Germany in the studied years. We can see here that the political goals established play an important role, as both energy systems look really similar. And we can see that the political goals are followed: 200 gigawatts in 2030 for photovoltaics, 400 gigawatts in 2045, 160 gigawatts for wind onshore, and 70 gigawatts for wind offshore in 2045. I would like to remark that this is a huge challenge that we have to face as well. It's gone? Yeah, now it's coming back. I think, yeah. That this is a huge challenge that we have to face in Germany. Why? Because in red are the current installed capacities for photovoltaic, wind onshore, and wind offshore. And we can see that the difference to 2030 is huge. And this difference, well, there is not so much time left. We can also see that one of the differences between the two different sectors is the hydrogen use. The capacity of electrolyzers installed is higher in the S2 chem steel compared to the S2 all sectors hydrogen. These electrolyzers are used for no, sorry, this is not electrolyzers. This is fuel cells that are used for a conversion in electricity. Now, looking at the installed capacity in Europe, we can see that wind onshore and photovoltaics are the predominant technologies. Similarly, the installed capacity of fuel cells for energy reconversion is almost twice as much in the S2 chem steel and is in the S2 all sectors scenario. Here we have a little bit of gas in 2045, but that will be, the emissions will be removed through DACs. And well, we can also see that the goals of Germany of wind offshore lead the installation of wind offshore technologies. From the generation side, again, the political goals in the installed capacity lead the generation, and both the scenarios look really similar in Germany. Here we can, as a further remark, as the installation of photovoltaics comes really fast in 2030 and 2035, especially in 2035, we have a highest level of curtailment, around 22 terawatt hours in 2035 for the S2 chem steel scenario, and around also 23 terawatt hours for the S5 all sectors scenario. We can also see that there is energy imports, electricity imports into Germany, with a higher electricity import coming in the S5 all sectors scenario, 30 terawatts more. For the generation in Europe, we can see that, again, the photovoltaic and the wind onshore are the dominant technologies. However, wind onshore, due to the higher full load hours, they produce more energy than photovoltaics. And we can see here the nuclear that in the European perspective was not phased out. And the small presence of CSP is almost not visible here. Now, this is something that is really interesting. Here we have, if you remember the previous graph, we have certain potential that we may use in the certain countries. In this graph, the more red that the color is, that the country is painted, the more capacity has already been used, the more potential has already been used. Therefore, we can see that in the S2 chem steel scenario, most of Germany, a large part of France, large part of England, potential for the photovoltaic is already used. We can also see that a chunk of Poland, the south of Italy, is also used. When we increase the demand of hydrogen in Europe, we also need to increase the production of renewable energy sources within Europe. And therefore, we have around 400 additional gigawatts that they need to be produced. And this electricity production will come mainly from the Iberian part, that we can see that it colors fully red, from orange to red, from the Balkan part, that it also has an important resource in both surface and sun, and from Poland, and a small chunk from Norway. From the wind perspective part, we have a similar part. The S2 chem steel scenario, it's already painted red in several countries, like Germany, the north of France, England, and we remember that the North Europe was the one that had the cheapest resource. So we are already using the cheapest resources here. Now, for the S5 all select, we need to install additional 92 gigawatts. This additional 92 gigawatts will come mainly from Norway, that it paints in North Norway red, and from Sweden, that it paints from yellow to orange. In the Balkan region, we may use less wind, and this may be because of the lowest cost, because of the way Enertile optimizes the wind turbines. He might have decided that it was better for the hydrogen production to produce it in Norway than in Sweden. Now, hydrogen results. This is the generation and the demand of hydrogen. Above the x-axis, we have generation, and below the x-axis, we have demand. We can see on the left side the graph for Germany, and we can see that it's basically split between import from the European Union and domestic electrolysis. We can also see on the demand side that it's basically driven by the industrial sector. And in the S5 all sectors scenario, we have an important part for the tertiary sector. In the S2 chem steel scenario, the part for the transformation sector is higher. From the European perspective, on the supply side, we see that it's divided between the domestic electrolysis and imports from non-European countries. These imports from non-European countries play a role for the S5 all sectors. In 2045, they are around 12% of the total supply of hydrogen. Now, we can also see that the industry is the one that drives the demand. We can see here the hydrogen trade flows. And in both the scenarios, basically all the trade flows flow within Germany and within the Benelux area. In the left, we can see that there are trades that there are hydrogen flowing from England to Benelux area, from France to Europe and Benelux area. And we can see that there are two sources of non-European exports through Italy and through Spain, 18 and 117 terawatt hours respectively. The highest value for Italy is because they have a lower renewable energy potential. Now, on the S5 all sectors, we can see that the lines color into a deeper blue or deeper purple. That's because there is a higher flow of hydrogen. The directions are mostly similar, however, there are more rows. If we look into Germany, we can see that the flows goes from north to south, meaning that the electrolyzer capacity is installed where the resource is, mainly the wind resource. We can further see this in the electrolyzers capacity that is here in producing gigawatt electrics. And we can see that mainly for the S2 chem steel scenario, they are mainly installed in France and in England, with an important part installed in Poland, the Balkans, and the Iberian Peninsula. And of course, in the S5 all sectors, the volume of electrolyzers capacity increased, with Spain playing the bigger role. We observed that Spain painted red in the photovoltaic technology, and this energy will be used in the electrolyzers and to produce hydrogen. France and England, they are still an important part of it, with Norway and the Balkan regions coming next. Here we see the hydrogen storage for Germany, the needs that are required, and the seasonal variability through the year. We can see that for the S5 all sectors, we have a higher storage demand, around 60 terawatt hours. And an important part is that the wind drives the hydrogen production, as in the autumn, around 5,500 hours, the slope changes driven by the higher wind rather than through the solar technologies in the summer. Now, as conclusions, I would like to say that we observe that the Germany renewable energy installations are set by the political objectives, that there is a large amount of renewable energy sources needed when we want to produce more hydrogen, we want to use more hydrogen. That there are pipeline hydrogen imports from non-European countries in both the scenarios. There is a high installation of electrolyzers capacity in Spain, France, UK, Poland, and the Baltic region. And storage is needed for a seasonal balancing of the hydrogen supply in Germany of at least 50 terawatt hours. With this, I would like to thank you for your attention. And I don't know if we have some time for questions or if we go further.
Very much, Mr. Garcia. We do have time for maybe one or two questions from the audience, and I encourage you to ask them now. We have one up there. Please wait for the mic to come. Thank you.
Hi, Maria Greitzer, Fraunhofer. I have two short questions. First one, about the price for the natural gas. You lower in your energy supply methodology the price for natural gas from 25 to 14 euro per megawatt for the other upcoming years. My question is why? And the second one, I have a problem with one of the assumptions in the methodology, and that is German political objections define installed capacity. Are we maybe energy modelers, maybe we go too far with this objection?
Yeah, so the natural gas prices, they are based on the world energy outlook, and we consider a small reduction, well, as a strong reduction of them, based as the demand will be lower for the future years. For the restrictions, yes, I agree. I think it would be interesting to make a scenario without restrictions and to see what the Enertile model offers. However, in this case, as we consider them to see what was happening, and it really influences the way it will shape. And in the end, if Germany has those goals set, and we are trying to install that, then I think it might be a closer look to the real situation.
Thank you.
Thank you very much. Is there another question? Hauke, please.
So this is a question from the online space to Mr. Rackwitz. Who will be paying for the energy transition of the infrastructure? Will it be the industry, or will it be the, and therefore the end customer in the end, or will it be the governments?
Yes, very interesting and good question. Typically, infrastructure is financed in a regulated regime and is financed by grid fees. That is the traditional way to finance infrastructure, and therefore all customers and consumers of energy pay for the infrastructure. But of course, in the transition period, there could be additional incentives needed that are then financed by the government. We see, for example, currently the important projects of common European interest, as just one example, financing hydrogen projects, large-scale hydrogen projects, including infrastructure. And these IPCEI projects are financed by national governments, where the European Commission is giving, or allowing this within the state aid guidelines. And therefore, there might be a transition period where investment incentives are provided within the transition period for hydrogen infrastructures based on governmental funds. But in the long term, the target picture is that financing infrastructures will be based on grid fees and therefore paid by the customers.
Thank you very much. Looking at the time, I would encourage you, I saw there was another question, maybe to take that question into the coffee break. And Mr. Garcia, also Professor Rackwitz will be there, and you can address them directly personally. So thank you both very, very much, and give them a great applause. Thank you. And my pleasure is to introduce the next two speakers to you. And they are both members of the TransHyDE project Safe Infrastructure. We're sort of looking at the gaseous hydrogen energy vector, and of course, we need to handle it and tackle it in a safe way. And we have the pleasure to have the two next presentations. One from Dr. Frank Schweitzer. He is a mechanical engineer, having studied at Furtwangen and also Hannover University, and he holds a PhD of the Karlsruhe Institute of Technology. And already during his PhD thesis, he has been focusing on hydrogen effects on welded steels. And currently, he is team leader in the area of lifetime concepts for hydrogen applications at the Fraunhofer Institute for Mechanics and of Materials. He will give us a presentation of safety of components in contact with hydrogen. And I will introduce the second speaker of the TransHyDE project Safe Infrastructure to you already. and the presentations will be one after the other, and then we get together into a question and answer session. So the second speaker is Professor Dr. Jürgen Wöllenstein. He is a graduate in electrical engineering of Karlsruhe University and currently head of the Gas and Process Measurement Technology Department at the Fraunhofer Institute for Physical Measurement Techniques, the IPM. He also holds a professorship at the Freiburg University, and this is for gas sensor technology. He will give us a speech on hydrogen-sensitive gas sensors for safety applications. So the floor is yours. Frank, please go ahead.
Thank you very much for your kind introduction, Dorothea. So when we talk about a safe infrastructure, we always have components like pipelines, valves, storage systems, which are in contact with hydrogen. And in this case, we always can encounter the problem that the hydrogen can diffuse into the material, as you see in this picture. And normally the hydrogen can diffuse into stressed regions. And you see the two red atoms here in this picture. This can also lead, if you have small defects in your components or especially in steels, that you have a decohesion and that you have a crack advance in your components and bigger failure. So we are especially dealing on steels in this TransHyDE project. So we are talking a lot of standards and standardization things. We have two use cases. One is for pipeline steels. This is use case 1. And we also have components of power plants in the use case 2. And we mostly focus on experimental setups for the testing of materials. And also we look at the optimization of microstructures using modeling techniques. So what do we usually do if we test samples or components in the contact with hydrogen? We have these high-pressure autoclave systems. You see here, there's a tensile testing machine where you place your samples, and then you can put all things around. In this case, up to 1,000 bar. That's a very high-pressure system. And we also are able to give boundary effects, like if the pipelines are in the earth, you have around 5 degrees Celsius or something, so we can cool down or heat up the components also. So we do different things to quantify these materials. It's tensile testing, crack propagation, stress intensity with different sample sizes. So the problem here is that there's high test costs, really at high pressures, and these tests take a long time to succeed, and so there are no extensive material data sets available. So in the project, we also develop alternative testing methods, like these hollow specimen techniques. On the left side, you see there's a tensile sample, and then you make a borehole through the whole sample, and then you can fill the sample with hydrogen. So you then don't have the hydrogen from the outside on the sample, you have it from the inside. And therefore it's not much hydrogen, so there's safety is not so important in the laboratory. And we can do a lot more tests with that, but these tests are not standardized right now, and we have to look how we can do this as a standardized procedure. And in the project, we want to collect a lot of data with these samples and want to optimize, especially the pipeline steels. So there's first results on the left side. You see, I'm sorry, these pictures are in German. I only have these in German, these two. You see stress strain curves from the selected material. It's an X52 pipeline steel, which we use in this project. And you see there's a difference if you use the hollow samples between axial and longitudinal directions. But these tests, these stress strain tests, are not so important for us. So more important is when it comes to a crack. So, and this is what we do on the right side. So we didn't do tests here. We just had a look if we can use the hollow sample specimen technique for these kind of procedures. So I found some literature data for this steel and put it together. And normally you see you have a cracked or pre-cracked specimen, and if this, you have a crack advance. So this is the crack advances every step you do, and then stress intensity becomes bigger and bigger, the delta K, as you increase the load or if in the testing. And you see in the black line, this is pure air. And if you add hydrogen to this, then you get an elevated crack propagation. So the component will break faster. And you see here, this is the different colors are different regions in the material. You see there are differences if you have welded material or if you have a sound material, but this is not so strong prolonged. What we also do is low cycle fatigue. This is a very important test we have. This is a test we did with the hollow sampleman technique. For an X56 pipeline steel, a similar steel to the X52 one. And you see on the y-axis, you have, if you have a larger elongation on your sample, then the lifetime decreases. And you see in the red and blue lines or dots is the lifetime of these steels. And you see you have up to 10,000 cycles, which the material can last. But if you introduce hydrogen inside of your materials, this is going down up to or down to about 100 to 1,000 cycles. So this is not so much as you can think. You can also only stress the sample up to 1,000 times, and you have to have a very close look how it how your sample or how the component built of this steel is acting in real life. We can also do these experiments with temperatures and up to 300 bars. Then we also, if you want to have a final look, also, for example, if you have regions of small regions like heat-affected zones, we also build up a test system for microsamples. You see this coin, how small these samples are. You can take these out of your, for example, of your welds and put it in a hydrogen chamber, right now up to 100 bar of hydrogen, and you can test this. The good thing about this also is you can do this tensile test as I showed, you can do this low cycle fatigue tests, but because the samples are so small, you can also do high cycle fatigue tests in this setup. And if you want to have even more closer look, you can do EBSD, for example, in your lab, and you see you have in the bulk material, or you have different zones in your heat-affected zone. So therefore, you see these are really quite small zones. You have to put microsamples out of it to have it in your microsample setup. And if you want to have a more closer look, we use numerical simulations. So we take these EBSD pictures, put these into 3D representations, and do numerical simulations. So we couple this with crystal plasticity models. We determine diffusion coefficients, solubilities, trapping phenomena in experiments. Then you can calculate, for example, you strain this representative volume element, and on this picture you see the results. These are the local trapped hydrogen in materials which you cannot distinguish from in an experimental or in experiments. So you have to do it with numerical simulations. And last results, we use the simulations not only for these small regions. We take the result from these representative volumes, put it to macroscopic components. For example, on the upper side, you have a blunted crack, which is stressed in one direction. And you see, because of the stress field in front of this, you have an elongated or more hydrogen at the crack tip, which will lead to elongated fracture. On the lower part, there's a simulation of a low cycle fatigue experiment. You also see on the sharp crack at the end, you have more hydrogen than you have in the bike material. So with these simulation techniques, you can have a look inside of the material, which you can not have with experimental experiments you do. The next steps will be that we model degradation mechanisms like localized plasticity or hydrogen-enhanced localized plasticity, hydrogen-enhanced decohesion, but that's ongoing work in the project. I'm sorry, this is 2 times. I'm going back, it's my fault, sorry. Yeah, last but not least, we validate our experiments with a fractographic analysis in the scanning electron microscope. Like you see here on the left side, you have a ductile behavior in air. On the right side, if you put hydrogen in pipeline steels, you have a brittle fracture. You see a brittle fracture. Also, you can look further into the material and see the cracks because of hydrogen. You can distinguish these from other cracks. Yeah, and in the project, we are using this to find position of initial defects, of crack paths, embrittled areas, everything you need to that you can quantify qualify your components. As I said, we use all these techniques for 2 use cases, and we always put these into standardization and activities. And yeah, this is very important that we can have real components or can calculate real components in the safety for a safe infrastructure. So as a summary, we have the safety of components in contact with hydrogen can be determined by experiments. We can do static cyclic materials. We can do numerical simulations or multi-scale simulations to determine these experimentally. And we have different use cases which we will regard. And we'll do this in standardization processes. So thank you very much for your attention, and hoping to can give you feedback on your questions after that.
We pass directly on to Professor Jürgen Wellenstein with his presentation, and we gather your questions in the subsequently.
Thank you, Dorothea. Good morning. My presentation. Einfach weiter. Next. Okay, I'm talking about hydrogen sensors for safety applications. And safety is an important topic in hydrogen technology. Why? If you look at this slide, at the left, you see the lower explosion limit of hydrogen in air is 4%, and the upper explosion limit of hydrogen in air is 77%. This is a wide range. If you compare this with natural gas is mainly methane. You have a lower explosion limit of 4.4% and an upper explosion limit of 70%. And the sensor people and the sensor companies develop since decades methane sensors, but no hydrogen sensors, because hydrogen sensors were no market. Only a very small market. And okay, and safety is really a challenge and very important for us. If you look at this picture, 3 years ago, a hydrogen fuel station in Norway explodes. This is not good for the acceptance of hydrogen technology. So we need sensor to improve the safety of the technology. And we started 20 years ago with the development of hydrogen sensors for the automotive industry, for the fuel cell cars. And in these cars we use a very simple detection principle, thermal conductivity. Because hydrogen has a 7 times higher thermal conductivity than all other gases except helium. But we don't have helium in our technology. And we use only the measurement of the thermal conductivity. We have a heater and we apply a heating power, and if hydrogen is present in ambient air, the heater will be colder. Easy measurement principle and long-time stable. This is, for example, in heater, this is a USB stick for some customers of us. Okay, it's low cost. Measurement of the thermal conductivity, 7 times higher than other gases. And you have to measure 10% of the lower explosion limit of hydrogen, and this is possible. Okay. Then we work. These thermal conductivity sensors are state-of-the-art in the moment. Then we work on another detection principle. This is speed of sound. Hydrogen has a 4 times higher speed of sound than other gases, except CO2 is a little bit a problem. And if you want to measure the speed of sound, you need a sound source and a microphone. And for example, in my mobile phone, there are 3 microphones and electronics, and Apple pays 20 euro cents. So it's possible to set up a very low-cost system on this principle. Okay, and the measurement principle is you have an acoustical resonator, an organ pipe. And the frequency of this organ pipe will change with the hydrogen concentration, because the speed of sound will change with the hydrogen concentration. For example, this setup has a detection limit of 18 parts per million. This is very sensitive. But we have one problem, CO2. CO2 changes the speed of sound too. Okay, we are working on this. We start working on ammonia sensors. There was nearly no market for ammonia sensors in the past. A little bit farming, a little bit chemical industry. And I will not go into detail. We try to measure ammonia optically, absorption of light. And we started with the development, we can detect 100 ppm ammonia in 1 meter range, remote detection, but our goal is 100 meter. Yeah, we start. But ammonia sensors, there was no market for, and nobody developed ammonia sensors. Okay, this is our setup. Another possibility to detect hydrogen is Raman scattering. Normally, Raman measurement systems cost 100,000 euros or more. For some applications, it's possible to use this high-end setups, but we try to build a low-cost Raman system, and you can measure with Raman scattering very, very selective hydrogen concentrations, nearly without cross sensitivities. That's an advantage of the technology. Here you see the Raman spectrum, and we set up an optical Raman system with a laser and not with a spectrometer to measure all these Raman Banden. We use a filter, and this is our goal within TransHyDE to develop with a company, partner of TransHyDE 2 and Hauser, and cheaper, low-cost Raman spectrometer to measure the purity of hydrogen. Okay. And summary, I'm too fast. Okay, no problem. Yeah, we are working on the measurement of hydrogen by using the speed of sound, because the speed of sound of hydrogen is 4 times higher than in air. We are working since 2 decades on thermal conductivity sensors. It works very well because the thermal conductivity of hydrogen is 7 times higher than all other gases except helium. We work with Herr Wartmann on measurement systems, remote measurement systems for ammonia, because there's nothing on the market, nothing. I don't show you, we're working on color dye-based hydrogen sensors too. It's a change of color of an indicator. And another possibility to measure hydrogen is an electrochemical cell. It's nearly a very, very small fuel cell, but this works only in air, in ambient conditions, because you need oxygen. Okay, thank you very much for, and go.
Thank you very much, Jürgen and Frank, for the insightful presentations in respect to the safety of components with hydrogen. And we open the floor now for any of your questions that you might have. We have a question from the audience. Hauke, please.
So one question that was asked online was, to Dr. Schweitzer, what is your view on hydrogen barrier coatings for steel?
So we are looking at the barrier coatings in other projects. These are mainly zinc nickel or zinc or even chromium systems. Yeah, you can you can have coatings, but the problems with coatings is also if you have hydrogen absorbed to the bulk material, that this acts like a barrier for the fusion of hydrogen. So if you have, so my personal view is if you have barrier coatings or if you have coatings on your steel samples, you have to adjust the heat treatment, or you at least have to do a heat treatment, which is not done on all components for the hydrogen infrastructure right now. So if you, for example, see real welded pipelines, these are normally on auf der Baustelle, was sagt man in Germany, on site, these are not heat treated. So if you have coatings, you need to do heat treatment processes also. But these can be, in some cases, can be beneficial.
Thank you very much, Frank. Are there any other questions from the audience? Yes, we've got one here, please.
Thank you, Herr Schweitzer, for your nice presentation. I would like to hear your opinion on the learnings from your studies on refurbished or redesigned gas pipelines. Consider a usual pipeline, gas pipeline using hydrogen. What does this embrittlement, this crack propagation, and this fatigue properties mean for that? Is there an increased risk of having a leakage and then a safety issue, or is this just to consider for to be considered for the lifetime? What's your impression?
So in this project, in this TransHyDE project, we look at new pipelines, especially in this X52. We had other projects where we looked at existing materials. Also, we had a look how the pipelines in Eastern Germany, Russian pipelines, for example, which had in the so-called Stadtgas at this time. There was a lot of hydrogen inside of it. How this, the microstructure and how this, how these steels developed over the years. So this is not a focus on this project, but we think about it, and you have to consider this. You have to know what your pipeline had as a mechanical, what mechanical stresses were on this pipeline. Also, if it's inside of the in the
earth.
If it was used, it can have different movements in the soil. So you have to at least look at the steels which you used in the laboratories, and test them in your systems, like I showed. So it would be good to have older systems, older steels, and test them in the laboratory as well.
So no final answer up to now?
No, I would right now. I would cannot give you any hint about the safety issues here.
Thank you very much. Regarding the time, I would take two more questions. I see one here.
This question is for Mr. Wöllenstein. You said the CO2 content by measuring the speed of sound is influencing. Yeah. Maybe can you quantify that a little bit more?
It has a big influence. Yeah. Outside it's no problem because we have 400 ppm. But inside, here in this room now is maybe 2000 ppm, and then maybe we cannot measure 20 ppm hydrogen. We only have a resolution of 1000 ppm because CO2 has a big influence on the speed of sound.
Thank you very much. We have one last question then here from the audience. The mic is coming.
Müller-Kirchenbauer, TU Berlin. I have a quick follow-up question to Frank on the hydrogen embrittlement. So you mentioned Stadtgas, that many of the pipelines have seen already in their past life, and therefore high hydrogen concentrations. But what about the newly constructed pipelines? So after the turnover from Stadtgas to methane-based natural gas, is that true for these pipelines as well? And what is the role of pressure swing in the operation of the pipelines? If we can consider a relatively stable pressure level, what does it change then?
Yeah, so we are talking about this right now in different aspects, also with the DVGW. So we'll have a talk from Mr. Sistermans in the afternoon, I think, about standardization. And there's we talk about it was also considered that you use the pipeline systems as a storage system in the winter. So you that you pump it up to a higher level and use the hydrogen in the if you need more hydrogen, and that would lead to a far more stress of the materials. Also, as I showed, these low cycle fatigue regimes, and this, I think, this issue is a problem. This cannot be done directly, but in the normal case, the first part of your question, in the normal case, we are really looking on a new steel material, this X52 we have here, or different pipeline steels around this, or X60. This is around the world. There's a lot of testing about this, but I think you have to have a closer look on the welds also, not only on the sound materials, but this is also from the manufacturer. I know they do a lot to quantify the materials for hydrogen, also for additions of different other gases. So it's not only a single scientific topic. It's also right now it's already an issue of the companies which produce these pipelines and also the valves. Does that answer your question a bit?
The most part of it.
Yeah, okay. But then we can also go deeper in the pause.
So thank you very much, Professor Wölnstein and Dr. Schweitzer, and give them a big applause for their presentations. So both are here today, so if you have further questions to the speakers, just use the time to network and to post them then in afterwards. So we're a bit over time, but we will go into the coffee break right now, and we will resume with the conference sharp at 11. So please come back to the audience room then in time. Thank you very much. And please take your seats. Now we will continue with and the next speaker is Dr. Achim Zatsch. He's member of the TransHyDE project, Get H2 TransHyDE. And the project itself focuses on the transformation of a gas pipeline system into a hydrogen pipeline system. And of course, very different necessities are to be considered in order to provide a functioning transformation. And Dr. Achim Zatsch, he is he is an analytical chemical engineer, and he studied he studied chemistry, and he holds a specialization in analytical chemistry. And after several industry positions, also focusing in the analytical area, he became partner of a new company called MetaQ Solutions, and is very much focused in the gas quality measurement sector. And his key activities include the development of a process gas chromatograph transmitter for the reduction of carbon dioxide emissions, and also analytical determination of hydrogen and its impurities in the gaseous phase. And today he will give us a presentation on hydrogen, a challenge for determining the gas quality. So please welcome together with me Dr. Achim Zatsch.
So welcome after the nice coffee break. I know it's always a problem to start again after having coffee and cookies. And second, I want to thank you for the very kind introduction, and even saying thank you that I have an opportunity today here and to talk in this conference. It's a very a challenge a little bit, and it's also like an opportunity for us to explain a little bit analytical techniques, which is sometimes always a little bit underestimated, but it's important as we want to see today. So again, that is the reason why I put it the title, a challenge of determining. So hydrogen, as you know, is one component, and it's an element and elemental component. And it sounds simple, but hydrogen has his specialties. So now we want to start a little bit an introduction, why we are doing these. Then we will look a little bit more into technical details. What are the requirements to measure the hydrogen itself? For that is the point. From the four speakers, we have heard that it is in safety, the situation is difficult and has challenges to measure the hydrogen itself, but also the impurities. So there we want to present a solution on that. And we started, as was done in the introduction already, that with a so-called nano-process gas chromatograph. So it's a new development of an online process gas chromatograph. So, and then the first step we did in that project was to set up test facilities, especially for hydrogen. And so then we looked in the laboratory on different applications like reusing used natural gas pipelines and to repurpose them for hydrogen use, or to analyze the hydrogen impurities. And this next and the last step in our project is the field installation in Lingen. And then in the end, I will sum up a little bit our results. So now coming, why it is a challenge to measure the hydrogen. We have heard before the coffee break, it's a safety issue. And the next is hydrogen is not climate neutral. So in all our installations, we have to consider to reduce emissions of hydrogen wherever we can. So hydrogen itself is not climate active, but what it does when it gets into the atmosphere, it is working like a catcher for radicals, which normally reduce the methane in the atmosphere, and for that it has like an indirect influence. But anyhow, it's a good reason then to look at new design, and we're starting now in a new process, designing that we want to look how to reduce emissions from the very first start. Now we have but we have problems in the natural gas networks, in which in the existing one to reduce now emissions wherever we can. But when we're starting anew, we should already consider that in our design. Then the next step, why it makes a challenge, is there is no technical guidance, no technical rules. There are only limited rules to it. I only have mentioned two, which to my knowledge are somehow suitable. One is called TRG19, but it's not so good adjustable for if we go for 100% hydrogen grid, because the TRG19, as it's called, coming from the PTB, from the Physical Technical Bundesanstalt, is regulating the 100% hydrogen injection into a natural gas grid. So it has nothing to do if you deal in a 100% natural gas transportation grid of hydrogen. This is the only rule, is the G260, which has designed now a new gas family. It calls hydrogen, and this is defining what kind of gas hydrogen quality is allowed to handle in our natural gas grid, not in the natural gas grid, in the grid itself, if it is hydrogen or nitrogen, whatever. So now we see we have to differentiate, or we have to rethink from the past, because now we have to distinguish, because of the G260, it says Group A and Group D hydrogen class. Group A is only 98% hydrogen, so that in other words, it is allowed to inject 98% pure hydrogen in a hydrogen network. So 2% can be something else, and that influences clearly the calorific value. And second, it says it can have, it's Group D is like a quality, which is like for the fuel cell quality, and this is like a limit value determination. And there we go from the normal measurements into ultra trace measurements. So as we heard, we're going into ppms, we're going ppb levels, and this makes the sampling handling system before whatever measurement it is much more difficult, because we have to get the component from the pipeline to the analyzer. I was a little kidding saying the pure analyzer can only measure what it gets. If it does get mistakes, it displays mistakes. Yeah? So the biggest mistakes we can make are in the sampling handling system. So for that, later on we will see we have to rethink our actually designs. So this is a picture which is explaining a little bit the G260. On the left-hand side, you see the different sources of hydrogen. So coming from the natural gas grid to hydrogen grid, now we have to learn that the hydrogen have different sources, different processes which will be created. Then we have the entry into the natural gas grid. That it is controlled by the G260, as I said, Group A, Group D quality. And in the end, we're having customers, end users, could be big companies, could whatever it is. So, but in between, it's regulated by the G260. So now coming a little bit more in the details, what does G260 Group A and Group D mean? You see the different components and the qualities of hydrogen. Group A says 98%, and Group D says 99.97%. And we go in low ppm ranges of components, which has to be tracked and has to be measured in the hydrogen if we are exceeding these values, or we should be below the values. You know? That is the requirement, to stay below these limits. So now then we started, and the first we did, we set up a system in our small company, and to test these components. And you see in the right-hand side in the picture, the orange box is our so-called gas chromatograph. And what does a gas chromatograph does? It takes a sample, it separates it into its component, and in the end of the detection of the column, on the exit of the column, there is a detector. As the fourth speaker says, it's a thermal conductivity detector. And the thermal conductivity detector, as he says, it's totally right. It's used for decades. It has a lot of advantages. It is very robust. You can use it easily in process. It doesn't need any support gases. It has a very high linear range. Good or bad, in our case it's good, it's unspecific, so we can measure organic components like nitrogen, oxygen, hydrogen itself, and we can measure organic components. So this is really the reason why it's very, very well used in chromatography. And you see the new thing is here in the black cartridge, all the columns, all the detectors, everything is included, so it's very easy to maintain. You just open the GC, you have that box, you take it out if you have a service problem and just put it in back. So it's completely new design. So this is details for chemists, what kind of components are in there, so you find it probably later in the documents. We don't have to go now through that. And then we start, when we now repurposing natural gas pipelines, what need to be measured online 24 hours for the next 15 years? And then we set up this component. Of course, we have to measure hydrogen, because what we're starting with natural gas, and we're putting hydrogen into it. Now we're discussing 20%, but in the near future, maybe then it will be completely rechanged, some pipelines. And then we're ending up in 100% hydrogen, and all the other components which are listed, they're going down. But we need a system which is all this capable to measure, and for this is the ideal application for a gas chromatograph. And the biggest doubt everybody has is to measure from 0 to 100% the hydrogen, because hydrogen you can see that in the curve a little bit in the beginning, so it's not a 100% linear curve. So all other components like methane, ethane, they are mostly linear responses in the TCD, but hydrogen is not. You need a multi-level calibration. And you see, we went up to different steps up to 100%, and you get not the highest accuracy. It's an accuracy of plus minus 1%. But you can observe the process if you repurpose a natural gas pipeline, pumping hydrogen into it, and you can control this process, and you can monitor the process with SGC, and you can see when it is finished. Now you know I have 100% hydrogen, and you will see the impurities. So nobody knows in the moment when we completely substitute hydrogen or natural gas by hydrogen. So what is the rest? There could be still some ppm, methane, ethane, or whatever, but it could be monitored. And for that we designed a solution, because this is like a temporary process. And then we designed a temporary solution. This is like a roller case with a GC inside. You can go on site, and if the company changing the repurposing of the natural gas into hydrogen, you just install this suitcase or roller case. Maybe for 6-7 months, nobody knows in the moment how long that process takes. But you don't have to install a fixed installation forever there. Then you can just take this temporary installation, monitor the process, and you see when it's finished. So that was the first task we did. Then we started furthermore thinking on the hydrogen quality measurement. And we simply we looked to the different processes where we think hydrogen could be produced from. And the first, of course, is electrolysis. So we bought just a gas for hydrogen. The hydrogen was a balance. And nitrogen, oxygen could be impurities, possible impurities from electrolysis. Electrolyzer companies always saying, hey, we deliver 5.0 quality of hydrogen. That's true. but only if the treatment is working. That is not by definition, there's oxygen, nitrogen always there. Yeah? So it's never that you have an electrolysis that comes out at directly 5.0 quality. So you have, anyhow, you have to control the treatment if the hydrogen is clear or if clean, or if hydrogen is 5.0 quality. And you can see it's, from a chromatography point of view, a very simple chromatogram. The big negative peak is the hydrogen peak, and then we have smaller nitrogen and oxygen peaks, so very simple to measure, and we can measure it easy. And then what the big question was hydrogen, because everybody knows we can measure 1, 2, 3%, or we can measure low ppm levels of hydrogen easily. But what is with close to 100% hydrogen? Can that be done? And here you can see it's a 99.989 something set point of the calibration gas. And you can see that we can measure that with a deviation of 3 ppm. And you can see also the window of the fluctuation, the repeatability of the reading is fantastic. So it is also relatively easy to measure the high level concentration of hydrogen and in addition the impurities. So this is more for the paperwork. We're having statistics so that we haven't done only 1 or 2 measurements. Yeah? So we did have done nearly 2,000–3,000 measurements with these. So it's a lot of statistics data available. Then we went to the next process, from electrolysis to the reformer process, and we thought what components could be interesting. And this is, again, hydrogen clear, but it is a CO2 and especially methane and CO to that. And no wonder we could also relatively good results, and we could measure them. Yeah, from that, electrolysis, repurposing, reforming, then we said, what could be a possible solution for like a custody transfer measurement of hydrogen in comparison as we have known it for natural gas? We thought, hey, then from this evaluation, we said this could be the components which could be interesting for a custody transfer measurement of hydrogen. So we said 97 to 100%. Then we're covering the 98% of the group A, we're covering the 99.97 of group D, and we have shown we can measure, and we can distinguish between 99.97 and 99 or 99.8. So that we thought this is good. And then we put the other components like CO, nitrogen, oxygen, because nitrogen, oxygen from the electrolysis process, CO, methane from the reforming process, and we thought maybe from the repurposing process, there could be higher hydrocarbons, maybe up to C4. It could be C5 or C6. I'm not saying this is a dogma. This is our first starting point. We say this could be a starting point, and let's have a look if that fits, and if maybe a component is missing, we have to add it. If it's a component too much, we just take it away. And the same is with the ranges. We said, hey, if we go along smaller than 0.1% or 1,000 ppm, this is just a starting point. And the reality, maybe in Lingen, and this is a good start in Lingen, to find out if we can justify this, or we have to adjust this. So then we thought, no, this is now actually the whole work of 2 years being in TransHyDE, not roughly 2 years, but we found safe enough now to go to PTB and go with this system to approve it for custody transfer measurement. For PTB is a challenge because it's new. As I said, there is no guideline. The biggest hiccup is that the so-called MES-EG, means the German Weight and Measures Institute, is not valid in the moment for hydrogen, because paragraph 5 saying all gases which are transported as a burner gas, or burnable gases are transported and have a lower calorific value than 6.5 kilowatts are excluded. And hydrogen has 3 point something. So there is no law which the PTB can approve it against. So this is a little bit the challenge, but PTB now says, okay, we're taking the advantage and or the challenge, and they said, yeah, we will do the test, but you do not get a certificate against MES-EG because hydrogen is not included, but we get like a proven certificate from PTB quality. So this starts now in January. And what I have never mentioned is, so we all components we measure is in 45 seconds. So we are, to compare to traditional gas chromatography, much faster. So then we come the last 7 minutes to the module D limits evaluation. And again, this, as I said on the beginning, if you go for group D quality measurement, it's a complete change of world in the net from which we know from natural gas. So the sampling handling system has to be properly designed. It has has to be passivated. It has to be heated because we want to transfer 4 ppb total sulfur. Yeah, so this is anyhow a challenge. I'm a little bit doubting in a moment that we really can do that. But some of the things we can do. But we have to be very, very careful on designing of the right sampling handling system. So then we really started simply in our laboratory with our test, and we bought some gases which should be challenging, yeah? And we tried and looked where we are. And you see for CO2, the limit value of, according G260, is 2 ppm, and this is the red mark. And you can see we had a 1 ppm calibration gas, and we really could easily measure and observe the 2 ppm. So with the same ranges, with the gas chromatograph, which we have designed now for PTB, for cascade transfer, we also can observe this value. So there's no technical change. On all the measurements, this statement is true for all other slides I'm now showing. You see, methane, the limit is there, 100 ppm. This is not a challenge at all. So then oxygen is a little bit more challenging because there we have different limit of valuation, but the toughest value is for hydrogen, and that works a bit above 16 bar, so for 16 to 100 bar. And there it says the limit is 5 ppm, and we got 3 ppm. This is oxygen, and I think there's a wrong picture in it. And then we have to get the 3 ppm oxygen concentration, and we can easily measure below the 5 ppm. For nitrogen, you see the limit value is 300 ppm, and we had here a calibration gas with 10 ppm, so it's no problem to measure them at all. It's just show that I can show you whatever kind of graphics, but this is a real measurement. You can see this is hydrogen, nitrogen, not in hydrogen, because then we had a very big peak in the front, but this is in methane, so the back peaks you see is methane, but you can see easily that 2.8 ppm is the first peak. And I was expecting the limit of detection is around half a ppm, so 500 ppb. And this with a simple TCD, so that the performance now, meanwhile, because of the long decades of experience, is fantastic. This is again the first list I said, which with the components, and you can see we could make a lot of green tick marks to it. What is impossible is we cannot measure this 0.2 ppm CO. This could be done with something else, but not with our GC. And the 2 ppm non-methane hydrocarbons. Yes, this is also a limit value which is probably not possible with our system. This is only sum up in words what I already said. Now the next is in February. Hopefully the test rig is ready by end of February. So then we can set up the field test. And the important is, you see, this is a traditional installation. And you see we take the sample out, have a pressure reducing station because we have 50 bars, 80 bars. Then we transport the sample to the GC or whatever measurement. And this takes time. This we call dead volume. Yeah? And for that, we need always a bypass system. The bypass has only one simple purpose, to purge the line and to make sure that we make the measurement representative. But the bypass is purged to the exhaust. And this is emission, and we don't want to have this emission anymore. It was in the past, in the moment it's natural gas, or we're using hydrogen, it's hydrogen. Could be a safety issue. You have a lot of 100% hydrogen. You create atmospheric air, explosive air possibly, and we have emissions we don't want. So we have to rethink, and we just want to see what is the effect of the bypass. If you just, I have here an example, and we set the bypass to 40 liters per hour. You see, we have a time decay of 12 minutes. You see, then the results we get, the sample is only 12 minutes ago. So it doesn't say this is the concentration or the quality of my hydrogen in the pipeline right now. It is the concentration 12 minutes ago. So if you put it to 20 liters, you put it to 23 minutes. If you just put it to 0, it's more or less 6 hours. So you have this is the big challenge we have to overcome. And our idea was to design a system, because the GC is too small. It's big like a shoebox, 15 kilogram. We designed a system to install the GC directly on the pipeline. The bigger challenge of the big advantage is, if it takes the same example, then the bypass is 0 because we have directly on the pipeline, and we have a dead time and for 3 minutes only. So we're really measuring representative. And we're reducing the emissions for natural gas or for hydrogen by 95%. And this is now done. So hopefully February start as the field test in Lingen. And this is the concentrations which we are at PTB level. So the first 2 years in the project went very well. We are completely on plan, but mostly it's not the case. And in the next 2 years, we do the field test, and hopefully get the PTB test done. So thank you for your patience and for listening, and now hoping for a lot of discussion now.
Thank you very, very much, Dr. Zach, for this very insightful presentation, and also a new technology that you have developed with your company. So let us hear your questions about it. I've got one up there, Hauke.
Yeah, thank you very much. What kind of impact pressure dependency on accuracy and repeatability does the gas chromatograph have?
The GC itself can only handle 300 millibars, but we reduce the pressure, but in the whole design system is that we can reduce 100 bar down to 300 millibar.
Thank you.
So any pipeline pressure, which is normal, I wouldn't say higher, but in a natural gas pipeline, 100 bar is the design pressure overall, so all this application we can handle.
There was one more question in the middle here, please.
Yes.
Can we have the mic on?
Yes. Does it work now? Okay.
Yeah, thank you.
One question related to type examination. You're referring only to the 5th gas family of G260. What about the 2nd gas family, which now includes mixtures of hydrogen into natural gas up to 20%?
To be honest, this is a tick mark. This is not something we develop anymore. This quality could be, you don't find it in the natural gas grid in the moment. Yeah? If you measure anywhere, you find nowhere hydrogen, yeah? Because the concentrations are much too slow. But from the metering point of view and technology point of view, this is done. Yeah? So every GC which is on the market and has so-called PTB approval, they can handle 20%, and this, from a metering point of view, this is finished.
Thank you.
Thank you. Are there any other questions from the audience? Hauke, please go ahead.
So, a second question from the virtual space. Do you calibrate the gas chromatograph for every analyzed impurity? And if so, how many calibration points do you use per analyte?
That's a good question. This is in the moment we're using 5 calibration points. Yeah? But this is clearly still under an investigation, and this is also probably what comes out from the PTB test, yeah? Because PTB is doing their own test, and in a natural gas world, I would put it like that, is that PTB says how many calibration points are needed for this instrument. And I'm expecting they're doing the same for hydrogen. Yeah. In a natural gas world, in a moment, it is like that you have, the PTB says you have to use 5 calibration gas points.
Thank you very much. I think I can take one more last question if necessary. Yes, please.
Thank you for the nice presentation. I have a question to the calibration. How long is the calibration stable?
You mean the gas or the calibration itself?
I mean the calibration, so you have a really nice and impressive limit of detection and accuracy.
Yes.
So, and how often do you have to calibrate?
Yeah, calibration is a difficult one. Yeah, one is because of the calibration gases. I put it a little bit under the table. Is that in the moment there is no calibration gas available certified back to national standards, like it is done by BAM or by PTB. Yeah, so BAM is in Berlin, so maybe they're hearing it and they're working on it. And the second is. That is the biggest challenge in the moment. We found, luckily, the VSL in the Netherlands, they only have been able to certify us 2 bottles with 50 and 100 ppm. And that is, if you put that, then is gold nothing against it. If they look into the price, and thank you to TransHyDE project, otherwise we couldn't afford that, to buy these gases, because 1 bottle of gas is 20,000 euros. Yeah? And I think these are the only 2 bottles now going back to the national standards. And to get these gases took us 11 months. So we got them in last week. So it is the last measurements we do in the moment, and then we can go to PTB. And PTB says they need these gases, otherwise they cannot do the measurement. That is always the chicken and egg problem. So we solved that. And the other one is that PTB always in custody transfer situations, going back to natural gas, PTB says whatever it is, whatever the manufacturer states, you have to recalibrate or do a recalibration run every 24 hours. And I'm guessing that if on hydrogen that would be the same. So you have to done an automatic calibration with an installed calibration gas on site every 24, normally at 6 o'clock. So this is all regulated.
Thank you very, very much. We will close the session with Dr. Zatsch. Please give him a big applause for this insightful presentation. Thank you. And we will actually change the energy vector now, and we will look at the hydrogen carrier ammonia. And I have the pleasure to introduce to you the next speaker, who is Dr. Michael Poschmann. And he graduated in chemistry and obtained his PhD at Kiel University, where he focused his thesis already on catalysis at the Institute of Inorganic Chemistry. He worked there as a research associate and postdoc, and recently he is working as a research associate and postdoc at the Max Planck Institute for Chemical Energy Conversion. And he is also co-coordinator for the TransHyDE project, which is called AMOREF, and is focusing on the reformation process of ammonia back to hydrogen. So please let us welcome Dr. Michael Poschmann for his presentation of Introduction to Ammonia Decomposition and its Challenges.
Yeah, thank you very much for this nice introduction. I would like to introduce you today to the ammonia decomposition and its challenges. So at the beginning, there's always the question, why should we do that? So why should we do ammonia decomposition? So we heard the starting point already today a lot, that we want to transfer our energy system from fossil fuels to renewable sources, and a lot of it is done by these electrical energy, but there's a lot of stuff like, for example, steel production or shipping or fertilizer production that is not electrifiable. But the problem with hydrogen is that it has a quite low energy density. So when you use very high pressures, like up to 700 bars, or if you use very low temperatures below 30 degrees, 30 Kelvin, you reach energy densities up to 2.3 or 2.5 kilowatt hours per liter. And when you compare this with the fossil fuels, like gasoline, diesel, or natural gas, you see that these have 1 to 8 times higher energy densities. And therefore, you have to use a lot more storing capacities to transfer from these resources to hydrogen. And additionally, because you need such very high pressures or very low temperatures to store hydrogen, you need a lot more infrastructure volume just for storing this hydrogen in such huge amounts. But besides these physical storing techniques of hydrogen, there are chemical storing techniques discussed a lot, and one of these is ammonia. Ammonia has a lot of advantages, I would say. You see here on this graph that ammonia has 18 weight% of a gravimetric hydrogen density, which is a lot compared to other chemical storing techniques of hydrogen. And ammonia has as well, or even especially a higher volumetric hydrogen density than hydrogen itself. And compared to other chemical storing techniques, it has a very high volumetric hydrogen density, and therefore it's a very good option to store hydrogen in ammonia. To put that into different values, you see here the German natural gas reserve of about 200 terawatt hours. When you want to store the same energy amount into hydrogen, you have to triple the amount of gas storage volume, which is not that nice, I would say. So in a gaseous state, I have to say here. When you store the same amount of energy into ammonia, you only need 75% compared to hydrogen if the ammonia is designed for directly combustion to regain the energy. That is not a big benefit yet, I have to say. But when we reform the ammonia back to hydrogen, then we only need 50% of the hydrogen, of the storing volume to store the same energy in ammonia. So that is already quite good and comes quite close to the natural gas reserve we have now in volume. But the real benefit of ammonia is that it's very easily liquefiable. So you can use pressures of something like 8 bars or only minus 30 degrees Celsius to liquefy ammonia, and therefore it's very easily to densify compared to natural gas and hydrogen. And then you only need 0.05 volume % compared to gaseous hydrogen, which is a real benefit, and therefore it's a very good option to store hydrogen in ammonia. For using ammonia as hydrogen storage, you have to do synthesis of ammonia, but that is done a lot worldwide. Therefore, it's not a new process, and this process you see here, the most part of it, or the biggest part of it, is just the hydrogen production, which will be soon electrified, and then it's as well synthesis that is done with renewable sources. Afterwards, so when you have produced a lot of ammonia, you need a supply chain. Here's the benefit that there is already, as I said, a huge global ammonia production of about 180 megatons per year. And there's as well a global maritime trade, for example, or a global trade of ammonia, and therefore the know-how how to transport, how to store, and all this what is connected is known, and so the know-how is there to really trade, transport, and store such huge amounts of ammonia. But what is missing is really the ammonia decomposition process. So it's not an industrial process yet, and therefore there needs to be some development. But there are already profitability analysis of this process, which are done at reforming temperatures of 650 degrees, 800 degrees, or even higher temperatures. And based on these calculations, the cost analysis predict a price of the hydrogen of about $6 or $6.3 per kilogram hydrogen. When you compare this to the hydrogen price in 2018, you see it's at the upper limit of this hydrogen price, so it's already quite competitive, I would say. The most of these costs are estimated because of the plant operation for ammonia decomposition. And when you see now that this plant operation is done at very high temperatures, that will have a huge impact on the costs. But actually, the reforming temperatures which are possible to use are below or around 500 degrees, and therefore the costs for ammonia decomposition derived hydrogen will strongly decrease when we have such a process on industrial scale. The thermodynamic limits of the ammonia decomposition you see here in the curve. So on the left side, it's best to be seen. Ammonia decomposition is a pressure-dependent endothermic process. And when you see here the violet curve at atmospheric pressure, you can reach almost full conversion at about 400 degrees already. So it's possible to do ammonia decomposition at low temperatures and therefore at low costs in principle. But additionally to the thermodynamic limits, there are kinetic limits which hinder the reaction, and therefore we need catalysts. There are already a lot of catalysts researched for ammonia decomposition, and the most prominent one is are ruthenium catalysts, which are already very active. You see it here in the left graph in turquoise, that it is or shows activity at between 400 to 500 degrees Celsius already, though it's a very, very nice catalyst, but ruthenium is quite expensive and has a low abundancy. But there are as well options to use nickel or cobalt-based catalysts, which show as well activity at about 500 degrees, for example, to convert ammonia back to hydrogen. Additionally, there are as well iron-based catalysts or other metallic-based catalysts that do the reaction as well at these temperatures, but with, at least in the literature, at lower efficiency. But all of these, or most of these catalysts published in literature are, or 75% of it are of a monometallic systems. But from other catalytic systems, we know that multimetallic or multi-component catalysts, so these orange or gray and yellow parts of this circular diagram, are possibly more active. So when you want to optimize your catalyst, you add more metals, more components, get a complex system, but then it's possibly the most or more active and more optimized catalyst. And therefore, there's a huge potential to even improve the current status of the catalysts. But the problems of these reports we analyzed is that these catalytic systems are measured at different gas flags, different catalyst amounts, different reactor sizes, and different runtimes, and therefore we need definitely standardized reaction conditions to really compare all of these very different data sets. And later, we are using these standardized reaction conditions in the AMOREF project, and later this will allow us additionally to do machine learning or apply machine learning to really speed up the catalyst development and get very quickly an optimized catalyst. So what are we actually doing in the AMOREF project? We are organized here in this scheme. We are doing high pressure ammonia decomposition or research on high pressure ammonia decomposition. We are doing research on the other big field at lower pressures. Low pressure means atmospheric pressure. And this both big parts are interconnected by nitride research, which is as well important for the understanding of ammonia decomposition. And finally, at the end of our project, the aim is to develop or build up 2 pilot plants, one for high pressure and one for low pressure ammonia decomposition. High pressure and low pressure ammonia decomposition, because as I have shown already, the ammonia decomposition is a pressure-dependent reaction, and therefore we want to investigate it at low pressure and high pressure. Both possibilities have their benefit. Low pressure ammonia decomposition is quite easy, and you reach at low temperatures already high conversions, and therefore already quite pure or clean gas. But yeah, you will definitely still have to do little gas cleaning. But the benefit of high pressure ammonia decomposition is that you obtain a hydrogen gas that is already pressurized. Okay, you need to do more gas cleaning because you have low gas purities, but you have a pressurized gas, and therefore it's easy to use for downstream processes in industry. Our starting point are commercial catalysts as a reference. We are starting with known catalysts, like, for example, the iron catalyst, which is built up by iron, metallic iron particles, which are separated by oxide particles, a so-called unsupported catalyst or Voll katalysator. And we're using as well as reference catalyst ruthenium and nickel-based catalysts, which are made up by small particles, metallic particles, that are supported on alumina or carbon supports, so-called supported catalysts. And their convergence curves you see here on the left side. And you see that the ruthenium-based catalyst shows already almost full conversion at 500 degrees. So it's already a very good catalyst, and it's possible to convert ammonia at these temperatures, which is really nice. As well, the nickel-based catalyst is already quite active at 500, or you reach full conversion at about 550 degrees Celsius, which is, yeah, as well, really nice. Only the iron catalyst is, in comparison, reaches only full conversion at about 600 degrees. Therefore, it's the least active catalyst in this comparison. Yeah, but beside of these just activities or just high conversion rates, you have to as well have a look on the long-term stability of catalysts. You see it here as a graph where 1 means that the catalyst is at least for short-term stable under these conditions, and you see the ruthenium and the nickel-based catalysts are active, are on a short-term stable under these conditions. Again, only the iron catalyst seems to be not that stable, and now these catalysts have to be tested for long-term stability, so about some 100 hours or even some 1,000 hours to really say that their long-term stability is given of these catalysts. But I have to mention again that these catalysts are not optimized yet. So there is a lot of potential to by adding promoters, for example, different additional metals or different elements to tune the catalyst ability towards ammonia decomposition. And therefore, there's a lot of space for optimization of these catalysts and reaching even lower temperatures for ammonia conversion and higher long-term stability. That is our goal. And therefore, we need a lot of catalyst synthesis. And we have different working groups doing this synthesis, like, for example, the Malte Behrens group in Kiel or the Annette Trunschke group here in Berlin, who are doing catalyst synthesis by co-precipitation. You see here the big reactor system, no, it's not a hydrothermal, but a precipitation reactor. And then by filtration and calcination, you get the oxide materials, which are the pre-catalyst, which needs to be reduced before ammonia decomposition. Similar material you can obtain by flame spray pyrolysis, which is done as well in the Annette Trunschke group. You get very fine particulate materials with it, and again, as oxides and as pre-catalysts. In the Saskia Heumann group in Mülheim, and in the Monika Bosic group in Freiburg, we're doing or synthesizing carbon-based catalysts by different synthesis methods, and these will as well be investigated for this reaction. And the more special ones, the nitrides and oxynitrides, are again synthesized here in Berlin in the Martin Lerch group. Again, different types of catalysts, and we hope to find very quickly very active catalysts. And then after the synthesis, we need to do catalytic testing. At low pressure, we have this Hahn protocol we are following. So you see on the left side our screening, or the temperature profile of our screening tests. So after pretreatment, you have different isothermal steps to really quickly judge on the activity and stability of the catalyst, and only if the catalysts are promising, we continue with long-term stability testing and kinetic testing. These screening tests are, for example, done in this such kind of instrument on the left side, and this is done at the Holger Ruland group in Mülheim, or at Clariant, or in the Trunschke group or Behrens group. So we have a lot of measuring capacities to really measure a lot of catalysts to find very quickly, promising catalysts. And after that, these catalysts will be investigated or are investigated by the Martin Müller group in Bochum using these instruments here. So they are our expert for long-term stability and kinetic testing. Beside that, I mentioned the high-pressure ammonia decomposition, which is done. That is mostly done, or only done, by the BASCAT here in Berlin or the BASF group. And additionally to that, they develop as well integrated processes of, for example, heat-integrated processes. And they are as well developing resistive and inductive heating. So they are developing concepts to electrify these catalytic processes, which is really helpful and nice. And they are developing as well heat-integrated reactor concepts and pressure swing absorption or gas cleaning for, as it says, gas cleaning afterwards, after the ammonia decomposition. So very important stuff. The first high-pressure ammonia reforming setup for testing is already built up, and it can decompose ammonia at up to 30 bars. You see it here on the left side. But beside that, we need a lot of characterization or very advanced characterization techniques to really know what is happening during the catalysis. And therefore, we have different groups that do electron microscopy or in situ and in silico testing. That is, for example, the Thomas Lunkenbein group here in Berlin, who can do electron microscopy on atomic scale, and as well in situ, they can do in situ investigations of the catalyst during operation, and can help to understand what is happening during catalysis, and therefore can judge on maybe some mechanistics of deactivation. Similar characterization, but very different technique, is done by the Serena de Beer group. They're doing in situ and in operando investigations with different X-ray spectroscopy techniques. And then we are supported by the Parinello group in Italy, who are doing molecular dynamic approaches to model or use computational models to investigate the mechanistics of these reaction systems. And I want to mention now at the end our next milestone, which is reached in these weeks, is that the first catalysts will be delivered to the Campfire project to be tested within their instruments. And with this, I want to thank you all, and maybe you have some questions I'd like to answer.
Thank you very, very much, Michael, for this insightful presentation on the decomposition of ammonia. And we are open for questions from the audience now. Ms. Al.
Thank you very much for this nice presentation of the decomposition process. As I'm not a chemist, this was very exciting to me. But when considering these efforts for decomposition, so either the high temperature or the high pressure, this is associated with some, let's say, energy effort too. And if you consider that and put that into the energy content of ammonia, what happens? Which amount of, let's say, kilowatt-hour load on the energy content of the ammonia itself will that represent?
I know that in these studies I mentioned, they calculate something like 40% of the energy that is needed for all the processing. But that will definitely depend on, for example, what temperature is used in the reactors and stuff. And therefore, I won't say, I guess therefore the pilot plants will be set up to really say what is really the amount of energy needed for doing this storing technique. And I would say then we really can say what percentage of energy is needed.
Because I think when we want to be clear and fair, we have to consider all these associated energy costs. And at least this energy for releasing the hydrogen has to be provided in Germany, as the importing country.
Sure. Klar.
Thank you.
Thank you. Any other question? I see one up there.
Thank you, Dr. Poschmann. I mean, this is crucial contribution, your work, what you are doing for the hydrogen economy. I mean, congratulations. I'm so amazed. I have one question. You presented for the catalyst the whole platinum group metals, and I'm coming back now to iridium and platinum. For the electrolyzers, for 1 kilowatt of the installed capacity, we need something like less than 1 gram, 0.67 of the iridium. How much is this, or can you please tell us, can you survive or produce catalysts without iridium and platinum, because you would like to reserve these platinum group metals for the production of the electrolyzers? And if not, how much is it like, how much would you need for Germany? I mean, if you scale up your technology, ammonia decomposition for the needs of the hydrogen economy in Germany?
Yeah, that will need a lot of metal definitely to have so much capacity for ammonia decomposition reactions, and therefore I would say the ruthenium or precious metals are definitely not the aim to be used. Therefore, we showed as well this nickel-based catalyst, which is maybe a better option when looking towards abundancy and price, definitely. But we have to see that these cost analysis must be possible, or it is possible, but it has to result in a cheap hydrogen, definitely. And therefore, we still have a look at it as an option, but for me personally, I would say nickel-based catalysts will be the better, or the cheaper option, I would say, or the for all better option.
Thank you. Thank you very, very much. And looking at time frame, I would say keep your questions and address the team of Dr. Poschmann and the cooperation partners of AMOREF for the lunch break. And we thank you very, very much for this insightful presentation. And it is my pleasure to continue on the path of the energy vector of ammonia. And it can be used in propulsion, it can be used also as transportation and also for logistical and bunkering methods. And I have the pleasure to introduce to you two speakers from the Campfire project of TransHyDE, which has already been mentioned. And one of them is Professor Dr. Hinrich Mohr, and he holds a doctorate in mechanical engineering of Braunschweig Technical University. And he has many years of experience in R&D and also key account management in industry. And in 2020, he decided to set up his own consultancy, Gaskraft Engineering. And Professor Hinrich Mohr, he also holds a chair at as a large bore and gas energy technology honorary professor. So welcome, Professor Mohr. Thank you very much for your presentation.
Thank you very much for your kind introduction. And I'm very pleased to give you an insight today to our activities within the Campfire project about the ammonia-fueled cracker engine power unit for inland waterway shipping. As a remark at the beginning, due to time constraints, I cannot show all of my slides, but I guess this will be handed out later after the conference by the organizers. So let's go further. I would like to give you a short information about the project tasks and the setup, about the project schedule, the current development activities, and there I can already promise that I can show you today a quite very new thing. And then I will give you an insight about the outlook. So within the Campfire research project, several technologies around the production and utilization of renewable ammonia are under development. And here we will handle two projects which are concentrating on ammonia-fueled inland waterway shipping. This is a quite interesting fuel for this application, so we have split that into parts. One is dealing with the general ship integration, the concerned regulations and safety aspects, and the other is dealing with the hardware establishment for the complete energy conversion. And this I will dive a little bit deeper now. The main focus is to develop a power unit of approximately 350 kilowatt output, which is a typical size for inland waterway vessels, which can be used as a one-engine configuration, but also as a multi-engine configuration. For that, we have built a very comprehensive consortium of 10 project partners. So that the cracker and engine development is executed in parallel at the different locations, and at the final end we will combine both at the Campfire Open Innovation Lab at Rostock-Poppendorf to demonstrate this complete power unit. We started at the end of 2021, so approximately 1 year ago. The concept development was initiated for the cracker itself, for the engine, but also for the packaging. When you think of an inland waterway vessel, there is not too much space available, and so we had to consider from the very early beginning this space constraints. Then we started the model development for the simulation of the different components and the unit. In summer this year, the single-cylinder engine testing has been started at Karlsruhe Institute of Technology, and end of next year, approximately same time, we are planning to start the containerized full-scale engine, which should be then available in the container. The cracker unit is going to be tested within 2024, and then in 2025 we are going to test the complete setup, the complete power unit, so that we have end of 2025 an operational demonstrator power unit. What have we done until now? You can see it here. The main tasks are the definition of the engine combustion concept. For that, we developed a very systematic approach with a big matrix of different combustion concepts. Currently, for the ammonia combustion in internal combustion engines, there is not so much knowledge available. In the marine industry, especially the very large two-stroke engines for the big container vessels and so on, there is also ammonia already under investigation, but they have a very important advantage compared to our small engine here. They have time. These engines are typically, the big engines are operating typically with 60 to 80 revs per minute, so just 1 rev per second, and we are operating typically at 1,500 revs per minute, so we cannot use the time to burn the ammonia. So we have to find other ways to improve the combustion. So this general concept is very important. Another task is the ammonia injection system. Typically in injection systems, especially direct injection systems, are dealing, for example, with diesel fuel, which you know as well. Diesel fuel is has also the possibility to lubricate the injection system. Ammonia is a dry fuel, so we need also to use, or we need to develop a respective injection system which can cope with this dry fuel. Then, of course, the single-cylinder engine had to be set up, and you can see here the test facility at the Karlsruhe Institute of Technology, and of course the simulation, the modeling has been started as well, as already mentioned. So here you can see the first test results. This is a single-cylinder engine, the first wake up, I would call that. This is just with hydrogen. So the typical things happened. On the left-hand side, you can see a typical combustion curve, cylinder pressure. On the right-hand side, you can see that there is something different from the left one, and this is a pre-combustion in the intake manifold, so you have a backfire into the intake. And this is, of course, not a typical combustion as it should be, and you have to avoid it, but this is also typical for hydrogen combustion. And as we are using hydrogen as an igniter for the ammonia, it's quite important also to get a lot of knowledge about how the hydrogen combustion behave. So, but now, last Friday, we were able to operate the single-cylinder engine on ammonia, and this is really new because there is not much knowledge available, and interesting-wise, the concept we have chosen from the big matrix, what I mentioned in the beginning, is working very properly. So we are using a direct injection of ammonia combined with a provision of the hydrogen into the combustion via the intake side together with the air. And we have here a 50-50 fuel energy share between hydrogen and ammonia. And already, I guess you are not all familiar with the typical figures of combustion engines. 11 bars BMBF, this is a quite, this is a good part load operation point, and already in the range where it's really interesting. And what is also quite important is from the beginning we reached a very high efficiency of already nearly 40%. The goal, what we set in the beginning, was 40%. And so we are very happy to reach already this at this early phase. What you can see on the right side, there you can see the torque versus time of the engine. This is not so stable, so there, of course, there needs a lot of improvement, but it's a good step ahead. Regarding the cracker development, there is the layout ongoing, and the test field engineering is under process. Parallel, we are doing also risk assessment and the safety evaluation of the ammonia and then hydrogen handling. You can guess on board of a vessel we have quite strict regulations for that, although a lot of them are not in place already. And of course we need also to specify the coil testing infrastructure. Regarding the packaging of the units, you can see here the current status. So we are working with standardized container units. You can see on the left-hand side a typical inside for the motor container where the combustion engine with the generator is located, and in the middle you can see the complete package where the small container will contain the cracker from ZBT. On the top right, this is the base engine we are using for this development from Liebherr. Size-wise, this is comparable to a truck engine. Yeah, how is the project going? We could have a successful start of this complex project. I have mentioned we have 10 project partners. So this is, you can guess this is not in so easy handling. We have an intensive regular alignment of all project partners. What was also important to identify the critical paths, and here we are well on track, I would say. We are now doing further detailed research by the single-cylinder research engine in Karlsruhe. And of course, the results will also go into the simulation models. And what is now going on to detail the safety topics of the ammonia usage. Further on, we are discussing already a follow-up project for optimizing the design and the operational behavior of the cracker engine power unit, because the special focus will be to prepare everything for a non-road certification, to be able to have really a product at the end of this development. Thank you very much.
Thank you very much, Professor Moore. We will sort of directly go into the second presentation of the Campfire project of TransHyDE, and it's my pleasure to introduce to you the next speaker, Klaus Büssen. And he worked for large German shipping companies as shipping clerk and had a special focus on logistics. He holds a degree of Wismar University in nautical science, transport options and logistics. And since 2021, with the project, he became project staff at the Institute of Innovative Ship Simulation and Maritime Systems. And he will present to us green ammonia logistics, infrastructure, transportation and bunkering. Please welcome Klaus Büssen.
Yeah, hello. First of all, thanks a lot for the introduction. Hello, everybody. I'm really happy to be here. Today, I will give you an overview about ammonia logistics and infrastructure, including bunkering and transportation. I will introduce to you 4 sub-projects regarding this topic, including new technologies we develop. We all know the energy transition is associated with importing green energy, such as green ammonia, to meet the demand we have in Germany or in general in Europe. Therefore, it's necessary to develop an ecological, sustainable, and economical logistic and infrastructure concept for the distribution and transportation of green ammonia. We consider the amount of produced green ammonia imports, as well as modes of transport, storage facilities, and future and current consumers. We do specific demand forecasts and develop climate scenarios and focus on the greenhouse gas reduction potential of green ammonia. Eventually, we will make a simulation of a Germany-wide ammonia infrastructure and supply with all the data and knowledge we gained. Yeah, here you can see the partners who are involved in the sub-project. We have 3 research institutes, the Incl, the DST, and the University of Applied Science. Also on board the partner ISC, who are experts for plant safety, as well as the partner from the industry, the shipping company Detmar. To figure out what is the current situation in Germany regarding ammonia logistics, we do a status quo analysis. We do this to identify what is possible today and where there might be problems in case of increasing volumes of ammonia. So we look where the production facilities are located, where the transshipment points, where the storage facilities located, how the ammonia is being stored. Is it cryogenic storage or is it pressure liquefied storage? How are the capacities? Where are the terminals located? And to get as much details and information as possible, we interview enterprises and players who already today cover ammonia in their business fields. You see, we export ammonia from Germany. Also, we import ammonia to Germany. We have an annual average of 330,000 tons. We export mainly to our neighboring states. Looking at the imports, we import an average 250,000 tons per year. And this is, as you can see, from all over the world. Obviously, this is still gray ammonia. As I already mentioned, we discover all these locations to create a data collection to eventually visualize or get a geographic visualization of all these locations. Additionally, we determine the current and future ammonia demand, as well as the amounts of ammonia produced and imported in Germany. Speaking of demand, like I mentioned before, we are doing demand forecasts on energy consumption for different sectors. Here you can see an example for the transport sector. We look at each federal state separately, and the most interesting part about it is what's going to be the share of hydrogen or ammonia in within these different sectors. Also really interesting is what's truly the greenhouse gas reduction potential of green ammonia. To estimate the greenhouse gas reduction potential, we create our own climate scenarios with the base year of 2035. And all the data will eventually, is going to be fed into a simulation software to get or to visualize our concept. Now I'd like to go on with the second sub-project. I'd like to introduce our flexible NH3 refueling system. I'd like to introduce solutions for refueling by ship-to-ship and truck-to-ship bunkering. We develop a non-stationary option for supplying ships with ammonia as fuel. This includes safety concepts, development of new components, as well as new components for various NH3 bunkering operations. We determine the type of fuel tanks, as well as the outer limits of the ammonia bunkering system. And additionally, we're going to simulate the gas dispersion in case of a release of ammonia. Yeah, these are the partners who are involved in this sub-project. It's also a combination of research institutes and partners from the industry. Here you can see our bunker barge design. We determined the dimensions as well as the required engine for this barge. This concept is needed as soon as there's enough demand for green ammonia on the part of the ship fleet. Here you can see our developed hose and coupling system. We are using innovative components such as the dry coupling, NH3 dry coupling, or the NH3 breakaway coupling to keep operation as safe as possible. Talking about safety, there are many different bunker options with ammonia. Here just shown a few. But they're all different and they have to be safety concept for each of those options. I highly suggest the ammonia bunker study from Singapore. This paper came out 2 months ago. It includes many information regarding ammonia bunkering operations. Here's an example of our mobile flexible solution. Especially in the first ramp up, small to medium quantities are expected to be supplied to a limited number of ships that already converted to ammonia propulsion. So a flexible mobile solution is needed. What does it look like? There's pressure liquefied ammonia is being delivered in an ISO container, for example by truck, to the terminal. Then the ammonia is being pumped into the fuel tank on board, which is also a movable container. Interfaces, safety concepts, and processes have already been defined, but especially the lack of experience in regulations and high safety requirements make this really complex. Now I'd like to present the third sub-project for today, our onshore NH3 refueling facility. In order to handle ammonia imports as baseload supply for large consumers, a facility like this is needed. The refueling facility is capable of loading and discharging ammonia, so gas carrier that carry ammonia as cargo, as well as bunkering vessels which use ammonia as a fuel. It's really complex to design an efficient, climate-neutral refueling facility for cryogenic and pressure liquefied ammonia for all these different applications. Eventually, we will demonstrate this facility at our test field Campfire Open Innovation Lab in Rostock-Poppendorf. Last but not least, I'd like to present the fourth sub-project for today, the NH3 to H2 filling station. In this sub-project, we develop a plant which produces fuel-suitable hydrogen from green ammonia. How does it work? The hydrogen is being cracked out of the ammonia and then being purified. For our cost-effective purification process, we use ultra-fine cleaning technology. This filling station is designed to supply up to 15 public buses which run on hydrogen, which is equal to 600 kilograms of hydrogen. Obviously, it's important to consider the profitability of this system, and we will also demonstrate this plant at our test field Campfire Open Innovation Lab in Rostock-Poppendorf. Here are the partners who take part in this sub-project. And also for this new developed technology, it's essential to have safety concepts. So we researched on existing rules and regulation to conventional gas stations. So already today, we have a fuel mix at the gas station. There's gasoline, diesel, CNG, LPG, even hydrogen. So we try to adapt there and try to identify the hazards that might occur. So especially if is there any external source of danger? Is there any source of danger during operation? Or interactions between other filling stations right next to the NH3 to H2 filling station? Or also the interaction with the surrounding area, such as buildings and facilities. For the hydrogen purification, we develop and produce our own components using innovative process technology like laser welding and 3D screen printing. Like I mentioned before, it's really important to consider the profitability of this plant. So we look at the cost for investment as well as the operational costs for this filling station. But the crucial point is, or the crucial question, what's the final cost for 1 kilogram hydrogen, bottom line, coming out of this filling station? We look at the market potential in Europe and worldwide to have this technology ready for export at the time market launches. Thanks a lot.
Thank you very, very much, Klaus Büssen. And please let us take the questions from the audience to Professor Moore or the presentation of Klaus Büssen. So there's one in the middle up there. And due to the time, I would say maybe address the other questions to both of them in the lunch break. And that we just take one question.
I have a question to Professor Moore. You are combusting ammonia in your internal combustion engine. What are the what are the NOx problem related to this combustion? Normally, you have the danger of fuel NOx formation.
Yeah, you're fully right. This is an important topic we are going to investigate. Because it's not only nitrogen oxide as we know it from diesel cars or petrol cars, but also regarding laughing gas. And this is one of the major research topics on the single-cylinder engine results. And interesting-wise, the first results showed not so much NOx than expected. And this is related to the combustion concept. And so we are quite optimistic that we can keep that level. Anyhow, we are expecting to install a catalyst in the exhaust gas anyhow.
Thank you very, very much. And please give Dr. Moore and Klaus Wissen a big applause for their insightful presentation on the applications of ammonia. And they're available in the lunch breaks, so please address them directly with your further questions. And we heard already that ammonia is a possible energy vector for import, and I'm delighted to introduce to you the next speaker, our guest speaker. He is His Excellency Philip Green, and currently Australian Ambassador to Germany. He's a Senior Career Officer of the Department of Foreign Affairs and Trade, recently First Assistant Secretary, United States and Indo-Pacific Strategic Division. And he served in different missions worldwide, for example, in Singapore, South Africa, and Kenya. And he will give us, or bring us the sunshine. His presentation is called Shipping the Sunshine, International Green Hydrogen Cooperation. So please give him a very warm welcome. Hello.
Well, thank you very much, Dorothea, and may I greet you all this afternoon with the word Jumalundi. Jumalundi is the word in the language of the indigenous people who are the traditional custodians of the land around our nation's capital, Canberra, which means hello and welcome. There are around 250 Australian Indigenous languages, and it would take me all of my presentation to greet you in all of them. So please accept my greeting in that one language as a token of our respect for our Indigenous people and their elders, past, present, and emerging. I was really delighted to take up Mario Ragwitz's offer to make a presentation here today. He and I have been very close partners for 2 years now in the Australian-German hydrogen partnership known as High Supply, and I want to begin by thanking you, Mario, for being such a great supporter of green hydrogen and someone who's helped give us a lot of guidance about where we can take this. Just 5 months ago, a new Australian Prime Minister was elected, and he gave a very short speech on the night that he was elected. He said a very few things about what he wanted his government to do, but in those few things, a key thing he said was that he wanted Australia to be a renewable energy superpower. A renewable energy superpower. And for me, that was music to my ears, because in my 2 years here in Berlin, my top focus has been on supporting the development of a supply chain in green hydrogen derivatives between Australia and Germany. And I now have all the political backing that I need to make that a reality. This is a slide produced by the bilateral feasibility study between Australian and German scientists, which gives you an idea of the underlying wind and solar potential of various economies around the world. The important thing here, we saw earlier that Australia is amongst those countries that is blessed by very good sun conditions, but we also have very good conditions of wind at night, particularly in the southern part of our continent, the so-called roaring 40s, where there is constant wind, which obviously is valuable when we're trying to produce a renewable product 24/7. So we can produce, so we have good conditions for producing green hydrogen, and we also have the ability to produce quite a lot. Sorry, this is quite a busy chart, but let me draw out some of the key elements here for you. We have a big continent and only 25 million people. That means that we have a lot of land that we'll be able to devote to delivering green hydrogen. And here's one way to think about it. If you just take 2% of the Australian landmass and you applied that to green hydrogen, that can produce 7 times Germany's annual requirement for molecular energy. Now, we will have other places that we are sending hydrogen apart from Germany, but it demonstrates that with only a small proportion of our landmass, we can produce a lot of it. We think that by 2040, we will be exporting in the order of 500 terawatt hours of green hydrogen. And just to give you a sense of the scale of what is happening at the moment, a full 1/3 of all of the investment in minerals and energy projects in Australia at the moment, a full 1/3 is being devoted to hydrogen. So, you know, we are a country where minerals energy has been at the core of our economic success over the last 50 years, and we continue to invest in minerals and energy projects, and 1/3 of that investment is now going into green hydrogen. Now, there are other reasons, however, why Australia and Germany are natural partners. We have good underlying conditions to produce renewables. We have a lot of land, and scale will be important in making this industry work efficiently. We also have 50 years' experience in the business of exporting energy. The LNG industry globally started in Australia, and many of the firms that are pursuing Australian green hydrogen projects are firms that are skilled in the business of exporting, especially LNG. So if you're looking for a country which has got not only good territory, but politicians, bureaucrats, lawyers, accountants, project managers who are used to doing energy projects at scale, we have all of that. But we think that the partnership with Germany is a beautiful partnership because we also need the key thing that you have. We have a lot of the underlying capabilities to produce green hydrogen, but what we don't have is a global class, large scale manufacturing industry that can produce the plant and the equipment that will be needed to make an Australian hydrogen industry work. That is just not the way our economy is set up. And so what I see when I hear project promoters in Australia talking about their partners, and in particular their electrolyser partners, I'm hearing the German names turn up all the time. Siemens Energy, Linde, ThyssenKrupp, MAN, these are at the head of the queue for being involved in the Australian hydrogen projects. So there's a lot that we've got going for us, but you will have noticed that Australia is a long way from Germany. And so one of the things that we and the bilateral study has put to particular focus is the question of transport and how big an issue this is. Now, the key conclusion is that when we are talking about hydrogen derivatives, and particular green ammonia and green methanol, the transport issue is not one that should stand in the way of a supply chain. Our calculations are that across the whole supply chain that you would be required to produce green hydrogen, the cost of transport between Western Australia and Rotterdam is in the order of 4% of the total supply chain cost. And we think that we can be a competitive supplier as far away as Germany for ammonia and green methanol on that basis. It's worthwhile saying at this point that we have had excellent cooperation with the Australian government and between the Australian and German governments, and with Australian and German industry and science. I guess I want to mention 3 particular initiatives. Firstly, there's been a very strong partnership called High Supply, which has brought businesses and scientists together to study elements of the supply chain. A final report of High Supply is expected in the next couple of months, and I don't think it will surprise anyone if it concludes that there is indeed not just a feasible supply chain between Australia and Germany, but a desirable one, and one that is already starting to take shape. We have an initiative called HyGate worth about 75 million euros, which is encouraging German and Australian firms to work together on key parts of the supply chain. And we expect the successful bidders for that funding to be announced in January of next year. And finally, I want to mention the very powerful delegation led by Bettina Stark-Fatzinger, which went to Australia, including for the Australian Hydrogen Conference in May last year, led by the Minister, but with Mario and with Robert Schlögl, with Holger Losch from the BDI. They made a very, very big impression on the Australian audience, and dare I say it, on the Japanese audience at the Australian Hydrogen Council. Now, a little bit more about Australia. I'll come to the specific projects in a moment, but first of all, some headline statistics. We calculate that the level of government support for the Australian hydrogen industry between our state and federal actors is now in the order of 4 billion Australian dollars. That's about 2.5 billion euros. The government has identified 7 hydrogen hubs as a place to build shared infrastructure, and our expectation is that projects will coalesce around those 7 points. They are broadly consistent with the dots. Unfortunately, I don't think I have a pointer, but in various places around the country, all on the coast, is where those 7 hydrogen hubs have been set up with shared infrastructure. Look, there are probably 100 Australian hydrogen projects going on at the moment. We at the Embassy follow about a dozen of them, the big ones that are likely to lead towards exports of green hydrogen derivatives. What we are perceiving is that there's now a lot of investment in Australia going into green hydrogen. We count that the number of hydrogen projects in Australia is about 1/4 of the total hydrogen projects all around the world. And the final thing that I want you to understand about the development of the industry is the key role that Japan is playing, both as an investor and an off-taker. And I want to run through just 3 or 4 of our more consequential projects, and they will give you an idea of where we're heading and what, and the role of Japan in particular. So the first, the Asian Regional Energy Hub. This has very large ownership by BP. It's there on the northwest coast of Western Australia. As you see, the plant size is huge. Their ambition is for a plant of 26 gigawatts. Production of ammonia, a focus on export, and they plan to be in business in 2028. When I started this venture 2 years ago, the idea of Australia producing green hydrogen was somewhere in the future, and you could imagine it might happen before the end of the decade. Now we have Australian firms which are planning quite clearly for plants and operation and export well before 2030. The next one is Woodside's. Now, Woodside, by the way, is one of the world's biggest natural gas producers. In fact, it just landed a cargo of natural gas from Western Australia in Rotterdam yesterday as part of our effort to help Germany diversify away from German gas, but they're getting very deeply into the business of green hydrogen. Once again, their output is for ammonia. It's a much smaller project, but their plans are to come into operation in 2026, so a bit earlier than the Australian Regional Energy Hub. Stanwell in Queensland is interesting. Here you might take note of what's in the bottom right-hand corner here. Strong involvement from Japanese interests, not just for offtake but also equity. And this one too is planning for to be able to produce by 2026. And finally, last but not least, South Australia, which is a jurisdiction which is very keen on hydrogen. The Premier of that state, his top objective of all objectives he has is to make South Australia a major producer of green hydrogen. Once again, here we're seeing a relatively early date of operation of 2026. So, ladies and gentlemen, we feel confident that an Australian hydrogen industry is being built at scale. We are very confident that that will involve substantial exports of green molecules around the world. I'm certain that that will include export of green molecules to our energy partners in Asia, and Japan, Korea, Singapore are key in that. But all of the Australian project promoters that I talk to have a very healthy interest in the German market, and the Australian government certainly does, and we will be doing all that we can to create this supply chain in green hydrogen derivatives before very long. Thank you very much.
Thank you very, very much, Mr. Green. This was a pleasure to listen to you and for you to bring the sunshine to us. And I would like to open the floor for questions from the audience. There's one here, please.
Thank you for the sunny presentation. You mentioned this interest of Asia, especially Japan and Korea, in hydrogen derivatives. And I know there is a steady ship cruising by Kawasaki in between of Japan and I think it's Gladstone. And this is not for ammonia, but for liquid hydrogen. How about your plans in liquid hydrogen? Because I always think in Germany we have not only need in molecular energy in form of ammonia, but we will need a lot of hydrogen in pure and even in liquid shape for our transport and mobility. So do you have plans to ship liquid hydrogen as an element? Because I know, for example, Korea is now in the application process of a big vessel, 160,000 cubic meters, like a typical LNG vessel. So what is your statement on that? Thank you.
So that's a really good question. I thank you for it. Look, I am trying to give German audiences an honest appraisal of what I think is in prospect. And, you know, the question you ask is a question on which I get different answers from different Australian project promoters. I'm not an expert in this. I can only explain to you what I hear from those who are in the industry. And what I get from the industry is that I think the balance of opinion is that the costs associated with exporting liquid hydrogen from Australia to Germany look very high for the foreseeable future, and that most Australian project promoters don't see that as a viable option in this decade. They would like to do it, and if the technology becomes available at a realistic price, they will do it. But the standard view is that that is more likely to be an issue for the 2030s rather than the 2020s. You're of course right that that means that the market that we are shipping into is more limited than if we were producing liquid green hydrogen, but the whole business of transporting that at extremely low temperatures is expensive. Now, maybe the Japanese and the Koreans are finding technologies that allow that to be possible sooner. That would be terrific. I see a couple of heads shaking. So, for the time being, my strong focus is on green ammonia and green methanol.
Thank you very much. Any other questions for Mr. Green? Yes, Hauke, please.
Thank you very much for your presentation, Your Excellence. How will Australia manage the fresh water supply necessary for electrolysis in Australia?
Yeah, good question. A lot of you will think about Australia being a dry continent, and it is. But there are important things to know about the geography of our country. The first thing is that you are probably most familiar with the southern part of our continent. That's where the British came and settled. And the reason they came and settled there was the temperatures were more temperate. But in some ways, Australian economic geography is upside down, because it's the northern part of our continent that has the largest amount of resources. It's the northern part of our continent that is closest to Asian markets, and it's the northern part of our continent that gets the most rainfall. In fact, twice as much rain falls on the northern part of on the top third of our continent than in the bottom two-thirds. So water is an issue, but it tends not to be an issue in places like Gladstone and Newcastle, where you saw some of those facilities being set up. The other point to make is that where desalination plants will be necessary to create green hydrogen, that doesn't look to our project promoters like a major impediment. They figure that across the whole supply chain, the cost of the electrolysis process, which of course would be done with renewables, is around 1% of the total supply chain.
Thank you very much. We've got another question up there.
Well, thank you for the insight, Mr. Green. You said that at the moment that you're planning to become a large energy exporter because you lack the manufacturing industry to consume it yourself. What are your expectations if this situation remains in the future? Or do you think that manufacturing companies will actually move to Australia to, to avoid the transport?
Really good question. There will be some of that, but I don't think in the near term there'll be a lot of that. So Australia has natural advantages in terms of energy, and as you know, it has natural advantages in terms of raw materials. It doesn't have natural advantages in terms of proximity to global supply chains, and it doesn't have the natural advantages that, for instance, Germany has of a long tradition of successful manufacturing industry. I won't try to explain all of Australia's economic history, but the short story is that we have proved ourselves to be very good at and very sophisticated at shipping primary products, and our efforts to go up the value chain have normally not been very successful. Now, I know that we're in a different dimension, and that might change some of those underlying dynamics, but my view is that it won't change them fast. And governments in Australia being cautious about how much they seek to change our economic model. I will say this, though, one of the ideas that is in our mind, and it relates to the previous question about whether it might be better to be shipping green hydrogen in a liquefied form rather than ammonia. It seems to us that shipping ammonia and methanol won't get us into the steel supply chain in Germany. And nor do I imagine that we will develop a steel industry in Australia that has anything like the complexity and scale of the German steel industry. But it is possible that we might choose with German partners to engage the first phase of the steel making process and taking iron ore from its raw form to what is called in the trade hot briquetted iron ore, small clumps of iron ore which can be transported without great complexity from Australia across the world, which would help your industry bring down the energy component of what gets done in Germany. We think that there'll be a role for that sort of intermediate good, if you like, to be shipped from Australia to Germany.
Thank you for the answer.
Thank you very much. And looking at the time, I say thank you very much, Mr. Green, for this beautiful presentation and insightful cooperation. And we have the pleasure to have you here over the lunchtime. So any questions that arise, please address them directly to Mr. Green. He will be there for you. And so as I mentioned, now it's time for a lunch break, and we will resume the conference at 2 o'clock or 2 p.m. Berlin time. And we say goodbye to the live stream at the moment, and you find lunch directly outside, and we welcome you back at 2 p.m. Thank you very much. Oh, it's been a pleasure. This is wonderful. Oh, es war echt schön. Also das, danke. Welcome back from the lunch break. I'm very happy to continue the TransHyDE Scientific Conference together with you. And we heard such interesting presentations this morning and tackled already a couple of energy vectors like the gaseous hydrogen, ammonia. We touched also briefly sort of liquid hydrogen. And I have the great pleasure to introduce to you the next topics coming from our TransHyDE project Apply. And this is focusing the area of liquid hydrogen. And I'm very honored to introduce to you three speakers who will present one after the other. The first one is Dr. Michael Wolf. He's a physicist and holding a doctorate of the Institute of Technical Physics at the Karlsruhe Institute of Technology. He held different research associate positions there and was focusing his work in the development of high-temperature superconductors for fusion magnets, as well as on liquid hydrogen, the hybrid energy transmission. And he's together with Professor Arndt, who is here today as well, co-coordinator of the TransHyDE project Apply. And two of his partners in the project, one is another staff member of the Karlsruhe Institute of Technology, Mr. Sebastian Palacios, who holds many years of work experience in the development and evaluation of energy, economic, and technical scenarios on national and international level. After the completion of his studies in physics and renewable energy, he is a doctoral researcher at the Karlsruhe Institute of Technology. And he's very much focusing on development and evaluation of application scenarios for the combined transmission of liquid hydrogen and electrical energy. And the third speaker is Professor Dr. Alexander Alexeev. And he studied and was research associate at the Department of Cryogenics of Moscow Institute of Power Engineering. He obtained his PhD at the Technical University of Dresden and was a guest scientist in Stanford. He joined industry and after several positions there, he's currently at the Linde AG in Munich as a technology and innovation manager for clean hydrogen technologies. He also is a honorary professor at the Technical University in Munich on the chair of industrial cryogenic systems. So please let us welcome Dr. Michael Wolf with his presentation of transport and application of liquid hydrogen.
Thank you for the kind introduction. So we'll start with the next session on liquid hydrogen. When considering the liquid hydrogen supply chain after the green hydrogen production, there are four essential steps, namely hydrogen liquefaction, liquid hydrogen storage, transportation, and use. And in this presentation, I will briefly walk through all of those four individual steps. The properties of liquid hydrogen, some of them were mentioned already this morning, are a high volumetric and as well at the same time gravimetric energy density, typically a low operating temperature. The boiling temperature is around 20 Kelvin at 1 bar. Gaseous hydrogen from a liquid hydrogen storage tank has a high purity. Liquid hydrogen is typically stored and transported at low temperature and low pressure. And in particular, there's no high temperatures required to release the hydrogen from a liquid hydrogen storage tank. And finally, it's since the case in use in applications, for example, in semiconductor industry and in space projects. So there are quite unique properties of liquid hydrogen, but also some specific challenges and opportunities. One of them is in the liquid hydrogen supply chain. The first step is always hydrogen liquefaction, which is an energy-intensive process, and a substantial amount of energy is required for the liquefaction of hydrogen. But as you can see here on this graph, substantial reductions from about 12-13 kilowatt hours per kilogram to below 7 kilowatt hours per kilogram are expected for future optimized and large-scale liquefiers. The second step in the liquid hydrogen supply chain is liquid hydrogen storage. And if you consider the boil-off rate, so the amount of hydrogen that is transferred from the liquid to the gaseous phase, the relative percentage per day reduces as a function of the storage size due to the ratio of the surface and the volume in the tank. And cylindrical and spherical vacuum and MLI or vacuum and perlite insulated storage tanks were realized so far up to capacities around 5,000 cubic meters, scaling towards higher storage sizes and technologies and ongoing, but it's not yet realized. So there's substantial potential for improvement of the efficiency, for example, by economies of scale. Once hydrogen is stored, it needs to be transported to the applications, and there are several transport options, one of them being the liquid hydrogen delivery truck or trailer, which is in operation in Germany, and the third part of this presentation will detail on the optimization of this type of delivery. Liquid hydrogen ships are one option, for example, for the bulk transport from continent to continent. So far, the largest LH2 ship actually from Australia transporting liquid hydrogen to Japan has had a size of the storage tank of about 1,250 cubic meters, so 90 tons, but designs are ongoing for ships up to 160,000 cubic meters, so relevant scales, but at the same time also large-scale import hubs for liquid hydrogen are not existing yet. The third option is delivery by railway tank wagon, which was in operation but not in Germany. And finally, liquid hydrogen pipelines, which is in operation but only in industrial facilities. So one can conclude that a trailer-based liquid hydrogen supply chain exists and an international supply chain is needed. Applications of liquid hydrogen are first of all a local hydrogen supply due to the high volumetric energy density of a liquid hydrogen in a storage tank and the high purity of hydrogen from LH2, which is, for example, at present used in semiconductor industry or for hydrogen fueling stations. For the large-scale supply of gaseous hydrogen grids, LH2 imports could be used, which allow a highly dynamic feed-in and no further processing, but this is not yet realized on grid scale. Important applications of liquid hydrogen range in the field of mobility, namely as a CO2-free aviation fuel, where in particular the benefits are the high gravimetric and volumetric energy density of LH2. Their R&D is ongoing, and also as a CO2-free fuel for heavy vehicles on non-electrified tracks, such as trucks or trains, again for the same reasons, and there some pre-series was presented. So a local LH2 supply chain exists today. There are many potential future applications, both stationary and mobile. And within the project Apply, we wrote a white paper on hydrogen liquefaction, storage, transport, and application of liquid hydrogen, which is currently under review within the TransHyDE community and will soon be available through the homepage of the hydrogen flagship projects and the TransHyDE newsletter. So thank you for your attention. I will now hand over to Sebastian Palacios.
Well, thank you, Michael, for the introduction. My name is Sebastian Palacios, and I will tell you how hybrid pipelines tackle multiple challenges in the energy transition. First, I will tell about the challenges, and then I will tell about the solutions. Some of the challenges in the energy transition are: first, we need an infrastructure for the import and transmission of hydrogen in large amounts. That's why we are here, TransHyDE. But the energy transition is more than hydrogen. That's why we need, for example, large amounts of renewable energies that produce electricity, electrical energy. As you can see in the point number 2, we will need 70 gigawatts of offshore wind power until 2045. Compared to today, that's a very big expansion. Besides this, we need to transport the electrical energy from the north to the south. And if we want to avoid the high costs and energy amounts needed to solve bottlenecks, we need to expand the electrical network as well. The third point, you see how the costs and the energy needed for solving bottlenecks in the last years have increased. Number 4, we need an efficient space usage. Germany is a densely populated country, and we need many applications in a small space. Number 5, last but not least, we need for each technology a high economical and technical efficiency. So what is a hybrid pipeline, and how does the hybrid pipeline tackle these challenges? It makes use of synergies. Imagine a pipeline that transmits liquid hydrogen and together electrical energy by means of a cable. Let's take a look to the liquid hydrogen side. The first property of liquid hydrogen that is used is the high volumetric density. If hydrogen is available in liquid form, it will also be useful for long-distance transport, like, for example, aircrafts, long-distance trucks, and also ships. But if we have liquid hydrogen, we don't have only a better high volumetric density, we also have cold and high purity. These two properties are also useful for other applications, like, for example, the fuel cells when they need high purity, but also the production of semiconductors, or for cooling. A hybrid pipeline can transmit fluid liquid hydrogen in a double-wall thermal insulated pipeline. It can be scalable to any size depending on the demand, and its maximal technical distance can be larger than 100 kilometers, as a patent has shown. On the electrical side, we see that the cold enables the use of superconductive materials. The benefits of these materials are they don't have any electrical resistance, and they have a high current density. This is useful for the transport of high amounts of electrical energy. Compared to copper, we have more than 2,000 times current density in terms of ampere per square millimeters. The example or the experiences done with HDA cables are several. For example, in Essen, there was a successful demonstration of this technology, and in Munich, there is now being constructed the largest superconductive cable in the world. These cables have been cooled with liquid nitrogen since it was cheaper, but if liquid hydrogen is available, then the performance will be increased. What are the experiences with liquid hydrogen and electrical energy? There have been already projects that use both energy vectors, but not transmitting fluid liquid hydrogen in bulk. Today, colleagues of mine are constructing a prototype at KIT. Other components in the supply chain are also being developed in Apply, like, for example, the current leads, which are made by Vision Electric superconductors, but also the tapes, which are developed by FIBA, and the superconductive pumps, which are made by Citre and TU Dresden. I have talked a lot about the technical advantages of hybrid pipelines. But as I have said, we need a high economical and technical efficiency for each technology. This is the main question of my work. I want to define scenarios where I can do a techno-economic assessment of this technology, because I want to know under which conditions this technology might be feasible. For this, I take a look to the upstream side and to the downstream side. I would like to remind you about a keynote that Professor Dr. Mario Rackwitz said. We need to think about the supply, the infrastructure, and the demand. Each of these sides interact with each other. On the upstream side, I take a look where the liquid hydrogen comes from, and I see that domestically, onshore is not likely to be produced, since we need large amounts of renewable energies, and we don't have that much space. In the offshore regions, we have a high concentration of electrical energy, which might be used for this purpose. On the other side, we will import hydrogens in large amounts, and one option is to get it in liquid form. Inside Europe, some studies have said that it's more probable that gas pipelines will be used since they are cheaper. On the electrical side, we see a high concentration of electrical energy in the offshore regions. And for the applications of liquid hydrogen, some studies, or many studies, have said that the industry will be the largest consumer of hydrogen. If we have already liquid hydrogen, we can also use it for long-distance transport. The electrical energy is also consumed at most in landlocked regions. That means also where the industrial sites are placed. If I analyze these different parameters, what are my results? Well, I decided to select the scenario Brunsbüttel, Hamburg, because of the two energy vectors that I take into account. As you can see on the left side, there is a map that shows which infrastructure is needed in the future for electrical energy and for hydrogen transport. I see that Brunsbüttel needs or gets a lot of electrical energy since it is an interconnection point, getting electrical energy from the offshore region, but also from the north of Europe. Besides, Brunsbüttel is getting a terminal which potentially can also be used for liquid hydrogen. Hamburg is a place where there is a large industry and also demand for large distance transport. So I see a lot of flows for both energy vectors in this scenario. And some studies have concluded that more infrastructure is needed, so this might be a good scenario for this techno-economic assessment. The next steps of my work are making this techno-economic assessment to know under which conditions the technology is feasible. But I will also take into account regulatory challenges. For example, the liquid hydrogen pipelines have been constructed, but only in private ground. Public ground, there is no experience with it, so there is no regulation in this case. Either is the case for big storage tanks of liquid hydrogen. Besides, there is a cross-sectional challenge, since actors in the gas and the electrical sector are mixed. However, if we consider going into the energy transition, we need to mix and go to sector coupling. In conclusion, I want you to remember that liquid hydrogen is not only a transport option. Liquid hydrogen has also other properties that are useful for the decarbonization of other applications. For example, we can use the cold to make use of superconductive materials, which, for example, can be used by hybrid pipelines. Hybrid pipelines are able to transmit large amounts of hydrogen and of electrical energy in a compact space. if the challenges will be tackled if it's shown that hybrid pipelines are feasible in an economical and technical way. Thank you.
Danke. Good afternoon, everyone. Welcome to this presentation about optimization modeling of liquid hydrogen supply chain. My name is Alexander Alexeyev. I'm working for a big industrial gas company, Linde, and some slides are prepared by me, but the most of slides are prepared by my colleagues, Christian Wolf and Oliver Chengguan Wu. Many thanks, guys. What's interesting about Linde? Linde is one of the largest producers of hydrogen. Every year we produce millions and millions of tons of hydrogen. Mainly it's gray. Some amount is a green in the meantime. And we transport and distribute this hydrogen to our customers mainly by pipelines. For this, we own and operate more than 1,000 kilometers hydrogen pipelines with compressor stations and even a high purity hydrogen cavern in Texas. That is huge amounts and huge experiences we own. Only minor part, as a really very tiny part of this hydrogen is liquefied. It is 170 tons per day. And we transported this liquid to customers by means of trailers. Every day we liquefy 170 tons of hydrogen, and every day we drive this 170 tons per day to customers. For this purpose, we have roughly 90 liquid hydrogen trailers. And we call it virtual hydrogen pipeline because it works already. What's interesting probably that it's only because we had a lot of discussions about ammonia and hydrogen, and therefore I decided to include the slide. As Linde is familiar not only with liquid hydrogen, we are one of the main technology provider for ammonia production. We have own proprietary technology for ammonia plants, and our customers like Yara, we deliver plants in this. To say the truth, if you need a really mega scale plant for ammonia, you go to Kellogg Brown, you go to ThyssenKrupp. But if you need a simply large plant, as a large, I mean 2-3 stadions, so like this size, then Linde is a good partner for this. The reason why I show this slide, just because we have this discussion what is the best ammonia as a hydrogen or liquid hydrogen, and for us it's really interesting because we have in the company both this technology to say, as from all independent parties, we are the most independent. And therefore, we performed a kind of study, internal study. If you are interested in results, please ask me then in the break. Today, we are looking on the liquid hydrogen distribution. That is only a small part in this supply chain. How it works. Usually on the liquefier side, we have hydrogen is liquefied and stored in huge liquid hydrogen tanks. Then you have to fill it into the trailers. That's a complex procedure. You need a pressure difference. Usually the liquid hydrogen in the tanks is stored at 1 bar, 1.5 bar, and you fill it in the trailer. The liquid replaces the vapor phase, and you have to remove the vapor phase. Because of pressure difference, this refilling process is a kind of expansion process. You have a flash gas. Because of liquid expansion, you have some boil of gas if this system is not ideal and insulated. And then the liquid hydrogen is delivered to the customer. And on the customer side, we have to fill the customer's tank. And that's even more complicated because the hydrogen stored on the customer side usually under pressure. It's not the pressureless tank. It's usually, if you have a hydrogen refueling station, there are 2-3 bar inside. If a customer operates a kind of fuel cell, you have a 6 bar and then therefore you have a for refill the hydrogen, you need some pressure in the trailer, and therefore to refill, you pressurize the trailer first. You evaporate some liquid. The vessel is closed. If you evaporate some liquid, then it pressurizes, and you get the pressure. Then you can refill. And during the refilling procedure, you have to maintain the pressure. You evaporate liquid hydrogen further. Then you go home. And during this sloshing process, the liquid and vapor are mixed, and at the end, the trailer arrives or achieves the site, and you have to depressurize this trailer. This is a complex procedure too, because liquid is under pressure. You've expanded the liquid, then it's flashed. It's like if you have a Coca-Cola bottle, if you open, you see this gas is flashing from the liquid. And from the vapor phase, it's interesting effect too, because if you expand it, partially the vapor is, you see a recondensation. In the Coca-Cola bottle, by the way, it's very similar. If you open, then you see sometimes also some white smoke inside. That is a kind of recondensation inside, and that is very, very similar process. But in reality, it looks like in this way. That is a picture of our site close to Los Angeles, huge spherical tank. That is a site close to Niagara Falls. We use a green hydropower here. There are 2 spherical tanks, and you see the trailers. There are 50 or 40. They are waiting here for filling, and then on the one side, as the upper corner, upper left, they are filling bays. Then trailers are filled there. What was our task of our team? We decided to try to simulate this whole chain thermodynamically, develop models to understand what are the losses, what are the reasons for losses, can we eliminate these losses, or can we mitigate those losses? That was the main purpose, and we started in a very classical way. For this process, you cannot use the standard S-band, Unisim, HYSYS models, because it's a dynamic process. The level, the temperature, the pressure inside of the vessels is changing always. Therefore, you need the dynamic models. Some processes are really equilibrium process. For example, the sloshing by mixing of vapor liquid. But there are a lot of non-equilibrium processes. For example, fast pressurization. You evaporate a part of liquid and pressurize the liquid in the trailer. But the liquid in the trailer remains still cold, as you cannot heat up the huge amount. There are 3 tons of liquid inside. You need some time. Therefore, this process simulator, this simulation includes as well as equilibrium approach, or we use non-equilibrium approach. That's dynamic simulation. In principle, it's very complex simulation. That's now we come to the results. I see I'm bad in time. There are some learnings. First, to say the truth, we are in middle of this simulation process. It's still not finished, but we can simulate the whole chain by means of this program. But we see huge difference between equilibrium and non-equilibrium approach. That's just really huge difference, and we can say this only equilibrium approach is not the right. Second, what we see, the results of non-equilibrium calculation shows that it is always better, always better. As the losses of liquid are lower, and what we are learning, and we can explain this why it is. It's because simply if you do this in non-steady state, as a non-equilibrium process, your liquid remains subcooled usually and has positive effect. During the expansion, it doesn't flash. If you inject this liquid into the vessel, then you condense the vapor, and that's really interesting. Simply, if you use an accelerated procedures or this fast refilling procedure that corresponds to non-equilibrium model, you can save a lot of liquid, at 10% of liquid. That's really much. If you try to improve your liquefier by 10%, that's cost really much money, and you save really a lot of OPEX and CAPEX, and that's simply by acceleration of refilling procedure. That's interesting result, and therefore we would like to emphasize this again. If we accelerate the refilling procedure, of course we have a savings in time, and time is money, but we really have a huge savings in terms of liquid loss, and that's real CAPEX and OPEX. Therefore, it was here, in principle, we would like to start next activity. It's about how we can accelerate this procedure. We need a large size liquid hydrogen pump. I think that it's a high priority action, and we recommend to support us and for development of this pump. Unfortunately, it's not of scope of Apple-High project. In Apple-High, we develop a very small, tiny pump, but we need here this large-scale pump. Good summary. The first models are developed. We can do this dynamic simulation with both models, equilibrium, not equilibrium. We have interesting results as a savings, 10% potentially available. These models are more or less universal, as we can apply it. We apply it now for hydrogen trailers, but we can apply it for filling of cars, heavy-duty trucks, railways, wagons, and etc., etc. Next, what we would like to do, would like to validate these models, as really measure the processes on our trailers. Then we would like to develop new models, combination of equilibrium, not equilibrium, and perform sensitivity study. That is a plan for 2023, 2024. Good, many thanks for your attention.
Thank you very much to the team of Apply. Please stay for further questions. Are there any questions here, I see, from the live stream? Please, Hauke.
This is probably a question to Mr. Alexeyev from Linde. What does a small hydrogen liquefier in the range of 150 to 600 liters per hour cost, roughly?
Oh, that's really... I know that these small hydrogen liquefiers, I'm not sure about the capacity, are built based on the laboratory helium liquefiers. So just took helium liquefier and revamped it, but adapted for hydrogen liquefaction. And I know that the helium liquefiers are today, the cost are less than €1 million. It's difficult to say what's production capacity. Maybe if you ask me, I can do this calculation. I need just 2-3 numbers. If you ask me in the break, I can give you a number.
Thank you very much. Due to the time, I would take one more question up here.
Questions also to Professor Alexeyev. How far from local equilibrium do you need to go in your non-equilibrium modeling in order to be realistic? Do you still get away with Onsager-like ansatz, or do you need to go really in full chaos theory and nonlinearities?
To say true, I'm not really understand. We have developed two models. One is fully equilibrium models. That is a kind of a Grenzfall in German. And we have for this non-equilibrium models, you can use the different approaches. One, for example, you say my liquids stay at the same temperature as a isothermal liquid approach, and then you will get some results interesting. We have two other approaches, isentropic, I think, the adiabatic compression, and another one, it's very close to this isothermal liquid approach. The real processes are that is something in between, and depends really on speed. If you're talking about processes taking days and weeks, then it's close to equilibrium. If you're talking about minutes or hours, that is like completely non-equilibrium. But if it's something in between, you have to model it as combination of a non-equilibrium equilibrium. I hope it helps.
Thank you very much. Please keep your questions until the coffee break, and the three colleagues will be there for you to answer and discuss with you. So give them a big applause. Thank you very much for your presentation. And we do have in the TransHyDE project a fourth energy vector that we are focusing on, and this is liquid organic hydrogen carriers, LOHC. Our project Heligoland is focusing on that, and I have the great pleasure to announce two speakers now who are going to present. One is Xiying Huang, who studied in China, in Paris, and also in Bayreuth. And she joined a German engineering company focusing very much on geothermal power plant and novel drilling technologies. And currently, she joined Hydrogenius, LOHC Technologies, and is in a position of Senior Business Development Manager, focusing very much on the Asian and also on the European hydrogen markets. And she will present together with Monja Grote, who studied at the University of Erlangen, Nuremberg, and Jena, graduated in chemical engineering. And she's working closely also with the research center of Jülich. And both of them will be presenting to you the optimizing hydrogen supply chain based on the LOHC technology by heat utilization at hydrogenation process and heat integration at dehydrogenation processes. So, can I please ask you to come to the stage? Give them a warm applause.
Thank you, Dorothea, for the very nice introduction. Hello, everyone. My name is Xiying Huang. I'm from the company Hydrogenius LHC Technologies. We are based in Erlangen in Germany, and we are a still very young company with focus on the liquid organic hydrogen carrier technologies. And
my name is Monja Grote. I'm from the HHLA, the Hamburg Hafen and Logistik AG, and we are one of the local terminal operators in the port of Hamburg. And we are focusing, of course, also on the import and distribution of hydrogen.
Okay, so before we start with our speech today, we would like to do a little bit teamwork and interaction because we are working together in the project Heligoland. And before we dive in the speech, I would like to ask Monja one question. So Monja, when I read the company name HHAA, so I always think about these very huge container terminals in Hamburg, and I'm just curious, how do you see the connection between LHC technology and the containers topics?
Yeah, containers comparatively to LOHC, because you can load it with hydrogen, not with goods, but with hydrogen, and unload it at the customer's site, and you can reuse it a couple of 100 times.
That's exactly the best way to explain the technology and to make it more easy to understand, so that we basically combine the hydrogen chemically with an organic liquid and load it with the hydrogen at the production site, and then transport the liquid to the off-taker and unload it the hydrogen, and we can reuse this liquid over a very long term of a period. So over 20, 30 years, we can still use this liquid and distribute this liquid in other projects, always use this liquid in other locations. So now we can jump to the speech of our speech today. So the agenda will basically consist of 3 points. So I will give you a very short introduction about the hydrogen supply chain based on the LHC technology, how it could look like in the future. And Monja will give you a description of the current status of our project Heligoland. And then in the last part, I will introduce a little bit more about what we are doing within the project Helgoland to upscale the LHC technology to optimize the hydrogen supply chain. So this is a very simple graphic to show how the hydrogen supply chain based on the LHC technology could look like. So as we already mentioned very briefly, at the production side, we can chemically combine the hydrogen with an organic liquid. In our case, it's benzyl toluene, so short for BT, and we transport the loaded liquid either by a ship or by train or by truck to different off-takers, to different harbors, for example, in Europe, and then unload the liquid, so dehydrogenate the liquid and release the hydrogen for different purposes. And we are also working, we have established a joint venture last year in Norway with focus to develop LHC propulsion solution for the maritime industries, so in order to decarbonize also the hydrogen transportation part. And with our liquid carrier, this liquid carrier has a very high storage density, so it can carry much more hydrogen in compared, for example, with compressed hydrogen in tube trailer, and we don't have any losses also during very long distance transportation or during very long-term storage. And besides, the liquid that we use as carrier is hardly flammable and non-explosive, so it's even it makes the handling of hydrogen much easier. And last but not least, we can also use the existing oil terminal or fossil fuel infrastructure to transport the liquid, because it's an liquid very similar like diesel or other kind of oils. And most important is that as the carrier we use is not explosive or hardly flammable, so it's very safe and can be also permitted even in urban area. And this is also very one of the most important findings that we've got in the last year during our project development, that we've got very positive feedback from the authorities in Helgoland, that even on this island, on this small island, storage hydrogenation process and also the storage of hydrogen in form of LHC is permissible. So here is a small introduction into the liquid that we use. So it's called benzyl toluene, and as you can see in the video, the yellow one is the unloaded one, and it's like just an oil and non-explosive, hardly flammable, has a much higher flash point than diesel, and also stays as a liquid even at very low temperature. So this technology can be also applied in very cold regions like Norway or Finland or other countries. And it can be stored at ambient conditions. So LHC plus here means it's loaded with hydrogen. And as you can see here, we can just store the liquid in this kind of simple equipment. And as soon as we move the fire, then the liquid doesn't burn. And the storage density of the liquid is about 54 kilogram hydrogen per cubic meter of the liquid. And last but not least, the liquid itself is a commercially available product, so it can be already purchased today, but as a heat transfer oil. And we are the genius part of this technology is that we are using a heat transfer oil as a hydrogen carrier.
So I will continue with a description of the current status of our project Helgoland. So we see the port of Hamburg as a spot for a potential dehydrogenation site, and of course as a distribution hub for hydrogen in the European hinterland. And the island Helgoland models for us like a blueprint for the hydrogenation process. Therefore, we are looking for scaling potentials and, of course, the adoption to other projects outside of the TransHyDE theme. Due to some changes in the project on Heligoland, we had to switch our project a little bit. We have now 2 little hydrogen volumes in order to implement a hydrogenation plant on that island. So we are looking for other import sources as well from other regions like Norway, as being mentioned. Why are we still focusing on Heligoland? That is an easy question, because Heligoland is something like the worst case if you look on the industrial side. You have an island in the Northern Sea, so you have to deal with all the island island properties. For example, the dynamic hydrogen production profile due to the volatile wind masses, and therefore it is difficult for us, or challenging for us, to feed the continuous hydrogenation plant with these changing hydrogen masses from the wind. Then we have limitations in order to space availability, that is for the space or the size of the plants, but of course the space of the storage tanks as well. Then we are on an island in the Northern Sea, so we have challenging weather conditions like the corrosive salt water and very rough conditions according to waves. And we have very strict permitting conditions because Heligoland is a tourist spot and is in the national reservation of the Wadden Sea. So we are always close to tourist spots and to the national reservations. Our motto is, if it works on Heligoland, then it works everywhere. Now I come to the Port of Hamburg. We at the Port of Hamburg want to be a hydrogen import and distribution hub. And according to the LOHC use case, there are 2 scenarios that we could keep an eye on. First is the containerized transport. Therefore, we fill the LOHC in containers, ship them with the container ship to the harbor. Then we do the container handling as we do right now, and need smaller tanks because we can use the container as a storage tank. The rest, the dehydrogenation plant, where we unload the LOHC and can feed the hydrogen directly in the pipeline, or we can fill it in pressurized tank, in pressurized trailers, and get the hydrogen to the customers that aren't connected to a pipeline grid. This means less CapEx because the container handling is already in place, but higher OpEx because of the comparatively small volumes. The second scenario could be the tanker scenario, where we fill a complete tanker with the LOHC, transport it to the harbor, unload the tanker with the jetty, but then we need bigger storage tanks because the capacity must be higher. The rest is same to the other scenario. We have a dehydrogenation plant where we get the unloaded LOHC and the hydrogen out of it, and we can fill it either in the pipeline or in the high pressure trailers. This means a higher CapEx investment for us because we at the container terminal don't have right now the capacity for such big liquid bulk handling, but we have lower OpEx. And third version would be a decentralized solution where we ship the LOHC as LOHC to the end customer, for example in Munich, and dehydrogenate on site. So, since this workshop has a title, Overcoming Techno-Economic Barriers, we have the exercise to study these techno-economical barriers and, of course, their solutions. One solution is, of course, the economy of scale. So we're looking into multi-hundred tons per day hydrogen storage and release capacities in this TransHyDE project. Then we, of course, want to build a business case. That means we can use the heat that is generated from the hydrogenation plant, because it's an exothermic process. We can use it, for example, in the local heating network, in the district heating. And of course, we have to investigate to heat sources to integrate in our dehydrogenation plant, since this is an endothermic process and we need heat in the port of Hamburg. That is also part of the TransHyDE project, that we are looking for heat sources and the possibilities for heat integration in this plant.
So I just would like to mention the last two cases that Monia already introduced. So in the first case, we look into the heat integration at our hydrogenation plant and look into specifically the use case to generate the heat for example, a district heating network. And as it's indicated here on the slide, so at the hydrogenation plant, we can produce about 10 kilowatt-hour heat per kilogram hydrogen that we store, and at about 250 degrees Celsius. And this heat can be very well used for a district heating network. For example, we use the island Helgoland as a scenario, as a case study, and it turns out that we can cover almost 100% of the heat demand of the island. So really to help the island to decarbonize the district heating system. And we have also other creative use cases already in mind, and that we are going to also investigate in the next 2 years within the project TransHyDE. For example, use the heat for seawater desalination. And so the most important takings on this topic is that we, after 1 year research, or case study, and also research with the support of the Heligoland community, our findings is that it is very easy to, there are different kinds of opportunities and creative business cases that we can look into, how to get really use of this heat that we produce, how to really add additional values to the complete supply chain. So not only transport hydrogen, taking hydrogen from one country to the other one, but also try to generate more added value in the production country or the production region. And then the second case is that we look into the heat integration at the dehydrogenation system. As Monia mentioned, the dehydrogenation process is an endothermic process, so it requires heat for the process. And for our dehydrogenation unit, we would need about 300 degrees Celsius heat, about 11 kilowatt-hour heat per kilogram hydrogen that we release. And after 1 year, almost 1 year research, we found out that in the port of Hamburg, so in this location, there is sufficient heat that we can use. There is sufficient heat temperature that we can use, and it's technically feasible to integrate the process heat, for example, process steam, into our system. And we are now also going to investigate other heat sources in the next 2 years, and also try to generate also create technical concept, for example, that we can use not only in Hamburg, but also in other ports in Europe. Yes, that's our last slide. Thank you.
Thank you very, very much, Xiying and Monia, for this insightful presentation, how to use LOHC as a carrier. And the panel is open for questions from your side. There's one at the very back, please.
Thank you, too, for yet another option of handling hydrogen, storing it. And we always hope for very flexible systems. And yet again, you're talking about a chemical process. And can you share with us your experiences if the hydrogenation is really a really flexible turn off and on process as we all hope for? Or do we lose efficiency if we turn it off when the sun is not there and the wind is not blowing?
This is a topic that we are now working on, and according to our technical experts, this is technically speaking feasible. We can use different methods during the operation, change the operation points, and other measures and take other measures to make sure that the flexible operation can be realized without any loss in the efficiency.
Okay, let's hope. Fingers crossed.
Thank you. Thank you very much. Are there any other questions? I don't see any, so thank you to... Sorry?
There was one.
Oh, I'm sorry. Please, Professor Arndt, go ahead.
Yeah, thank you for this nice introduction in LOHC. If you think of your favorite application, is it more in the field of long-term storage of hydrogen, or do you think of high throughput? I would guess it's more in the term of long-term, as it's really stable as you put it away and forget it for some time. But or for rural applications, so far out, perhaps this might be a good approach. What is your favorite application use case for LOHC?
First of all, I mean, the LOHC technology is a young technology and a very innovative technology, and we are kind of, let's say, still exploring what would be the, let's say, very attractive use cases for this technology. And like I would say, also the hydrogen market and hydrogen economy is also just starts to grow. But by now, we do see that, let's say, the most attractive use case for this technology is the long-distance transportation, and so long distance and also large quantity transportation of hydrogen. In the meanwhile, we are also looking into other applications like using the liquid as energy storage technology over long term, so over years and years, and also use the liquid as a fuel, for example, on a vessel or on a train. So these are the other applications that we are also looking into.
Okay.
Did I answer your question?
Then perhaps let me add something, because I simply did a calculation, and this means a 40 tons truck is able to transport only 2 tons of hydrogen if you bound that to LOHC, right? So perhaps not so much for long distance, but more for long-term storage would be my guess.
Well, if maybe let us put this way around. So I know you are working on liquefied hydrogen, and with let's say per cubic meter of liquefied hydrogen has about I think it was 71 or 72 kilogram hydrogen, so the density. And with the liquid with LHC, we have about 44 kilogram hydrogen. So it's about like 20%, 18% less than liquefied hydrogen. But if we look at this question from another perspective, in order to increase the efficiency by 20% or 18%, we need to, or the industry will have to invest so much money to build up a completely new infrastructure, which is not yet existing today. So I think at the end, it's a trade-off for the people, for the industry companies that are actively involved in this market to consider if they would like to have a higher efficiency, then they need to invest a lot of money up front, or if they can, they would have this trade-off to use the existing infrastructure, have less investment, significantly less investment at the beginning. I think that's the question to the let's say companies at the end.
I want to add one thing, and that nails your first question, because I guess it isn't, is it LOHC or liquefied hydrogen? For every kind of carrier, there will be a business case. And if you want to store the hydrogen over a long time and you have heat available, then go for LOHC. But if you need the liquefied hydrogen, as liquefied hydrogen, for example, in Hamburg, we are the third biggest aviation cluster in the world, then go with liquefied hydrogen if you need it like this.
Thank you very, very much. And I think this is also the case for TransHyDE, because it is for any technology open, and we will consider the business cases in the TransHyDE project system analysis, where we heard already the keynote and also the presentation from Dr. Garcia this morning. So I think it was a very good point. We will need all the technologies in order to set up an efficient hydrogen infrastructure. And I thank you very much for this insight into LOHC technologies, and give them a warm thank you. Thank you. And you heard many, many presentations now for the 4 energy sectors in how to overcome techno-economical barriers and what kind of solutions can be offered by the TransHyDE projects. But if we have the technologies, can we apply them? That's the question. Are the rules and regulations actually up to speed in order to put them into action and bring them on the industrial level? And we have a project which is called TransHyDE Norm. And I have the honor to present to you Thomas Sustermans, who is the coordinator of this project, and he will give us insights of the research done in the project regarding the certification and also the standardization, current rules and regulations, whether they are up to speed and H2 ready. Let me give you some insights about Thomas. He is a process engineer of Cologne University, and already in his studies he focused very much on the topic of hydrogen. Currently he's a referee at the German Association for the Gas and Water Industries, called DVGW, or the VGW in English. And we're very, very happy to have him here to present today inventory of technical standardization and certification requirements of the hydrogen transport and storage options that we considered in TransHyDE. So give Thomas a warm welcome.
Yeah, thank you, Dorothea. Okay, in my presentation, I will give you an overview of the first results we got in Working Package 1. And let's start. So, on this slide, you see the agenda, and I would start with the motivation for standardization. So why is it necessary to have standards? And this is followed by highlighting the different working packages before I will present the results of the Working Package 1, which we finished this year, May. And after that, I would like to finish with the barriers and challenges we have in our project. And last but not least, I will give you an outlook on the next steps. So beginning with the first bullet point, why is standardization necessary? So standards ensures technical safety, like we heard before on the other presentations in this morning, and it ensures comparability, environmental compatibility, and acceptance, for example, in the general public. That's especially important, and it's a basis for optimization and efficiency. And therefore, standardization and certification requirements are crucial in addition to the technical and regulatory developments on hydrogen we heard before. On the left side, you see this chart. I'm sorry that it's in German. And it gives you a background to the standardization process, like we have it at the DVGW. And first, we start with the demand we have to detect. And after this, we get a committee which develops a draft. It is number 3. Before we get into a consultation time, which is mostly 6 months or sometimes a little bit longer. And after this, we go to the publication and then, of course, to the application of the standard. So the target of TransHyDE, which we heard before, is a practical introduction of transport and distribution and storage options for hydrogen. And what are we doing? So the technical and regulatory requirements are necessary for this, but on the other side, consistent guidelines like standards and certification programs. And in the green box, you can see our flow chart, and these are our planned workflow. And we start with state-of-the-art last year and finished this this May. And we're going to have a database including the state-of-the-art and a holistic gap analysis. And target is a time and implementation plan in beginning of 2025. Here you can see the different working packages and as well the project months and the time data on the right side. And meanwhile, it's not on the slide, we have a 6th working package, which is called H2 Hohlzug. And we also have an expert here, which maybe can tell you more about this. I'm not an expert on this project. And this one is more or less independent. But it fills an already identified gap, and it's about tensile tests for tubular steel samples flown through by hydrogen. And Mr. Sobo can maybe correct me if I said something wrong. Okay, so these are the 6 packages, and now to the results. So we created a data bank, and I'm again sorry that it's in German, in Excel, and for each topic we considered, so gaseous hydrogen in pipelines and in vessels, then liquid hydrogen, ammonia, and LOHC. We created a data sheet, and in each data sheet the structure is more or less like this one you see here. And it's divided in different columns to make it easier to search and to filter for special documents. And we start with the document number. Then the next one is the document type, like standards, technical rules, certifications, laws, and so on. The next one is validity range, like Germany, Europe, international, Asia, and so on. Then the title. Then we have a really German word like Gewerk, and I try to translate it with field of application. And it's divided in general, application, production, and infrastructure. And in the next column, you can specify it more. It with points material, staff, qualification, safety, products, and so on. And the last column you see here is gives a description of the standard or of the document we have. Then, of course, it's important to collect the committee And we also have the contact person, which is responsible for this project or for this specific standard. We have the the publication date, and then the revision status, like creation of a new document, a draft, when it's published, if it's published, revision planned or revision in progress. Then the document access, and the most important column, the H2 readiness level. And the last column is, has space for comments. So now the results. So as you see, we almost collect 700 entries. And as I mentioned before, this is the state from May 2022. And as you see in the second column, LUHC has had just 9 entries. That's because it just started 2 months before we finished this milestone. So we didn't have time to fill or to collect so many entries. But now we have more than 500 entries for LUHC. So the database is growing, and we have biannual updates for this, so it's still growing. And as you see here, the most entries for May 2022 are for pipelines. And maybe a little bit easier to compare is this in percent. And you see on the 56% is already 100% H2 ready, or it's not affected. And not affected means that there's a document or a standard, for example, which was created, which was not created for hydrogen, but for example for methane, but it's 100% applicable for hydrogen. Then the 3% is partly hydrogen ready, so 10 to 20%, and 41% is not yet ready, or it's not tested. And tested means we are not actually, at this time, we are not sure if it's applicable for a 100% hydrogen or maybe for 10 or 20. So we have to do a lot of work here. So let's go to the barriers and challenges. Maybe the most important challenge is the access to individual international standards, and as well the regulatory framework as a basis for standards development, which is partly existing, and of course the holistic documentation of existing standards and specifications based on this needs analysis of the relevant gaps. To give you an outlook, what are we doing right now? So we are right now in working package 2 since May this year, and we are interviewing the other TransHyDE projects to identify the relevant gaps for the several topics. And we're planning to finish it in April next year, and we're also planning to have a stakeholder workshop in the end of April next year with stakeholder outside of TransHyDE, and we'll hopefully identify then more gaps. Also, as I mentioned, we update the database in biannual intervals. And in working package 4, we will have a compilation of the results and evaluation, and with a target to have a recommendation for action in 2025. So I thank you for your attention, and if there are any questions, I would be glad to answer them.
Thomas, thank you very much for this insights into your very tedious work in compiling all the rules and regulations and checking them. And my question would be actually, how can you make sure that you really sort of get all the national, European, or maybe international rules that are applicable?
Yeah, that's a good question. So we did a plan how to make sure that we can have all the important standards or also papers, research papers, which are relevant. But we had a focus on the national standards. And of course, we will, yeah, with our interaction to the TransHyDE projects, but as well to the stakeholders, which are yeah, externs, we hope that we can get a holistic database for the standards and all relevant documents.
Oh, thank you very much. Are there any questions from the audience? Yes, I see one there. Sorry, here's already the mic.
Langbeck, EWT Solutions AG. Thanks for the presentation at first. So you've shown that there's already 40% of the pipelines which are H2 ready, 40%-ish. So my question would be, for example, there's the ASME B31.12 guideline, which is not a European but an American one. And there are very clear standards due to crack propagation and to brittle fracture and hydrogen embrittlement. Is that already taken into consideration into that H2 readiness, or how exactly is this defined?
Yeah, I would like to go back to the slides, but it's not possible. Is it maybe? Oh, no. Okay. Yeah, as you have seen in the table, it was divided into the four parts: hydrogen readiness level to 100%, to 10 to 20, and this is these are the parts we considered to put it into the right hydrogen level, readiness level. So. Oh, come on. So, yeah, so on the left side. But yeah, that's it. So.
But what's the guideline to be 100% H2 ready?
Yeah, so that's a question, because you have to define what is 100% ready. So, and that's not already done. So we just defined it, for example, by at the DVGW, we defined it in different it's a G260. I'm not getting the word. Gasbeschaffenheit, so I don't know the
gas properties.
Yeah,
gas properties.
And so we define it over this. So we have the second one, the second gas family. We have the fifth gas family, but others like the Canadians or Australians or the Asians, they have other specifications how they define 100% hydrogen readiness. But when I have it clear, I think next year COCO will do a workshop for hydrogen readiness. What is hydrogen readiness? And maybe that will help to define it. Because, yeah.
Actually, within the project, we have identified that we always speak about H2 ready, but there are different specifications depending on whether it's used in the political field. And we identified that from the scientific field, we can add sort of also components to the description of what means H2 ready. And this we took on as a project in the coordination role from TransHyDE, and we will start a workshop there together with the partners of the project in order to see how we can contribute to the definition of H2 ready. And I think it's a good point that we identify on the way towards hydrogen economy the gaps that are still needed to be filled. And I think this is a really good example for it. Everybody talks about it, but the definitions need to be really precise and sort of also commonly used or comparable to each other. So thank you very much for the question.
Maybe one more. I can give maybe an example. So at the DVGW, we work in pipelines. So it's our topic. So when we have 100% hydrogen readiness in pipelines, that means that there's no problem to put 100% hydrogen into this pipeline, for example, to feed in. So. Another example is then that we have components which are not hydrogen ready, but then we have to define what is hydrogen ready. But for some examples, it's really easy to define, because when there's no problem to feed in hydrogen, so then it's hydrogen ready. But so
it's not about the material, but it's about the feeding in process.
Sorry, once again?
It's not about the material, for example, of the pipeline. It's about the process, how you would get it in.
It's both. It's both, of course. It's about the materials. It's a process. It's everything. It's a staff qualification. It's yeah.
Maybe we can talk in the break.
Yeah.
Bitte? Thomas, we have one question from Mario. What do the numbers mean in the slide?
Yeah, of course. So this is, as you see on the right, there are 682 documents which we collected, so almost 700. And the other ones are in each column to each topic, the amount of documents we collected. So for pipelines, we collected 353, for LOHC 9 in May 2022, but now we have over 500, and and so on.
So we have sorry?
Once again?
Yeah, but then, like, what does the document mean? Is the document a relevant...
A document... A document is, like you see in the document type in the second column, it can be a law, it can be a standard, it can be a paper, it can be, a certification.
Then if it's 100% hydrogen ready, the document as such, the law is 100%.
Yes, right. Right.
Thank you. We've got another question up there.
First of all, thank you very much for the interesting talk and for mentioning us as well. I have two technical questions. So I'm involved in a European Horizon project exactly with this purpose, collecting the data and organizing it. So my two questions are, first of all, how accessible will be the data bank? Mm-hmm. And second, in which language?
Good questions.
Because we want to reach harmonization in Europe eventually. And
the accessibility is difficult. So it's possible to share it in TransHyDE, but we are not sure yet how to share it in public. But we would like to. And then English would be nice, but we have a focus on Germany, so
Okay, thank you very much.
Maybe for the audience also to know that we are going to issue white papers in due course and sort of describing and compiling results from the projects. One will be the study that Thomas has just presented, and we plan to publish them in German as well as in English. And they will be published then on the website of the BMBF. So we've got a question up here.
Thank you very much. I was wondering, when you flip back to the vessel chart and you looked into the vessel norms, is it just for inland waterway vessels or also for international shipping too? Because I believe I mean, I followed the IMO discussion the last 10 years, and there's a lot of, we heard it also before, not ammonia and hydrogen as cargo, but as shipping fuel. So I'm wondering, so what you analyzed here, the inland waterways or also the international shipping, and to what degree?
Yeah. Are you here tomorrow as well? Oh, no? Oh, okay. Because our colleague, Ms. Boyle, is the expert there. So maybe I'm not into vessels, so maybe we can share contacts and then that's maybe easier.
That's a good idea. So also, if you have any other question, yes, please.
A very quick one, thanks. From the 41% that are not H2 ready or yet not tested, can you separate these numbers? Like how many are not tested and how many are not ready, or was it one column?
Yeah, the bigger amount is not hydrogen ready. So yeah, I don't have an amount, but yeah.
Thank you very much, Thomas.
Okay.
And it's been really a interacting question session. So give Thomas a big applause for the presentation. And now we're coming to the coffee break. I'm happy to announce that, but we will have a shorter one. And if you're in need sort of for a drink or have not finished, just bring the cup in. We will resume with the conference sharply at 10 to 4 p.m. And we have a sort of stricter timeline then, because we will have the honor to have our Federal Minister of the Ministry of Education and Research speak to us. So we kindly ask you to come in quickly so that we can start with the first presentation and end sharply in order to receive our minister. Thank you very much and have a nice break. to tackle the topic of regulatory issues. We already heard it in different presentations this morning, this afternoon, that there are gaps. And we have the next presentation prepared by 4 ladies, in fact, and 2 of them are working at the Institute for Climate Protection, Energy and Mobility, the ICAM, it's called, and they both studied law. Leonie Ohle, she studied law in Hamburg, Berlin, and she gained professional experience in the public law domain. And Friederike Allolio, she studied in Freiburg, Pisa, and Amsterdam with professional experience in administrative law. And they both are research associates of the ICAM, and they're focusing on hydrogen infrastructure. And Ms. Ohle has an additional focus on transport import regulation, infrastructure development, legal questions around ammonia and alternative fuels for the shipping sector. And Ms. Allolio, she has additional focus on legal questions on international mechanisms in climate action. And after their presentation on regulatory barriers for green hydrogen with a special focus on infrastructure, we welcome the 2 ladies from Crew 21 and from the Fraunhofer Institute IEG, Cecilia Gage and Dr. Elena Timofeeva. They are our coordinators of the regulatory community, which not only tackles issues coming up in the project of TransHyDE, but also in the sister projects and working in collaboration with them of H2Giga, focusing on the industrial upscaling of electrolyzers, and the sister project of H2Mare, who is focusing on the offshore production of hydrogen with renewable wind energy. Ms. Gage studied law, and she's currently working on her PhD thesis in the field of green hydrogen. And Ms. Timofeeva holds a doctorate in legal science from the Free University of Berlin and also an MBA of ESMT Berlin. And she's has been visiting lecturer and research associate at Technical University Berlin, and is currently a research associate with the Fraunhofer IEG. So please welcome the first 2 ladies, Ms. Olio and Ms. Allolio.
Thank you very much for the very kind introduction. Today we're here to present the study on the legal framework of a future hydrogen economy, which my colleague Leonie and Ole and I wrote, and which will be published in the coming weeks. And first of all, a brief little agenda. We will start with a short presentation of our institute before giving an overview of our study results and the topics that we tackled. And secondly, we chose 2 focus topics to dive a little bit in depth what we actually researched and analyzed. So the ICAM is our institute. It's the Institute for Climate Protection, Energy and Mobility. We're in Berlin. Our institute has more than 10 years of experience in interdisciplinary climate research. We do have a legal focus, and our aim is basically to support the energy transition by providing or helping to provide a coherent legal framework. I now come to our study. First of all, what was it actually that we did? We looked at the hydrogen economy along the entire value chain with a clear focus on transport infrastructure, however, also in the spirit of TransHyDE. And we did a screening, a status quo analysis, and basically used this to identify barriers and white spots. So basically spots where there's spots in the legal framework there are still open questions and which could possibly hinder the ramp up of the hydrogen economy. And we hope that our study will be able to serve as a starting point to find maybe solutions in this realm. Those are here on the slide, the analyzed legal fields that we covered. We looked at green hydrogen production with the, of course, contentious issues still of what actually constitutes green hydrogen. We also looked at permitting and approval procedures of electrolyzers. Secondly, of course, transport infrastructure, as I said, it's a focus of our work at this point. Here we looked at hydrogen networks and storage, as well as terminals under permitting and approval or perspective. We did, however, not only limit us to grid-bound transportation, but also looked at the transport of hydrogen carriers, such as ammonia, by road, rail, and ship. Here, for the law on the transportation of dangerous goods is the prevalent field of regulation. Then, of course, we also looked at the regulation of hydrogen networks, and here we put a focus on the in-place regulation and upcoming regulation of pure hydrogen networks, as well as blending. We also took a look at the end use of green hydrogen. For example, we posed the question if and how emission trading can possibly serve as a tool to further enhance the hydrogen economy. And lastly, we took a look at the legal framework for funding, so in particular state aid legal framework and funding instruments that are important for the hydrogen economy. On this slide, you find one of the graphics that we included on our study. Unfortunately, it is in German, and I also don't want to go into detail and read this out loud. As I said, the study will be available soon. However, our general finding was that there is still no coherent, comprehensive, and user-friendly legal framework. However, we also see that it's a highly dynamic field, and the legal development is constant, and it's growing, and there's definitely a growing awareness amongst legislators. So there are already now some approaches that are very promising for the ramp-up of the hydrogen economy. Yeah, so there is some sort of a duality that you find when looking at the subject, and in this duality we also want to structure our short presentation, and I will start with a focus on the regulatory framework for hydrogen networks as like maybe more one of the problem childs of the issue. So what does it actually entail, or what is the key factor? We do need an effective regulatory regime for hydrogen networks. Why is it a key enabler? Because it is decisive for shaping competition and is crucial for investment decisions, and also basically the operation of a hydrogen network, or future hydrogen network to be precise. This regulation of energy networks is, of course, an already known topic. We have regulation of course, electricity networks as well as gas networks. And basically the starting point is that there's a lack of competitive pressure due to the monopoly of the position of the network operators. And because there's also a level of state guarantee to provide energy supply, there's the need for extended supervision, and this is done in form of regulation. And the aim is, as I said, to ensure effective and undistorted competitions. This happens in a couple of core areas. We have grid connection, of course, grid access, so third-party access, for example, as well as grid charges. And one of the contentious issues as well is unbundling, which basically describes that there needs to be a separation of activity between production and supply, which does fall under like a competitive stance, and on the other side, the transport. So as we've seen, there is already of course, there are already regulatory rules for networks, but how does it show for hydrogen? I want to focus here on pure hydrogen networks. There's also rules on what happens if you blend in natural gas, but basically, very shortened, usually this would mean that it falls under regulation for gas networks. And regarding pure hydrogen networks, we have a transitional regulatory approach in the ENVG, or the Energy Industry Act, since July 2021. And here we see that there's not an obligatory regulation, but the hydrogen network operators can choose to submit themselves in a way of an opt-in into a regulation. Upon this voluntary submission, certain rules apply regarding network access as well as network charges and also unbundling, but broadly one could say there's still a high level of flexibility because this whole legal framework is set out to be transitional, especially also because there are rules expected on the European level. In our study, we dive in this in more depth. However, the particular legal uncertainties coming from this framework would basically just jeopardize the frame a little bit. So one of the very contentious issues is the pure hydrogen networks regulation according to the so-called gas package, consisting out of the draft of a directive and the draft of a regulation by the European Commission. So this is not yet in place. However, it is through this one can, to a certain extent, anticipate what the idea is for the hydrogen market or for pure hydrogen networks. Shortened, we have basically no opt-in possibility, but after a certain transition period, grid access and grid charges will be regulated more or less comparable to gas networks. However, there are also unbundling rules that are horizontal as well as vertical. And here we do see, or we have identified that this is in fact potentially could become an obstacle on the way to the ramp-up of the hydrogen economy. The question, of course, is why is that? It's not in principle wrong to assume that we will need certain unbundling rules. However, at this point in time, we're still in a nascent market and we are looking at the phase of ramp-up. In this phase, the Commission draft entails that there's the phase out of the ITO model, so one of the unbundling models for the transmission system operators. There's no separation of network level. So no separation between transmission operators and distribution operators, as well as horizontal unbundling. And also this would probably have to be explained a little bit in more detail, but what it amounts to is that those are even more strict rules than are now for the unbundling on the gas market. And this essentially puts a limit to the incentive for the conversion towards hydrogen out of the gas network, because it will pose a limit or an obstacle to investment. And also there's fear that there will be ineffective duplication of structures, in particular through the horizontal unbundling requirements now in the draft. So what is the outlook on this particular problem? So as I said, this is only a draft, and the coordination on EU level is ongoing, and there are numerous critical voices, particularly with the unbundling requirements, not only out of industry and businesses, but also the rapporteur to the Energy Committee voiced in his report a different opinion on what the Commission has stated, and also we're still waiting on a parliamentary decision. We see there's still there's a high level of unclarity with this regard, and we do see that this combination of legal uncertainty in combination with potentially very strict rules could pose a problem. And with this a little bit dire outlook, I will now give to my colleague Leonie Ohle for planning and approval.
Thank you very much. I excuse a bit for my voice, it's the cold season. So I will now shed some light on planning and approval law regarding hydrogen networks. I'll try to give a brief overview, but also try to go into some details that we consider quite interesting. So the key factor, obviously, of which you all must have heard, I think, is the acceleration and simplification of permitting processes. The European Commission has already identified this as a hindrance, like the slow and complex permitting processes, as a key obstacle to unleashing the renewable energies. So as renewable energies are also a key factor for the ramp-up of hydrogen, hydrogen infrastructure is in these legal developments, in our opinion, not enough considered, so it should be equally considered as important as the unleashing of renewable energy. In this regard, we for example, have a council regulation laying down a framework to accelerate the deployment of renewable energy, and it would be sensible to implement an equal framework for the hydrogen infrastructure in this regard. So what general leverages do we have when we want to accelerate and simplify those permitting processes? We, of course, have to digitalize the administration. That's, I think, a well-known issue in Germany. We could also add some senates to the Bundesverwaltungsgericht because legal protection is always still taking up a lot of time. I will go into that in detail later, where it is most important. And most importantly as well, the expansion of human resources and professional expertise is also very important, and I will point out the detailed legal issues where that is really necessary in our opinion. So now coming to the legal perspective regarding acceleration and simplification of permitting processes. We have two sides to that. On one hand, we have the approval process. On the other hand, we have the legal protection. Both sides can take up a lot of time, up to many years. So what legal leverages are already implemented regarding hydrogen infrastructure? We have two leverages. Like one is the implementation of the construction of hydrogen pipelines, that comes with some acceleration, like legal acceleration tools regarding, for example, the early admission into possession. We have the possibility of an early construction start, and we have a concentration effect on a formal basis, which means that every material decision, like every legal aspects, are included in this one formal decision by one authority. So this can have a acceleration effect, but this needs to be accompanied by the human resources and the legal expertise on the side of the authorities. I will go into that later as well. Then, most importantly, we have now a legal privilege for the conversion of natural gas pipelines to hydrogen, which I will explain also on one of the next slides. But first, I will also shed some light on the legal protection, where we can change some areas there to accelerate processes as well. For example, we can shorten the appeal process directly to the Oberverwaltungsgericht or the Bundesverwaltungsgericht for certain infrastructures. When we deem like some infrastructures as crucial, that is possible, and I think we would all agree that hydrogen infrastructure could be such a crucial infrastructure, so it would be, a direct way to the Bundesverwaltungsgericht for legal protection claims against such infrastructure projects. We could also have an adjustment in interim legal protection, and such legislative projects are already in departmental coordination, so we can expect some legal developments in this area, taking these steps very soon, actually. Well, now I would like to go a bit more into detail of the construction of new hydrogen pipelines. As I have already said, it is now integrated in the planning law regime of the ENVG. As a procedure, we there have a quite long and complex procedure that is also due to this concentration effect I have just mentioned, and it thus ties up a lot of resources on the side of the applicant as well as on the side of the authorities. So it is crucial at this point to further the resources in this regard. The planning law regime entails a planning justification that is needed, and this again entails public and private interests affected must be weighed in, and there comes a huge legal step into place, namely that hydrogen pipelines are now considered in an overriding public interest until December 2025. This is parallel to the overriding public interest of renewable energies. Actually, in our opinion, we don't see why it is timely limited, so the time limitation should be dismissed, actually, because most projects will start after 2025. And then as well, within this planning justification, we have a determination of the energy needs. So the paragraph 1 ENVG determines that we have to have a safe, affordable, and consumer-friendly supply of hydrogen. And this leads me to demand planning. We currently don't have an integrated demand planning. We have different demand plannings for natural gas networks, for electricity, and it would be sensible in this area to have a strategic and integrated infrastructure planning, so an integrated net development plan. Now, the most important aspect, in our opinion, is the legal privilege for the conversion of natural gas pipelines. A scenario based on the TSO sees that 70 to 80% of the hydrogen network is to be established from converted natural gas pipelines. And here on the slide, I just put on a comparison of the planning approval that I've just mentioned and the procedure for the conversion. So there we have a notification procedure. We always have a safety notification procedure, which just aims at determining whether an equal level of safety can be guaranteed. We might have a further notification procedure, a so-called third approval decision that aims at determining whether the changes made to the pipeline are not so significant that it can be approved without a formal procedure. So this stands against the planning approval for new pipelines, where we have a complete examination of all legal areas affected and an extensive public participation, a limitation of the overriding interest, as I've already said, when the time, like when December 2025 has run out, we go into a very deep weighing of all the interests affected by infrastructure projects, which takes time and also gives some legal uncertainty of the outcome of the decision. So we now have to, it remains to be seen if those approaches to accelerate those procedures are sufficient. In our opinion, it is already a step in the right direction. This leaves me with an outlook. Well, as I said, the legal focus is now on the expansion of renewable energy, which also obviously helps the hydrogen market ramp up. But hydrogen infrastructure should also be integrated in these developments in more density. The current legal approaches already show potential to accelerate those permission processes, but need to be accompanied by according human resources and also the legal expertise that is not in place in authorities right now. And it remains to be examined to what extent those privileges can be transferred to other hydrogen infrastructure elements, like, for example, hydrogen storages. For the moment, we don't have the same privilege for the conversion of hydrogen, conversion of natural gas storages into hydrogen. That could be also an idea to have a similar privilege. And we don't have, for underground cavern storages, hydrogen is not implemented into the mining law. That means that we don't have the framework, for example, for underground cavern storage for hydrogen. So this is also, these are elements, white spots so-called, that we identified. And with that, I will give over to my colleagues, Elena and who will present the work of the regulatory community. Thank you.
In the interest of time, we unfortunately have to keep our final message short, and my colleague Cecilia Gitsch and myself would like to invite all the project partners, in case you have spotted any regulatory aspect that you would like to incorporate into your research design, or even more importantly, if you are working on something that can provide some relevant input research-wise to solving the regulatory topics. We are looking forward to hearing from you and talking to you. Thank you.
Much for this very insightful presentation on the topic of regulation, and thank you for being so tight in the time frame. So the panel is open for questions from your side. Mara?
Maybe there's no other question. You elaborated on the unbundling issue in particular, also the issue on unbundling natural gas and hydrogen infrastructures for distribution and transmission.
Sorry, could you repeat the question, please?
You elaborated on the issue of unbundling.
Yeah.
And like one issue that is on a key focus for TSOs and DSOs is the issue of natural gas and hydrogen infrastructure to be separated after 2030. And
yeah. So
can you elaborate a little bit on the pros and cons And
so with regards to the unbundling, as I said, the rules are a little bit more strict as they are now laid out in the draft. Regarding the vertical unbundling, as I said, we have the ITO the ITO model that will be faded out, and instead the ownership unbundling. Additionally, we have the horizontal unbundling for hydrogen network operators and gas network operators, which is a legal unbundling, but nonetheless, will again lead to like not the most perfect use of synergies that we should have. Because also, as has been shown on the planning approval side, we want to develop our hydrogen grid out of the existing gas grid. And through the current rules, or at least in the draft, this seems to make it complicated in a way that is not really necessary. So the Commission, in my knowledge, was hesitant with the ITO model already in the gas field, which is still unlimited possible. But there's no real reason why this model, which is also in a way has proven to work, particularly also in Germany, to be dismissed at this point.
Thank you. With the ITO model.
So this would, I mean, as I said, our study mainly focuses on identifying barriers. So this is definitely, in our opinion, it is an issue, just in particular for the starting phase of the ramp up.
And I think this is also the next step, sort of identifying first the gaps, but how can we sort of fill it with content then, and in order to go for an efficient hydrogen economy. Are there any other questions from the audience? Can we have a microphone here in the front, please?
Thank you very much for the really nice overview. You have focused on the national regulation. Do you know how the other European countries, is there more ITO models in the European countries, or is it also the ICO or only ownership unbundling models? I mean, like, we're speaking about European perspective. So from the German perspective, I understand about the synergies. But if the Brussels will decide, they will, of course, consider all the countries.
Absolutely, and I'm not an expert on the construction of these companies Europe-wide. As far as I know, it is different. The ITO model is here, it's the popular one. For example, I think in the Netherlands and Belgium, it is not. It's the level of the state, so there is a different sort of ownership unbundling anyway in place. But I don't think it's about choosing the best model, but to offer the flexibility at the start of the ramp up, especially if there's like no real identifiable detriment to it.
Can we hold the question maybe, because I get a signal that we have the honor to connect with our Minister of Education and Research, and we're very honored to welcome Ms. Bettina Stark-Watzinger with us. Welcome. Thank you for joining the conference.
It's a pleasure. It's an important topic you're talking about today, so I'm very, very happy to be here. So, dear Professor Schlögl, Professor Rackwitz, Mr. Langham, ladies and gentlemen, recently we've learned it the hard way. It all comes down to energy. Energy is the key issue of our time. For industry, for wealth, and thus for our ability to fund the goals we have as a society: education, infrastructure, social systems. And I know tonight I'm preaching to the converted, but anyhow, oil, gas, and coal, they create dependence. And Russia is using this as a weapon. We are aware of this every single day. But above and beyond this, fossil fuels generate more than 80% of greenhouse gas emissions. They're the main cause of climate change. They are responsible for global warming. We are therefore focusing on sun, wind, and hydrogen. We are betting on renewable energy, on greater independence. And I'm firmly convinced that green technologies made in Germany are an opportunity for us to seize. We cannot just wait for the fossil era to come to an end. This has also become clear at Sharm el-Sheikh. We must act now with great commitment and speed together with our European partners. It is our task to jointly build the climate neutral economy with creating more wealth rather than destroying it. It is our task to reverse the trend at this historical turning point. And Germany has set its goal to achieve climate neutrality by 2045. Renewable sources of energy are the basis for this. Today, they account for 1/5 of our energy supply, and we need to massively increase this share. But this is not enough. We will not be self-sufficient even in future. We are a highly industrialized country, so we cannot rely solely on green electricity. And this is why we need hydrogen. It is a versatile energy carrier, safe and clean, and it contributes to our sovereignty. Hydrogen enables us to store solar and wind energy. We can reconvert it into electricity as required. Hydrogen provides a climate neutral basis for industry. So importing large amounts of green hydrogen from far off countries is also a good thing for our partners. Green hydrogen, for me, is the missing piece in the puzzle for a climate neutral energy supply that we can count on. Green hydrogen is a once in a century opportunity, an opportunity for prosperity to grow. Climate action is the business model. So what do we have to do? We must now combine all our efforts and accelerate the upscaling process. Research and development are crucial in this connection. They make the difference between success and failure, and they are the drivers of progress. Progress means hydrogen technologies which are efficient and suited for practical use, which enable us to produce, store, and transport green hydrogen. And that is the purpose of our natural hydrogen strategy. That is why the Federal Research Ministry is so dedicated to support hydrogen research. We will provide roughly 700 million euros for flagship projects, and we will continue to provide massive support in the coming years. Research is the beginning. A start has been made. We now need to build completely new supply and value chains. And the 3 flagship projects aim to remove the obstacles on our way to a green hydrogen economy and enable us to use hydrogen on a large scale. This is how we ensure the transfer of green technologies into industrial use. This makes Germany a trendsetter. The TransHyDE project is one of key importance in this respect, because grids and storage systems are essential. They are the backbone of the hydrogen economy. They ensure that hydrogen arrives where it is needed. They link producers and consumers of hydrogen. And this is why we now need a hydrogen infrastructure, which is firstly internationally linked, secondly anticipatory, thirdly integrated, and fourthly technology neutral, and which is planned accordingly. Internationally linked means based on a European network of pipelines. This includes ports where overseas imports of hydrogen can arrive. Secondly, an anticipatory infrastructure must be established as part of the upscaling process. It will ideally anticipate supply and demand in order not to hamper their development. And thirdly, we must plan the energy grids in an integrated manner, combining electric power and hydrogen, gradually converting gas grids. In this way, we exploit reciprocal effects and build an intelligent grid for a climate neutral future. Of course, hydrogen pipelines will not be sufficient on their own. There must be alternative means of transport, but it is not yet clear how to best achieve this. And this is why, fourthly, technology neutral development, it is so important to also provide for the possibility of transporting hydrogen carriers and products by ship. TransHyDE creates the prerequisites, planning the hydrogen grid, covering different technologies. You, ladies and gentlemen, are demonstrating how this can be done. At a test site in Lingen, where you are analyzing how hydrogen can be transported in pipelines safely and efficiently. You are exploring ammonia, liquid hydrogen, LOHCS, and high-pressure spherical storage tanks. For this very purpose, you're working together in research and implementation networks. This is what I mean by combining knowledge, combining our efforts. So one point is in particular important to me. We must now focus on workable solutions, and we must do so quickly. Trade is a good example. The oil refinery is a major employer in the Uckermark region, and it is an important supplier of fuel in Eastern Germany: diesel, petrol, kerosene, fuel oil, and liquid gas. But what about the future if no more oil comes from Russia? What happens if we become a climate neutral economy? TransHyDE has just published a paper which presents alternatives to oil, how Schwed could switch to green hydrogen and to synthetic fuels. The aim is to quickly enter the hydrogen economy and at the same time develop approaches that have not yet reached maturity but offer potential. Something which seems still a long way off is the combined transport of liquid hydrogen and electrical energy. But this may soon change, also thanks to your research, dear participants. So one thing is certain: research and development, they are the key drivers for making green hydrogen the energy of the future. A mega trend. Ladies and gentlemen, the times are changing, as Bob Dylan once sang at the beginning of a new era. And now again, we are experiencing rapid change. Now more than ever, we must see the crisis as an opportunity so that we are no longer dependent, that we protect the climate, that we modernize German industry. So hydrogen means progress. This is how to transform the energy system. Let's get down to work. Let's make Germany a hydrogen republic. I wish you all the best for your conference, and I'm looking forward to discussing the results with you. Thank you very much.
Thank you very much, Ms. Stark-Watzinger, for your support, for your inspiration that you're giving our team here with the TransHyDE projects. And we're very happy having received you and hearing your words and all the trust that you bring to us and put into the projects. And I'm sure what we heard today will make it happen. So thank you once more, and give her once more a big applause.
Pleasure, and thank you. Take care.
And you heard it during the day. We have very many questions that arise in order to tackle and establish a well-functioning, efficient hydrogen economy. And we're bringing the questions up now to a panel discussion with high-level representatives from industry, from science, of course, but also from the civil society. And I have the pleasure to introduce to you our moderator. She's Lea Waleska-Giebel, currently head of the international grids at the German Energy Agency, and she's got more than 15 years of experience in the energy field, especially in the maritime area. And please welcome together with me, Lea Waleska-Giebel.
Thank you, Dorothea. Welcome to you all. It is my pleasure to be the host of our last exchange here today. And yes, the question of this panel is, how can the techno-economical and regulatory gaps be closed in order to expand the hydrogen energy, and now in a timely manner?
And that is a key question. We heard that speed is in order, and that's also the challenge a bit about this discussion. We only have an hour, but I am super, super happy that I have such a great panel here that I will introduce, and I think we will have a very joyful roller coaster ride here through the issues. First of all, I would like to ask Ulrike Hinz here to the podium. Ulrike Hinz is a policy advisor for climate and energy at the WWF Germany, focusing on power-to-X technologies and hydrogen. She has been also working in a electromobility company, and she has also been working at 50 Hertz, with the German one of the German TSOs. So I'm very happy you're here. Thank you. We also very happy that Mr. Bark is joining us. I think he was supposed to sit here. Mr. Bark started already in the 90s at VWG, and then from 2006 on, he joined the subsidiary of ONTRAS, where he is since 2008 in his current position as Managing Director, Controlling and Development. So very good to have you on the panel. We have, I'm looking, we have online with us. Hello, Mr. Kusch. Good to have you here online. Thank you for taking the time. Mr. Kusch was appointed in January 2002, so this year, until 2024 as the General Director of ENSOC, so the European Network Transmission System Operator for gas. So thank you for taking the time. Previous to that, he was a Deputy Director, and he will probably go back to that, Director Gas at Gas System, that is the Polish Transmission System Operator. Mr. Kusch, thank you.
Thank you. Great to be here with you. I hope you can hear me well.
Wonderfully, great.
Perfect.
And then Professor Rackwitz and Professor Schlögel, please join us here. There are 2 seats left. Mr. Rackwitz, I don't think I need to introduce you. You were introduced this morning. Professor Schlögel is director of the Fritz Haber Institute of the Max Planck Society. Both are here to represent this flagship project of TransHyDE. They are coordinating it commonly. And yes, they are both not only doing this, but also advising the German government, the German parliament, and various other institutions. So yeah, I think we have a wonderful panel for an hour. I would like to give Ms. Hinz, Mr. Kusch, and Mr. Barke the opportunity to have an introductory statement reflecting on how this immense project can contribute to a European vision on hydrogen infrastructure, because we're now elevating it a bit from the national level to the European sphere and back. And to your opinion, what knowledge gaps are addressed here and can be filled? So maybe ladies first.
Thank you very much for the invitation. I guess it's a little bit hard to follow up on the Ministry of Education's words, who's already given you a very good insight why these projects are important. You're all working in them. I want to step back maybe a little bit and look at the bigger picture, why we are all here, why are we all doing this, what is the hydrogen economy in general, or the power-to-X technologies. And I think they also are just involved in the energy triangle as we know it. So it's about prosperity, economic prosperity, it's about energy security, and it's about climate protection. And we always have to find the best solutions in these 3 dimensions, basically, and act clever on that. And I think one of the obstacles, we've just heard it before in the presentation from the Incl as well, of course, is the expansion of renewables, because that's the absolute basis that we need in order to establish the hydrogen economy. I think, and that's very nice that we have this panel today about regulatory gaps. There's a lot of regulatory gaps which now have to be filled in order to give planning and investment security, because there's so much money which needs to be invested in so many things that we have to do, because of course the hydrogen economy is an important cornerstone in order to reach our climate goals. And thirdly, and this is of course more related to the TransHyDE project as well, is transport. How do we get the different hydrogen
to the place where it needs to be, and where is it produced? There's a lot of open questions here, and therefore I'm really happy that this project exists and that there's so many intelligent people working on all the obstacles and the technological developments.
Great. I maybe switch to the online guest, Mr. Kusch.
Thank you very much. Once again, good afternoon, and I'm really glad to be here on behalf of ENTSO-GSO, the organization that is representing all the transmission system operators for gas in Europe. And to start, maybe to set the scene of our panel today, I think that I can only allude to the words that were raised already by the introductory remarks by the ministry, by the German ministry representative, that we need infrastructure to build hydrogen economy of the future. We need infrastructure to fulfill our goals, and as you know from this year, our goals, our European goals to set up hydrogen economy are even more ambitious. So we have to act in a way that we support the rollout of these challenges that are posed in front of us, to put Europe on the way to decarbonization, but doing it also in a very safe manner, and also remembering that we have to create the solutions that will be affordable and that they will maintain the industrial competitiveness of our continent. And here I believe that infrastructure and existing assets are stepping in to provide for this synergy in terms of cost and in terms of speeds. And I think that the biggest challenge, apart from probably the regulatory aspects that we'll discuss today during the panel, is also to bridge this top-down approach with the European goals with the bottom-up activities that will, let's say, prepare us to go for this long and challenging journey. And let's say that each journey starts with the small steps, and I believe that these small steps will be only possible with the support of such projects as TransHyDE, or going more into details into these H2 areas, where basically thinking about the future, we have to prepare and set up all the important technical safety material things that we are ready, and we are building the framework that is sound and that will last for years, and that will provide also all the aspects and the risk, then the concrete activities within the development or repurposing the existing infrastructure. So this is, I see as let's say, value to provide real hands-on experience and knowledge to everyone who wants to step into this important area of developing the hydrogen infrastructure.
Yes, thank you for sorry for my voice. Thank you very much for the invitation. And of course, we have, as ONTRAS, as an TSOs, they are playing with numerous current practical projects at the moment. For us, it's very important to have this platform to address our question that we have in the technical area, of course, also in the regulatory area. We heard this very good presentation before. And of course, a very crucial thing for us at the moment is how we find an appropriate way to finance this project. If we look on the risks that we have for the usage for these new assets and so on. And therefore, I'm very happy to have this platform and to address this. And hopefully, we also get some positive results from this.
Thank you very much. Maybe one quick note. We decided here on the panel that it's been such a nice, lively discussion also with you in the audience that maybe a quarter to we will open for questions and invite you also to come in. Until then, we will maybe keep it here. And I also forgot to inform you, as it's still in the program, that Mr. Georgios Chatzimarkakis obviously is not with us. Unfortunately, he had something, the CEO of Hydrogen Europe, which of course lacks a bit an interesting perspective, but I hope we can all make up for this. This brings me also to the question that was also risen by Mr. Barke, financing and planning. That was also the last presentation. I heard from Mr. Kusch, he's very much for a bottom-up scenario. There's also, when you look at Europe, the possibility from top down. And if you really look at Europe, I mean, even though we heard Australia is really willing to come in, we do have very good production sites in Europe. And we also have, especially in Germany, very good storage site, naturally. But of course, this means we also have very great transmission needs. And my question would be maybe to Mr. Kusch, as you are now a European representative here in this group, what do we do if some of these very important, let's say, transition countries hesitate to give pathways? So let's have transition pipelines built through. What can be done?
Okay, I will maybe stop here to let's say look maybe in general at the role of infrastructure and how it is needed. We already heard that we need interlinked, we need integrated and anticipative approaches. And what you rightly mentioned here, that with this task we have to, as I said before, we have to look in general what are the transmission needs. And for this, I think this is also another aspect of such setup of meeting in a different setup, not only discussing infrastructure itself. We have to have this look along the whole value chain. And here, as you said, in Europe, the very important thing from the side of infrastructure is to really determine the geography of the potential production sites and look where there will be the applications of and usage of the hydrogen for the customers. On the other hand, we also have to remember about this, let's say, anticipative role. So we also have to plan, and we also, if we want to create the market, we also have to look at how this infrastructure can be done to serve then the future needs. So in an integrated manner to go towards setting up the big framework for them that can be used in the long term. And here I think that the approach of regulatory thing that you can provide for, let's say, a bit bigger capacity with TPA based on also repurposing existing asset is stepping in. On the other hand, what we see is that with these new ambitious goals that are represented in REPower, we have to be aware that Europe itself is not going to implement the goals for the production, and we also have to look at the imports of hydrogen from outside, be that through pipes, be that through the terminals, and this is also something that we have to take into account. And here with this question, we already started, and speaking on behalf of European TSOs and European infrastructure companies, we already start many of the actions that are targeted to support this development of infrastructure. First of all, we, for this year, as our regulatory task as ENSOC, is to provide the 10-year network development plan. And I can already tell you that there is over 100 hydrogen projects that have been presented by the various project promoters that will be then analyzed. And of course, they will then constitute the first wave of the projects that then can we will then start to see where the projects are being prepared by the promoters. So there will be already the official processes within the European infrastructure policy that will already show the first projects. And on the top of that, they will also be the first indicator to fulfill concretely the infrastructure need in terms of new European infrastructure policy. We all know that there is a new TENI regulation that addresses only the projects that are related to renewable gases and hydrogen, so not anymore the fossil gases. So this is also something that will help to determine which of the projects can become the projects of the European interest. And if you ask me then, which countries, if we have the cases of the countries that are maybe not willing, or we see the issue of transit countries that maybe not take on board this approach, I think that this is also the European processes that help to determine the main corridors, which help to determine the main avenues for the hydrogen. And through these processes, we will have to propose the setup, but also show that, for example, using of the existing infrastructure, which is also in the countries that will in future transit gas, is possible in a quicker manner and in a less expensive manner. So this is basically the processes we can apply. And finally, just one last remark. NSOC and other infrastructure operators are already working on a project to map all the existing potential and developed projects within hydrogen, to also show how the idea of the corridors that has been presented by the EU policy can be also visualized, and there will be very soon a map that will show all the existing and developed hydrogen projects in Europe in a different perspective and different players. So this is also our contribution to maintain the visibility of these issues.
Thank you, Mr. Kusch. I figured the answer is that there is already a lot of projects in the pipeline.
Yeah. Pipelines in the pipeline, that's correct.
The TNE regulation will set incentives, but we heard also from Mr. Barker that financing is a big issue. And we also just heard from the legal perspective that this whole issue of unbundling is still not solved. And I've heard that it could be that negotiations go on for at least another year. Well, you never know, but we've heard it. And as we all heard, speed is in order. Mr. Barker, I know it's a very tricky question to you. How can all these pipelines that we need be financed if there is so much uncertainty? Because we just heard it's very much a bottom-up thing. What do we do next year? And we cannot hold still.
Yes, of course, we cannot hold still. That's quite clear. And that's also not what we do at the moment. We are in the moment on a clear track to start the project. We have the first one around in the Saxonia-Anhalt area around the storage at Bad Lauchstädt. That will be the first pipeline that we repurposed up to the end of next year, 20 kilometers between the storage and the Leuna chemical industry. And we hope also the electrolyzers, equipments and the wind parks will follow this speed. And that gives us the possibility to ramp up with the first experience that we need for such a thing. You ask for the financing for this, of course, quite clear. What we get is a state aid for this project. That's covered not all the costs. That's also quite clear. And the other ones is, of course, we calculate with the fees for the customers. They will use the pipes. And that's exactly the main points or the main struggle that we have at the moment. If you look on our project, then we find out a huge major costs for new build pipelines, also as well as repurposed pipelines. And on the other side, we have only a smaller amount of customers. They will pay this. And if we will allocate all the costs to the customers, then we reach prohibited fees, and it's not possible to ramp up this market. And therefore, a special model that we, or not that we know, that we have heard for the DENA, is that we make a risk sharing in this issue. That means the usage. We start with the financing from the TSOs. We have a clearly timestamp after maybe 10 years, and then we look around. Have we reached the usage that we need to cover all the costs in this area? Is this not the case? Then we could share the risk from the financing issue together with the state, and that would be, for me, an appropriate starting process to ramp up this process.
Yeah, I heard this framing of the DENA model before. Yeah, yeah, it's a state guarantee you're opting for. Okay. Now that we are already on European level, there are many other things that are undecided. You hinted towards it, Ms. Hinz. There's also a revision of the regulatory directive, and there are some subsequent delegates acts that everyone awaits, and they're heavily discussed, especially when it comes to criteria of the renewables that can be used for the production of various products. And also with relation to greenhouse gas emission limits. Is your organization, the WWF, are they happy with the current drafts? I mean, this is also a bit of a backbone to build up the whole hydrogen economy. What is your stand there?
Yeah. The renewables directive and the certain amendments. which should be decided hopefully very soon. The trilogue is happening right now, so hopefully the Commission and the Parliament can come to an agreement there. Just for a repetition, so in May the Commission made a proposal on the RED, including a delegated act, which includes additionality, so using additional renewables for the production of RFNBOs, so renewable fuels based on non-biological origin. And this, I think, is very important to understand that we live in an energy system as a whole, and eventually only if the renewable capacity is additional to what we have already, then we can also fulfill our climate goals and actually go into that transformation direction that we want to go to. Because if we use renewables that are already in the electricity sector, then of course in the electricity sector they have to be replaced, and they're going to be replaced by fossil fuels. So this is really important to take into account. I understand from a business perspective that an electrolyzer is obviously more economic if you run it on more full load hours, of course. But eventually, like this directive, which is laid out now with a delegated act, which is now in question, they have a transition period there as well, which was first until 2027, now it's until 2030. And to be honest, that's still a bit of a time, and that actually gives a lot of incentive to realize your hydrogen project as soon as possible, because all of these conditions in there actually don't grasp at the moment until 2030. So that could be actually a bit of a ramp up of hydrogen economy as well, if you will. Yeah, I just want to mention that I think it's really important that renewables are additional. We use otherwise curtailed electricity, and we of course expand renewables. And this is the electricity criteria that is in there. I might even want to go a little bit further. I don't know if RED is the right place, or if it might be the Hydrogen Pact or the G7 or the G20. But it's also really important to talk about sustainable and fair trade, international trade, because of course we will be dependent on imports as well, as we are already in Germany, but also in hydrogen and hydrogen derivatives. And I think there's a huge chance to build up a sustainable, great hydrogen economy, if you will, internationally, strengthen partnerships, improve our situation, be able to defossilize and decarbonize our industries and some parts of the transport sector, and just make sure that all of the partner countries benefit from that. And I think this should be considered in the discussions internationally with all stakeholders at the table.
Mm-hmm. Thank you. Well, still in my blog where it's about planning and financing, setting the framework, maybe if no one else wants to comment, I would ask to Professor Schlögl and Professor Rackwitz a bit. We heard today a lot about also the modeling and very important the supply and demand modeling. And one question that I had that was striking me is of course the assumption how much demand is there. We heard it also, it's crucial. But then there's this news coming in of big industries, energy-intensive industries, maybe leaving Germany. We heard it from Mr. Habeck when he was still in Schleswig-Holstein. We have the energy, we have the space, come to us, but what does it mean on a global scale for Germany? These assumptions, have you been in contact with regard to that in the TransHyDE projects? Any assumptions on this variable?
Thanks, Johan. Sure. Let me start with your last point and then also elaborate a little bit on the others. Of course, there's a competitiveness issues for energy-intensive industries, but it always has been there. And if I talk to steel manufacturers, for example, they also say, of course, coal got a little more expensive, but steel is way more expensive. So some of them are also at the moment quite profitable. And we have to make sure that we understand this transition as an overall European and national challenge and endeavor where the state provides the correct long-term framework conditions, and based on that, the companies will invest. And also the Minister Stark-Watzinger mentioned it is now the chance to make an opportunity from the challenge, where we of course see that natural gas prices will be higher in the next 10 years than we expected it to be a year ago. And that will make also climate neutral energy carriers, hydrogen in particular, more competitive. And therefore, I think there is a clear target picture, because you mentioned energy intensive industries. I will elaborate a little on that, how to transform them, and that large parts of the energy intensive industries also can remain and will remain in Europe, because there are integrated value chain and production chain from steel to final products like cars. And what is now really needed is that first we have to agree on a common target picture in terms of prioritizing demand sectors. We are quite well advanced with this already. Then it is clear that major parts of our hydrogen demand will be imported and will be produced from central sources like offshore wind energy. And for those, we need really strong infrastructures, pipelines, but also other harbor infrastructures for ammonia, for example. And it is quite clear that we need system development strategies and plans for strong transmission infrastructure from Northern Africa to Northern Europe, in particular connecting the harbors. And for that, we need the scientific analysis in terms of developing the models for system development plans, which we develop, among others, here within the TransHyDE project. And so my wish to policymakers and regulators would be to go ahead quickly with these obvious framework conditions we see. Energy-intensive industries will have to decarbonize. We will need large amounts of hydrogen and low-carbon energy carriers. They will have to be imported to a large extent and also produced based on central renewable production opportunities. And for that, we need now the planning of the infrastructures. The tools are here being developed, and now let's come together and apply these tools and go forward with the regulations, and also with this we will support within the TransHyDE project.
Super. Great.
Now, from my point of view, I consider myself as sitting here in the machine room of this whole activity, because after all, you're talking on very high level on administration, on technique, on legal thing, on finances, but the whole thing has also to work. And of course, we as scientists, we are responsible that everything works. This sounds trivial, but it is not as trivial as you would think, because parts of this technology, they are well proven, and there's no problem that this can be done. So what we have heard about these projects that are on the way and that we also have in TransHyDE, they are okay. So there is, from the technology or science point of view, only the possibility to make it better or make it cheaper. But there are other things that are by far less clear than it is being said at the moment. The first thing is, what is the correct transport form of hydrogen? This is by no means clear, because there is no world-scale transport of hydrogen at the moment. This is PowerPoint, what we do at the moment, techno-economic analysis. And the future will show that I'm sure there will be more than one opportunity, and we will see a mixture of carriers. This is pretty obvious to me. Now, when you do an analysis, then you find that in all of these transport chains, there are stumbling blocks that have not been solved yet. There are very nice assumptions being made to help you over these stumbling blocks, because it's far away in the future we get first started. And that is, of course, the problem in TransHyDE, that we really identify these technological stumbling blocks and we really work on them. And sometimes I'm a little bit surprised that we do not show the necessary openness to see that we are not sure what is the real solution yet. At the moment, everybody thinks, this is hydrogen in pipelines and this is ammonia in ships, and more or less this is it, because all the other things are a bit left aside. But we are not sure whether this is the only and the real solution. We have to see this. So technology openness is the most important thing that I can ask from the scientific viewpoint. And then we have to see that some of these issues, I still think they are undercritical when it comes to research activities that are in there. Because if you want to, by 2030, a world-scale hydrogen transport network everywhere, then we have some technology bits that are at the moment only existing in the lab. And it is very well known from chemical industries, from lab to large to world scale, you take usually 15 years. So this is 8 years for 15 years, so you would have to enormously speed up the activity. And I do not see really the feeling that there are some critical issues that are way too slow that we are still dealing with them. To cut a long story short is, I see no reason that we will not be able to solve this problem from the technological point of view. There is nothing where I would say there is a stumbling block that is a risk to our concept. The concept is perfect and this is fine, and we need this. We need definitely a little bit more flexibility in our thinking, because when I hear we make now the planning of who is needing what kind of hydrogen carrier when, where, then I would say, Naya, you think this in a time scale of 30 years? I'm not sure that I can plan this for 30 years. There's no way. So the flexibility in the planning is something I think that has not been clearly outlined enough at the moment. And as I say, there are 4 or 5 technological issues which I think are over-researched, and there are about 4 or 5 technological issues that are under-researched. So a rebalancing of our efforts, I think, would be quite useful.
Yeah, we would need these results first because, yeah, as you also said, we have not much time, and even though this openness is very nice, it means a lot of resources in many LAs, and that is slowing down.
We could also say
that is a trade-off I see here. But thank you for bringing it up. It's also the next cluster I think we should discuss, speed and coordination. Yeah. And here I would like to turn to Mr. Kusch again. We've all read, if you like it or not, from NSOG, there should be a new NSOC, so to say, for hydrogen, ENNOH. And I was thinking when I read this proposal, I mean, the ENSO-E and the ENSO-G, they're doing really good work, but the vision, for example, for a really well-working European, let's say, integrated power system is not yet fulfilled. ENSO-G maybe a bit more, but they had decades, so to say, and now there is a new player on the market and it has to deliver, say, in 10 years. Can you give this new institution some advices? How can they speed up? What kind of roadblocks do they have to skip over? Because it's an enormous task.
Thank you. It's a very valid and good question. And if we look at the regulatory proposal, and then if we set it together a bit in a contrast in what we were speaking just before, and I think the word integration and cooperation was named here very many times, I would say that we don't see, let's say, creating new extra organization or new extra, let's say, organizational setup as something that goes along these lines of integration and basically facilitating. What we observe here is that we have to look really still in the let's say, abiding the principle of energy system integration, and of course the question that is posed if not everything was achieved, I say that we look at the perspective that much was achieved, having in mind that ENSO-E and ENSO-G are existing since 10 years, and they have already developed a set of very important aspects that basically put a sound basis on a long-term vision for energy, for let's say, for the energy system setup. And here I will once again allude to what we aim for is to have this integration between, as we are sitting here, we are all aware that the future will be electrons and molecules, and we have to plan this future in this very close coordination, not setting up another, let's say, separated avenue for the separate, let's say, as it is set energy vector, but plan together and look at all these interlinkages between how we see the long-term decarbonization and long-term functioning of the system, where molecules and electrons and the molecules, firstly of natural gas, then going to the low carbon gases, RFNBOs, biogas will be will be present. And this is also let's say the joint work that is being handled to provide this in coordination with electricity, but also embracing the policy goals that stem from the latest EU goals of the REPowerEU. And then based on this, we can produce together, and we can work together on our 10-year network development plans, which will then cover the gas, but we'll also have to look at where the electricity will come from and how we can then work together to make the most of the alignment for the resources to produce the future fuel. Finally, maybe towards that we can look at also a pragmatic manner. If we need synergies, if we want to speed up, then if we look at the let's say constituency of these new actors, we see that the majority of them will be the current infrastructure companies that operate gas pipelines, and they will be there to step in as the first ones to repurpose and to prepare this networks for using the hydrogen. And it will also be of crucial importance to also maintain, doing in an efficient and of course cost-effective manner as they are allowed and as they are given the certainty, like it was said before, which is also of crucial importance. And for us, it's also importance of certainty, but also to provide for all what is related to safety and security of supply throughout all the process. If we go for repurposing, we have to really work closely and see how the assets are interdependent, how the assets are moving from gas to hydrogen, and how the system can be also stabilized between these molecules. And the last thing you also alluded when we discussed also the future policy framework, it is very needed that this stability is also there, because then the long-term actions, the long-term exercises cannot, let's say, finish with saying that, okay, in 2024 there will be no more TONDP prepared, whereas we are already working a sense of on TONDP 2022 that will have natural follow-up and natural tools that are being now developed on cost-benefit analysis and on system interdependence. So there are many of, let's say, arguments that it could be made in a different manner to somehow build on integrating what is on the molecule side for infrastructure.
Thank you, Mr. Kusch. We are very fortunate that Mr. Barke is also since 2009 in the management board of NSOC. Anything to add, you think, from your perspective?
Yeah, I could I would underline Piotr's mentioned content. I think we have often heard today the speed is the key for this whole process. That's the one point, and the other point is we speak about long-term investments with a huge amount, and therefore we have to be careful how we will handle this. And one of this, I think, is we have to be sure that we could use the synergies that we have between the natural gas assets that we have at the moment and the people they maintain this, and the new upcoming hydrogen assets. I think that's very important to save money and to have a lot of speed. And in this direction, I see the words from Piotr and the discussion about the NZOH, that we say it makes no sense to split up this in both directions. I think we have to deal this together and to save the money and to have ramp up the speed.
Yes, I also understood that it's a very close collaboration between NSOE and NSOG that also started for integrated planning, and the new entity shall come in. That brings me also to a point which I really liked here, is also this TransHyDE project is also a lot of an integrated view, really, and I really like that. But I also like the question from the audience that how will this result be made public? Where can I read this? Do you have this in English and all this? So this would be my question regarding speed and coordination to the coordinators. As we heard from the minister, large sums also in the coming years, so much money, but the other countries might need to learn about it, the European level might need to learn about it. How are you ensuring in TransHyDE that this bridge is made? What are your tools for that? Apart this great conference, where obviously people on European level are participating.
Okay, as a scientist, of course, it is the easiest thing to do is we communicate this on the scientific levels, and we are pretty active on that. So I think the science layer is very well coordinated, not only in Europe, but globally. And this is something that is sometimes a little bit underestimated when it comes to higher levels of communities that are outside of the scientific community, that there is a lot of communication ongoing. Where I see a problem is in the translation. So the scientific language on one side and also the scientific agenda is not necessarily always suitable to inform the decision makers. And the decision makers have an agenda that is completely decoupled from the scientific agenda. That is also something where coordination is more important. So to a certain time, you take decisions that are scientifically not ready, or you simply don't know what science knows. And also what we learn is that the speed of this decision-making is sometimes frightening to me, because as you said before, we're talking about long-term developments that have consequences of 50 to 100 years, and then we take 6 months' time to decide on this. Well, okay, whether this is a wise idea is, I'm not so sure. On the other hand, we have the pressing need. That means this is a disjunction that we only can overcome if we try really to use this platform idea. And science talks to decision makers, and decision makers take the effort to come and talk to scientists before they take decisions. Usually we get it the other way around, because we tend to learn about decision-making agendas from the newspapers. At that time, it's way too late. So it would be very nice, and this is also something what TransHyDE is not so bad at, that if there is something in the political air, then it would be good to come in due time and try to negotiate with us, to discuss this with us. The knowledge that is in this community, that is in this room, is enormous. But it is difficult to tap on it, because when you try to read scientific papers, you have not the time to translate this. We can translate our knowledge into what decision makers need, but we do not know when decision makers need what knowledge. And if you just throw it out, as we do it usually, then it is also wasted, because then we say, 2 years ago we had this nice paper, but you forgot about this. So communication platforming is the most important thing. I do not think it is necessary to invent new things, but it would be very nice if this Bringschuld, Hohlschuld issue would really be taken serious on both sides.
In the English issue, I learned.
The English issue, as I say, we have no problems in discussing this, and we have lots of European activities, so you can certainly allude to that as well. And I'm very well connected in the European level, and you're also very well connected, probably even better than I am. But this is not seen everywhere. And something that before I end, I have to say to you, it is also super important that our communication gets better, because sometimes we tend to see us as some kind of enemies or something, but we are no enemies, not at all. We should really try to do so. NGOs and scientists are natural allies, normally, I would say. And this is something that I would very much welcome, that this is a little bit more intensified.
That's a strong expression here today.
Can I answer that just very quickly? Because at WWF in our climate and energy team, and I think generally we are very scientific focused, so we really try to base all of our analysis and our opinion forming, and then what we advise politicians to do on facts and research and science. So I would not agree with science and NGOs being enemies, probably. But it's good to discuss that. We can continue.
We can continue on this. In my capacity as Vice President of the National Academy, I can tell you I have heard this in quite different views. It is good that you do this differently.
Yeah, Robert Schlögl has essentially set the key strategies and issues we are following here in TransHyDE. But I think there is also this duty on our side that we try to work on relevant issues that are also relevant to our counterparts on a policy level. And this is really something we strive for. For example, looking at a European and even pan-European dimension of a hydrogen infrastructure, we have to also talk to the European level. That is something which we started, for example, with developing the scientific research innovation agenda, also with BMBF, and that was communicated with the European Commission. And that now has to follow on, for example, for infrastructure regulation. Certification is a very important issue, and we have probably done very important steps, but there needs to be continuity. And then we have to publish also results on issues that are pressing at the moment. One example is that Minister Stark-Watzinger has mentioned the paper on Schwedt. That was one example where we tried to be as quick as possible and give an answer which is relevant for a pressing current issue. Another example is the one I've mentioned on results on European gas security of supply, where we used the modeling framework within the TransHyDE project and could answer relevant questions by policymakers. And I would also would like to thank to our excellent team in the coordination and communication team, which really have working hard every day on communicating results to the broader public sphere and also to the decision makers. And now I think it's going to be important for the next 2.5 years remaining project duration, where more and more results will be produced and where we can build on this excellent basis and then really scale up the publication and communication within the project.
That is a very good. Sorry, it was not as bad this morning. It's the air here. Many people are coughing. I promised to open to the audience a little bit before the time ends. That would be now. If there are questions from the audience, I think we're all very happy to take them. Otherwise, I have plenty more here. Are there any questions? Yeah, from chat, I see.
Yeah, so we got one question from the virtual space again. I think it's a question for the whole community on the stage and also virtually, Mr. Kusch. Why should taxpayers subsidize energy-intensive industries while big parts of the energy-intensive industry, like the automotive industry, are making high profits at the same time?
Who wants?
There are externalities, like from the economics point of view, you try to find instruments if there are negative or what type of externalities, like for example, environmental externalities are covered by a CO2 price or instruments on CO2 reduction. And at the same time, here for the hydrogen economy and infrastructure, we have so-called innovation externality. For example, in like steel industry, the first mover, if the first mover steel producer would cover all the costs to drive down the cost of a technology, it might not recover all the investment from his or future business of being the first mover. And therefore, in like economic theory, you would subsidize this type of innovation externality as long as the technology is specifically expensive. Like, for example, we have this carbon contract for difference, but it has to be clear that that these instruments have to be phased out when technology costs come down, and market forces together with CO2 emission constraints and instruments will be the key driver. So this is only a transition period where certain demand for innovative products are incentivized. And by the way, we've talked a lot about the infrastructure. The infrastructure costs will mainly be covered by grid fees in the midterm. There will be a transition period for the introduction of hydrogen infrastructure, where there will be investment incentives possibly, or other instruments, for example, for the IPCEI projects. But in the medium and long term, these costs will be covered by grid fees, and grid fees are not subsidies. They just natural instruments to allocate costs. Yeah.
But I've heard you two want to join in. Please.
Okay, thanks. Maybe I come back to my initial statement of the triangle, basically, of climate protection, prosperity, and energy security. And we are in a transformation process right now, you've already said it. And we are not doing this transformation for fun, let's say, but we're doing this in order to reach our goals. And these are societal goals, in order to do something for society as a whole. And every transition that we've always had was costly, and there was always a financing part from the state and other means that we needed in order to scale up mobile phones, the internet, everything that we know nowadays, right? It's always been supported in the beginning because transition will cost money and will incur changes. And I think that's really important to understand. I mean, we have to act clever upon this, and of course we have to phase out subsidies when they're not relevant anymore, or if they're bad even, especially. But I think it's in every transition there will be costs occurred. And I think it's also dangerous to always to communicate that the energy transition doesn't cost anything. That's probably not true, because it is a transition, and it's really important that we work there together. Otherwise, people might be frustrated eventually, and acceptance would go down. And if acceptance goes down, then we will not be able to realize all of our infrastructure projects, especially expansion of renewables, as we see it in certain regions. So I think it's important.
I would agree with anything that you just said, and of course also with what you said. But I would like to add something. It's clear subsidy for the energy transition is not subsidy for making more profits, but this is subsidy in order to come over the transition barrier. And this is why it is temporarily and in dimension has to be limited. The EEG was a very good example at the beginning, how valuable that was. We wouldn't have renewable energy in the industrial stage if there hadn't been an EEG. The mistake was there was no exit strategy to this. So the exit strategy of such subsidies, this is a different thing. But I would like to say very clearly, more important than subsidies from the state would be clear boundary conditions. So the rule-setting part of the state is way more important. Because industry can much easier come over the transition barrier if they know exactly the rules. But if the rules change all the time, and the energy rules tend to change every couple of months, then this is, of course, very difficult for long-term investments, for infrastructure, for business cases in as I say, infrastructure. So the most important thing that the state should do is not try to throw out money to this transition, but to give clear-cut rules, and they are simple enough, they are technology open, that you really can rely on these rules for decades and not for months.
Yeah, but it's also a very volatile transition where
the general things are very clear. We have decided we want to step out of fossil energy, and this too quick as possible. So this is a very general rule. There should be no exceptions to this. Okay. And if that would be said so clearly as we do it here, then this would be very helpful.
Okay. Mr. Kusch, now, is there more? You wanted to say something?
Yeah, maybe I will just. I cannot comment on subsidizing, let's say, energy-intensive area. What I can say is that in the case of infrastructure, it is quite important, and it is practiced for years with our EU energy policy. To support infrastructure to address those externalities. Yeah. They used to be security of supply, and they still are security of supply. They still, in some areas of our continent, were also promoting the competition going along this triangle of goals. And now we face the externality of sustainability. And this is something we have to do as quick as possible. And we are fully aware that the first stage and the first, let's say, decision to invest and to develop the infrastructure for new gases will not be something that will be market driven. And then we have to provide the stability through the infrastructure that is supported by public funds in many cases to foster the markets. But what is also very important mentioning that infrastructure costs a fraction of the market that will be created. So this is a small cost that will leverage the bigger developments. This is the first thing. The second thing is very important to know that each subsidy in infrastructure that is being built is not increasing the cost of this infrastructure. We as, let's say, the infrastructure operators that profit from public money, they are not double counting them into their regulated asset base. So this money is not being charged to the customer again. So this is this leverage. And the third thing I want to also allude that having this integrated approach between assets that are used in a classic manner to the assets that are used for the new gases, we can also see that already some of the assets that have been already amortized or let's say depreciated can also serve to mutualize some of the costs and let's say decrease and provide the value, let's say existing value to the new gases, so make also this transition a bit cheaper. And this is also an important part of this new regulatory package that should be allowed in the long term.
Mr. Kusch. See nodding here. Are there more questions in the audience or online? There is a question here in the front. Can we have a microphone here?
Thank you. Transitioning over to hydrogen, so we might know, or we're researching on its safety, and we will have it through to be safe. But how can we communicate this with the whole society? Because people could be afraid that all of a sudden they have a hydrogen pipeline close to their house and could be afraid of explosions or something, which, like, we keep an eye on that they don't happen. But yeah, what's the strategy there? Is there a strategy?
Yeah, the acceptance is a good topic. Yeah.
Maybe I come a little bit from the project that I'm working in, the Power-to-X Copernicus project, and we deal a lot with the topic of acceptance as well. There's surveys with like 2,700 people about what they know about the hydrogen economy already and what they don't know yet, and if they favor it, if they're in favor of it, but also what kind of infrastructure they like in general and in your own backyard. Of course, always the same question. And it's really important, I think, to take the society with us and all the people with us for several reasons. For the acceptance reasons, so not to have blockages when we have to create infrastructure, secure infrastructure, of course, but also to teach our society which kind of jobs will be needed in the future, right? There's so many jobs with the hydrogen economy in general and all kinds of levels. So it's also like just important that these people understand what is the chances in the future, especially young people, but all people, and to take political decisions, which every one of us does basically every day as well in terms of electing and all of that. And what we do in WWF, for example, we try to now educate the public a little bit with different methods. Yeah, for example, we have a virtual reality experience, which we're now distributing. We have an e-learning module, which is now available. That's just for that, but I guess in general, it's important to understand that participation in general is important, and which like level of participation. Is it information? Is it consultation? Is it real participation also in terms of monetary incentives, or like being able to invest in the own infrastructure project in front of your house? This could also really lead to acceptance. And I think this has to be evaluated on a very regional and not project-based, but at definitely regional level with the inclusion of the society.
I can only underline what you just said. It is acceptance is only half of the story. Participation is the important part. And we have to be open also to the development, and it would be very good, and we try to practice this, that we include, of course, the public in our research work, because as soon as they begin to understand what we are doing here, they usually lose also their possibly negative, say, prejudices on this. So be open and be transparent is super important. And I think think that is something that we do already. We practice this, but possibly we can even become better than we do it at the moment.
Thank you.
Do we have the time for one last question? Yes, I see. Is there one last question? This one in the here, third, fourth row, other side. Yeah, sorry.
One question: what do you think about the timeline? If you make maybe a target back calculation from the point we will go through, and if you know the time, maybe you will build up a new tank. It takes from the first step 3 years building time, or other things we need, pipelines or carriers or tankers for the sea. We need time schedule backwards, in my opinion. Do you know if something planning this, or is it?
Yes, of course. Thanks for this question. At the moment, as you know, we plan a pipeline of more than 900 kilometers around in the eastern part of Germany for pure hydrogen. That means the most of them is repurposed, but also new build pipes. And of course, we have some timelines very exactly. And the bottlenecks, of course, is the permitting. That's quite clear, and that was very often mentioned today. And I think there we need a change in permit to how we could reach permits in a very fast way without lose also our safetiness for these permits. I think it's very important. And the second one, of course, for the experience for the last years is the availability of the materials at the moment, and the services that we have to use from the market. But we have very clear views, and if I look on this special project of the 900 kilometers, we will finish this project, and we have to finish this project in 2027 or 2028.
Maybe one comment on that. I think if we extrapolate the timing we used to need over the last 2 decades for energy infrastructure projects, it's quite clear we will not manage the energy transition. There's no way. If we do not accelerate processes, we will just not be fast enough. On the other hand, we have seen how fast things can develop in emergency situations like during the last year. We construct LNG terminals in incredible time. We could, in principle, construct pipelines, and we get agreements on directives at European level in a few weeks instead of a year. And I think we need to, I mean, of course, certain policy processes cannot be accelerated infinitely, and also Robert Schlögl pointed at that for some delicate and difficult issues you need to take your time, but we need to find a new compromise. And like, for example, for first step, finding a common vision of infrastructures, we need to be quick now at European level to agree on a vision for a hydrogen backbone. I don't think we have the time to discuss between France and Spain for another decade whether a pipeline in France is reasonable or not. I think that should be quite clear. We have the modeling for that, and so agreement should be reached faster. And then we probably should have a look what we can learn from permitting procedures for LNG terminals for pipeline projects. But you mentioned it before, we really have to involve the public, and in order to not undermine acceptance for infrastructure projects, but we certainly need to find ways to accelerate and look at the experiences gained for the last 8 months.
Great, yeah.
I just want to add, this is extremely important, that if we would ever come to a point that we can agree on a roadmap, That would be so good. It's not that thousands of roadmaps, but they're not agreed upon. The point is we have to agree on a roadmap, because if we agree upon a roadmap, then we have agreed upon what are our targets. This is a precondition. And as long as we always start to discuss things in every little bit at the fundamental level, we will never make any progress. So it would be super good if one could do, as a first step, a real roadmap, not on CO2 targets, but on pathways. How do we achieve this? And that is something that I'm badly missing.
Okay, though not a very more warning note as a last word from the panel, but I think we should maybe close the discussion. We are a bit over time. I think it was a very insightful discussion. Thank you very much for everyone here on the panel, also to you, Mr. Kusch. I take away that we need transparent communication, and I also like the subsidies always with a limit tag on it, and we need a consolidated acting, whether it's a roadmap or on other issues like the backbone. And if you don't know, the TransHyDE project goes on for another couple of years, 25. So this is only the beginning. And we heard also that all the material will be communicated open and transparently. So I think the idea is to stay tuned and to meet again and discuss. Thank you, everyone.
Thank you, goodbye.
Valeska for moderating the panel. And I ask you, Mario and Robert, could you stay on stage? And because the TransHyDE project is coordinated also by 3 coordinators, and we have our third one here, who is Jimmy Langham. Please welcome him. And we'll have a wrap-up session of the day, and maybe you can give us also an outlook and the perspectives for 2023 for the TransHyDE project.
Yes, thank you very much, and good evening to everyone. You haven't seen much of me during the day. I was sitting in the corner and listening. My name is Jimmy Langham. I'm a colleague of Mario and Robert. I'm one of the 3 coordinators, and I was asked to do a wrap-up, a summary, and I said yes, and afterwards I thought about it, and I realized, okay, this is a high-class scientific conference. I'm coming from the energy industry. It feels to me like I'm the only one in the room that doesn't have a PhD. You are all tired, hungry, so me telling you what you have heard today might not be a good idea. So please allow me to share my personal thoughts, my personal findings of the day. I was involved right from the beginning at the birth of TransHyDE, when it evolved out of the Ideenwettbewerb for Hydrogen Republic in Germany. And I remember when we sat together, we had a bunch of ideas which had to do with storage and infrastructure, and they were all put together. And we tried to bring structure into that. And I remember we had some ideas that didn't make it into TransHyDE. We had some ideas that really got together to a new idea, which was really, really good. And most of the ideas are present here. And then we set up a structure. We set up the matrix structure with the execution projects. And then we started to set up a work plan as a decent scientific project does, at least I was told. And what we see now, and that's the difference to the last meetings, to the General Assembly we had, what we now start to see is we're starting to see results. And this is really what impresses me. We have the different work packages, really, there's outcome. No, the last 1.5 years we were busy sorting ourselves, getting ready, getting staff, getting all the necessary equipment together, and now we're producing results. And one of the personal findings I have is at the beginning we had a discussion, what is TransHyDE actually? What is it? What are we? Who are we? And the picture, I'm an architect, I need pictures. The picture I'm always having is we are a toolbox. We are a toolbox for hydrogen infrastructure, and when I get asked, what's the silver bullet? Is it going to be ammonia? Is it going to be liquid hydrogen? it was said before, there's not going to be a silver bullet. It's going to be a toolbox, and this toolbox is unfolding before us. And what I can only say is that toolbox doesn't get better if I lay it out on the workbench and I discuss it. I need to use these tools, and we are starting not only to develop these tools, but we use these tools, and this is good to see. The second thing is, when we started up with TransHyDE, the world was a different world. Well, we had so many changes. First of all, we didn't foresee many of the things we are dealing with now. For example, the intense regulatory community we have, which is discussing regulatory barriers. We hadn't foreseen that. Otherwise, we would have set it up differently, and there would have been another regulatory work stream. And the same goes for many, many other topics which we hadn't foreseen. We have not foreseen the Ukrainian crisis, for example, where, for example, the Schwed paper or other imminent work packages, activities have evolved from. So we are in a position where on the one side we need to fulfill our work plan. On the other hand, of course, we need to react to what's happening around us, and we need to react to current crises. We need to speed up certain things, but still, again, work on our work plan. And that's a challenge to the TransHyDE community, which I believe we are, I must pass that back to the work packages, we are doing well. We are doing well within the constraints of resources we have. And the next and the last thing I believe is what I'm, my finding, we're not even halfway through TransHyDE yet, but it's 2.5 years to go. And what we need to start thinking of is we need to start thinking ahead. Because we don't want to, at mid or at beginning of 2025, say, hey, it's been a nice time, let's wrap up and go home. But since the target originally was to build up a hydrogen economy in Germany, we need to think of what's the next step? What's beyond TransHyDE? What do we do once we've finalized our work plan? What do we actually need to do next? What's behind it? How can we scale up the scale up? And that is something where we start to think about now, and it's going to be an intensive part, I think, of the next 1.5 to 2 years to really see how we scale up the scale up. And these are my personal findings of today, and I know I'm expected to buy some time for the catering, but I think it's not going to be dinner anyway before 6 o'clock. I would also take the opportunity, before I hand over to my colleagues, to thank the team behind this conference, which is, of course, the coordination team of TransHyDE. First of all, Dorothea for this excellent role as a master of ceremony, which I think is worth a big applause. Then, of course, all the work packages and everybody presenting and working in TransHyDE, which is a lot of people, a lot of competence really concentrating in TransHyDE. Many thanks to all the work packages, to all the presenters today. And also many thanks to the team behind in the different companies that supported the ones on stage with their work. And with this, to my best knowledge, Dorothea, I think dinner is at 6. And I would pass on to my colleagues. Thank you very much.
Thank you. So we have microphones. Actually, nothing really to add to what Jimmy said. And I think when I think of what comes next, which you mentioned also, the idea of the toolbox is really to accelerate the process in order to help to achieve these extremely ambitious targets. There's only one key performance indicator for the technology platforms that are rolled out by BMBF, is that we really bring our contribution to reaching the 2030 targets. And they are incredibly ambitious, 660 terawatt hours of hydrogen or green energy carriers in the EU until 2030. I cannot see at the moment how you reach that. But the excellent thing about this toolbox is that we are producing tools which many can use, and then the acceleration will work by distributing these tools further and using open source results of the TransHyDE project. And I just want to give a few examples along our research projects. First, in the system analysis, we produce modeling results, and many of those results are based on open source models, on models that also other teams around can use and which they should use in order to elaborate and develop system planning further along with the results produced in the TransHyDE project. Then in the infrastructure, in the second project, secure infrastructures, I've learned today that the tools that are developed in order to check whether steel types are hydrogen ready for existing and new built infrastructures can be used also by other companies in the market, and so we are developing results which should spread over, not stay within the TransHyDE team members, but really spread out. And then also for the Apply project, I've learned that connecting electricity and liquid hydrogen transport can be also used in other real-world applications, and where now the first application cases and use cases where multiplying those results should be found. And similarly, in the AMORAF project, we have learned from Campfire how to use catalyzers from AMORAF, and I think that will not be restricted. It will be used in really in order to scale up for example, ammonia as a transport carrier. And last but not least, for the results presented in this NORMS project, I've also learned in the coffee break that companies are urgently waiting for the results to become public to use it in order to develop their projects along standardized norms and schemes. And therefore, that would be my vision, really, to develop results which can be used by a broad crowd out there, and we're contributing with that to reaching the 2030 targets and to scale up and to reach the next step. And with this, I'm really looking forward for the further collaboration within the next 2.5 years within the TransHyDE project.
Now, 2 minutes and 16 seconds before dinner, there is not much to say. I think I have to do two things. I would like to thank all of you in TransHyDE that you made a significant journey from 90-something partners to now really a platform that is working. So you said this in special, and I say this, I want to reinforce this. This is maybe the most valuable tool that we created, that this is now really a platform and that can really go on also in other directions. So this is stable and this is practical and this is working, and we all should be, I'm very grateful, and we all should be proud of this. And the very last thing that I have to say is I have to thank these two guys. So it is really important that this group of coordinators, this only works because we have a very close interaction and we understand each other, and we have this COCO team that multiplies this understanding very well into you. And I think this is a good working relation between backward and forward and between us. And I think this is one of the most important success factors that we have created in TransHyDE. So I should thank you all, and in particular, I want you to give these guys a great hand, please.
No.
And I think in the name of everyone here present, we thank each one of you for all the guidance that we have received in the project during the last 2 years. Also, you made it happen that this project could be sort of sponsored by the Ministry of Education and Research. And I think we all together, hand in hand, form a very strong team. And thank you all for the participation, for the great results, and the support that you three have given to us, the guidance also to the coordination and communication team. Thank you to every member of it. And We are looking forward to the next 2.5 years to really make this hydrogen economy sort of function and do the best from our side for the storage and the transportation infrastructure. So I just heard dinner is ready. We do not need to wait until 6 o'clock. So whenever you feel ready, it will be served downstairs in the basement. So you go to the registration desk from this morning, turn to the right, go downstairs, and there you find a dinner space. And I would like also to take the opportunity to say goodbye and thank you to all the participants who were on the live stream, and say bye-bye from here, from Berlin. And we're looking forward to a great communication, networking evening with all of you tonight. Thank you. Yeah.